Hey, Radu, when do you plan to start with the introduction of the workshop and in general? I think you can go ahead if you feel like.
We'll start soon.
Okay. Actually, let me see. Okay. Yeah, so whenever you want. Actually, it is starting to fill the room, so yeah. Is everything okay, Radu, from your side?
Yes.
Okay, good.
Andrey, should I proceed?
Okay, yeah, I think so. Okay, hello everyone. My name is Andrey Ignatov, and together with Radu Timofte, we are the organizers of the Mobile AI 2022 workshop. Welcome everyone to this event. The main workshop event is now happening on site at VPR, and the workshop is also streamed live on YouTube. And all presentations delivered at this workshop will be also available on our YouTube channel, so you will be able to check them later as well. This workshop is a very practical event. Besides talking about the thing how to make the model smaller and lighter, we are also talking about how to deploy neural networks on mobile hardware, how to optimize them for edge devices, and this optimization do not necessarily require cutting some layers or shrinking the network. And we also will talk about how to make the networks compatible with dedicated mobile AI accelerators. This event is actually a continuation of our last year mobile AI workshop, where we had lots of talks on efficient AI for smartphones and for edge devices. Last year, we had a large introductory talk providing an in-depth overview of mobile deep learning software and hardware. We were briefly checking all key optimizations needed for fast machine learning inference on edge devices. And we have also briefly covered the topic of power consumption of mobile MPUs. Today, we'll also have an introductory talk, and at the beginning, we'll have a quick recap of what we discussed last year, a quick recap of how we can run deep learning models on mobile devices. And then we would mainly focus on the latest updates, on the latest hardware and software updates that happened during the past year. Additionally, we'll also check Android, Apple iOS AI ecosystem, and we'll see how we can deploy TensorFlow light models on Apple devices. And we'll even check how good is the performance of the latest Apple A15 SoC. And finally, we'll review the burnout benchmark that is introducing a novel paradigm of combining computational performance, throttling behavior, and power efficiency of mobile SoCs. Last year, we had a number of invited talks from all major SoC vendors that introduced you to their AI hardware and software. There were presentations from MediaTek, Qualcomm, Samsung, Huawei, Google, Imagination, and Synaptics. If you haven't checked them yet, we recommend you to check them. Today, there would be a few more presentations. In particular, MediaTek and Qualcomm will introduce you to their latest software and hardware platform updates. They will tell you a lot about power, about efficient deep learning, about power consumption optimizations, and about efficient inference on their devices, on their platforms. Today, Intel is also joining our workshop, and they will introduce you to their software and hardware optimizations for AI inference that can be found in their processors for mobile and laptop devices. Synaptics today will introduce the optimizations and the changes they made during the past year. In this talk, they will also provide lots of information about the Synaptics VS680 platform, and for all participants of the image super resolution challenge, you should probably not to miss this presentation, as this platform is used for performance evaluation of solutions submitted in this competition. And finally, Huawei will present the performance test of their cloud servers that can be used for performing AI workloads for mobile devices remotely in the cloud. The last part of our workshop, as usual, is tailored to efficient software solutions for smartphones and for mobile devices. Again, there were lots of interesting presentations last year, and there would be a number of very exciting talks today. Google, OPPO, Samsung, Lenovo, and some other institutions will tell you about their software solutions for portable devices and for smartphone devices. Okay, 1 second. Okay, good. And we will start with an introductory talk where we'll discuss software, mobile AI software that can be used for AI inference on Android smartphones and on some Linux platforms. So those of you who attended our presentation last year should probably remember this slide, as it provides a general overview of deployment of deep learning models on mobile devices. So this deployment can be split into 3 different parts during the first and 3 different stages. During the first stage, you need to train your deep learning model, and here you don't need to do any modifications. You can just use some standard deep learning library like TensorFlow or PyTorch. Next, you need to convert this model to a format that is supported by mobile AI libraries. So unfortunately, you cannot run the resulting TensorFlow, PyTorch, or TensorFlow model directly on mobile devices. Therefore, you will have to convert it to an appropriate format. So this is done during the second stage, and during the last stage, you take the exported model and run it on your mobile device with the corresponding deep learning library. And there are 2 main approaches that can be used for performing AI development for mobile devices. The first approach consists in using custom deep learning SDKs developed by smartphone SoC vendors. So each vendor presented their own solutions, and you can use these solutions for exporting the model, for converting this model to appropriate format, and for running this model on the corresponding hardware. The major problem with this approach is that all these SDKs, they support only hardware from the corresponding vendor. So this means that if you are using Qualcomm's SDK, you won't be able to run the resulting model on Huawei devices or MediaTek devices and vice versa. And therefore, if you want to design some general purpose Android application with AI capabilities, you basically need to convert your model 5 or 6 times. You need to integrate 5 or 6 deep learning frameworks into your application. You need to integrate 5 or 6 resulting converted models to your app. And then you will also need to maintain all updates of all these SDKs and fix all issues and so on. So in this case, we do not recommend you using this approach. And in general, you should use it only if you understand the difficulty of this path. So if you understand that, okay, you will be facing some particular issues and you know that you will be able to cope with them, this might be an interesting solution. But if you do not realize the difficulty of this approach, you should probably avoid using it. And instead, the second approach consists in using generic mobile deep learning libraries. The 2 most popular libraries are TensorFlow Lite and PyTorch Mobile. They all support, both of them support a subset of TensorFlow and PyTorch ops. Their operators and kernels are optimized for mobile inference, and by default, they are running models on smartphone CPU. But you can also accelerate the obtained models on AI accelerators, on NPUs, DSPs, by using Android and an API or delegates, and we'll talk about this just in a few minutes. TensorFlow Lite is considerably more popular library, therefore we'll start with it. To convert the standard TensorFlow model to DFLite format, you just need 3 lines of code. In the simplest case, if you do not want to do any additional optimizations. So you first just need to initialize DFLite converter, pass your safe model to this converter, run it, and then it will save the resulting DFLite model to your hard drive. And then you're taking this hard drive, this model from the hard drive, copying it to your application folder, and in your Android codes, you just need to initialize DFLite interpreter, define input and output tensors, and then run the model. And that's it. And after that, you'll get the outputs of your neural network. So in principle, it's quite simple. And as was already mentioned, by default, all computations will be happening on CPU. If you want to run your model on AI accelerators, you need to use one of the 2 available options. The first option is to use Android Neural Networks API. This is a part of Android operating system that was introduced in Android 8.1, and it serves as an intermediary layer between high-level deep learning libraries and devices' hardware accelerators. So how in this case the inference happens? So your machine learning library, like for instance, it's TensorFlow Lite, instead of doing the computation, it just parses the model and transfers it to Android Neural Networks runtime. Then Android Neural Networks runtime checks if there is some registered hardware, if there is some registered DSP or NPU or GPU that can efficiently execute this model, and if it exists, it passes the model or some layers to this hardware, it performs the inference, returns back the results, and Android Neural Networks runtime also returns the final output to your machine learning library. So in this case, machine learning library is not doing any computations at all. It's just, it also serves as an intermediary. And Android Neural Networks runtime, it cannot directly communicate to this hardware, to the specialized AI hardware. Instead, it communicates to an API drivers, to Android NN Health that is developed by the corresponding vendors. And this is a special drivers developed for Android, for this runtime, for Android Neural Networks runtime. So if these drivers are missing, then Android Neural Networks runtime won't be able to run this model on DSP or GPU or on APU, even if it exists. So all communication happens through these drivers. And if these drivers are outdated, if they contain some bugs, then you would have issues with acceleration. So you would have some problems here. So yeah, the most important thing that you need to remember that Android Neural Networks runtime on itself is just an intermediary. It cannot work with AI accelerators. Instead, it works with the specialized drivers that are developed, that should be also developed by SoC vendors. And if Android Neural Networks runtime cannot find any registered hardware, then it runs all computations on CPU. This approach is potentially very promising because in this case, you basically do not need to take care of different AI accelerators that can be found on your smartphone. You just do not think about it all. You just pass your model to Android Neural Networks runtime and it does all job for you. It just checks if there is some efficient AI accelerator, and if it finds one, then it runs everything on it. But this approach has basically two major limitations. The first limitation is fragmentation. You need to understand that NN API drivers, so these drivers, they are not fixed. And when SoC vendors, they are continuously improving them, they are introducing some bug fixes, they are adding support for new features, and they are improving their performance. So NN API drivers are changing. And in the majority of cases, NN API drivers are part of Android firmware. So to update them, you need to perform a full smartphone firmware update. And for this, your smartphone vendor should send you the corresponding update. And as you know, the situation with updates in Android ecosystem is quite terrible. Many devices are getting only one major firmware update. Some of the devices are not getting any major firmware updates at all. So therefore, right now we have more than 50 NN API compatible mobile SoCs, and for each SoC there exists several NN API HAL versions, having each own properties. And therefore we have a very, very huge zoom here. And for instance, if you take two different smartphones that have the same hardware and they run in different versions and have different NN API HAL, then you might get absolutely different results when performing the inference. So in one case, the model would be running much faster. In some other case, there would be some bugs, or the performance would be quite terrible. So you can never guess what would be the actual result. So, and you should be prepared for this, and you should add the corresponding logic to your application. Since Android 12, Google and Qualcomm are working on bringing updatable NN API drivers. Right now, they're working on bringing these drivers for only two SoCs, for Snapdragon 888 and Snapdragon 8 Gen 1. But everything is happening quite slowly here, and in general, this won't change anything dramatically, because you would still have these 50 plus chipsets that have different NN API HAL versions, and the fact that in case of two flagship SoCs, these drivers would be updated, this is not changing the entire picture. And the second problem, as we discussed last year, NN API supports only a subset of TensorFlow Lite operators. And with an API, you can accelerate only ops supported by an API. So in the latest Android 13 version that would be officially released at the end of August or at the beginning of September, there are still it has still an API 1.3 support, which means that potentially you can accelerate approximately 100 different TensorFlow operators. And this is enough for running the majority of common computer vision models. But you might get issues when using some non-standard architectures, when using some NLP networks, and when using some non-common layers or activation functions. So the question is how we can deal with this problem. And so with an API, so in general, it's a very, very good concept. It's a very interesting concept, but it has two main issues. First issue is fragmentation, and the second issue is limited ops support. And good question is whether we can overcome these problems, and the answer is yes, we can overcome them by using TensorFlow Lite delegates. These delegates, we also covered this topic extensively last year. These delegates these are libraries that are developed by SoC vendors for directly accessing the AI accelerators. And the workflow in this case looks as follows. Your machine learning library, instead of using an API path, it just transfers the model to TF-Lite delegate, and then this delegate runs the model directly on NPU, GPU, or DSP. And these delegates, you can just take this delegate and integrate it directly to your Android application. Using these delegates is also extremely simple. You are just copying the binary, you're just adding the corresponding binary to your app project, then you are initializing the delegate, and in TF-Lite settings, you just specify that this delegate should be used for inference instead of an API on CPU fallback. And that's it. And then the model would be executed with this delegate. And as we discussed, this approach has lots of advantages. First of all, it's independent of Android operating system. So you can just go download the latest version of the delegate, and you'll get the best possible support for all SoCs, regardless of, for all devices, regardless of the Android versions they are using. It also overcomes many Android and API limitations. It can provide implementations for ops not supported by an API. And in general, it also provides you with a better performance than an API path. And the main delegate that you should be aware of is TensorFlow Lite GPU delegate. We also discussed this last year, and this delegate is extremely useful. With this delegate, you can basically run any quantized or floating point model on any mobile GPU. And in case of high-end and mid-range mobile GPUs, you would be usually getting a very good acceleration. Also, this delegate can run very huge models because it can consume almost all RAM available on your device. And besides that, finally, TensorFlow Lite, and TensorFlow Lite GPU delegate, they are all developed by Google. Therefore, there is a synergy in their development. And TensorFlow Lite GPU delegate is usually the first one to get support for new ops and layers. And right now, it provides the largest ops coverage among an API and all other delegates. So the rule of thumb here is as follows. If you're developing something for mobile devices, then the first option that you should try is probably TF-Lite GPU delegate. If your model is not working with TF-Lite GPU delegates, then most definitely it won't work with an API and with other custom delegates. And so this is a general rule. So, and from our side, we strongly recommend you to use this delegate because quite often it can provide you with the best possible performance on legacy devices and on devices that are no longer supported by the corresponding SoC vendors. There exist also a couple of other delegates developed by several SoC vendors, and we'll cover them in a few minutes when we will be talking about the hardware from the vendor, so that you have a more clear connection between the hardware and software that can be used on it. And in this section, the last thing that we should mention is PyTorch Mobile. So the situation here did not change significantly since the last year. If you want to develop your solution with PyTorch mobile, with PyTorch, then you can, of course, run as a resultant model with PyTorch mobile. And if you're planning to run it on CPU, then you wouldn't have any troubles. So CPU performance is good, and we didn't observe any significant issues here. But if you want to run the resulting model on AI accelerators, then you have to use an API, and the current PyTorch and an API support is still not okay. So in general, if you're looking for new experience and for new adventures, then you can, you can try to develop AI model to develop AI models for mobile devices with PyTorch and an API. But if you want to use something more common and more mature, then we recommend you using TensorFlow Lite, as it has quite a number of advantages in terms of OPPO support and API support and delegate support. So the second very important topic is inference types. We have also covered this topic really extensively during the last mobile AI workshop event, and now we'll just have a very, very brief recap. So there are 4 major inference types that you should be aware of. The first inference type is FP32 inference type, single precision floating point type that is providing an accuracy of 7-8 digits after decimal point. And whenever you are training your model with TensorFlow or PyTorch, you are getting FP32 model. So whenever you have trained your super resolution network, this model is FP32 model. The problem with this inference type is that its accuracy is generally excessive for inference. It's important for training, but for inference, you don't need FP32 precision. And therefore, it's not used at all. And besides that, the majority of NPUs are not supporting FP32 inference. Therefore, if you decide to deploy FP32 model, you won't be just even theoretically able to run it on mobile AI accelerators. And instead, you should use FP16 format that provides a little bit lower accuracy, but this accuracy is sufficient for maybe 99.99% of use cases. It's actually a really complex task to find a model that will require FP32 precision than the model for which FP16 precision would not be sufficient. And in general, FP16 inference is faster, the model will consume less RAM, and the most important thing is that FP32 to FP16 conversion, it happens automatically in all mobile libraries. So you don't need even to do this conversion explicitly, you can just get the result in FP32 model and set the flag in TensorFlow Lite or TF-Lite GPU delegate, and these libraries would automatically convert the original floating point 32 model to FP16 format. So from this slide, the main takeaway message, you always need to use FP16 format instead of FP32 format, unless you really notice that there are some issues with the accuracy. You can go even further and you can perform quantization of your network. You can switch from floating point inference to quantized inference. And this is something that is referred to as quantization. The general idea of this procedure is, again, super simple. You're taking the original floating point weights of your model. Suppose that they lie between interval armin and argmax, and then you are just mapping all these weights. In the simplest case, you're mapping linearly to interval from 0 to 255. And then after this mapping, you're also performing rounding of the resulting values so that you are getting only integer values. So that's it. You're just mapping floating point models to integer values. And there are also lots of advantages of this approach because it's obvious that the model becomes much smaller. In general, intake models run faster on almost all hardware. They consume less RAM. They are more power efficient, and there also exists lots of mobile NPUs that support int8 inference only, so they can technically not run FP16 or FP32 models. But these advantages, they come at the price of accuracy loss. So you understand that if you are just converting 32-bit or 16-bit weights to 8-bit weights, you will definitely lose the precision. And the good news is that this, in case of threshold-based problems like image classification problems, this loss is usually negligible. In some cases, you won't be able even to see any performance degradation. So in these cases, you can just easily use int8 quantization, and you shouldn't have any major troubles. It works also for simple image processing tasks like image super resolution, basically for residual-based image processing tasks, and it does not work for the majority of complex vision problems that are involving heavy image manipulations, and also this approach rarely works for NLP problems. So int8 inference is also very important, but when quantizing your model, you should always look at the resultant accuracy, because in some cases it might surprise you a lot. In some cases, you might just notice that the model is just providing you with some random output that are even not that much correlated with the outputs that the original floating point model is generating. So, and there exists also one additional inference type in 16 inference. Compared to int8 inference, it offers a much wider dynamic range, and this solves the majority of accuracy issues. But there are two major issues, major problems with this inference type. It's not supported by many NPUs, and there is still no real support in TensorFlow Lite for it, and in PyTorch Mobile as well. So if you want to perform int16 model quantization, you should use vendor SDKs. This is the only option right now. And on this slide, I have also provided you with some additional links showing you how you can quantize your model, perform integer quantization of your model with TensorFlow. Here you can see several possible options. So for those of you who are participating in the quantized image resolution challenge, you should definitely check this slide. And we have covered almost all major topics related to mobile software and inference types, and we can now switch to mobile hardware and see the major hardware updates from all SoC vendors. And from the first point of view, it might seem that there is also a huge zoo of different AI accelerators, that everything looks quite complex, but as a matter of fact, we can classify everything in just a few minutes. So we start with Qualcomm chipsets, and in this case, you can find three different types of AI accelerators on them. The first type is classic hexagon DSPs. You can find them in these Snapdragon SoCs. So these DSPs support int8 inference only, and yeah, they can be found in old Snapdragon platforms. More recent Snapdragon SoCs have hexagon DSPs with hexagon tensor processor, and this HTP can also run only int8 models. And in the very recent Snapdragon chipsets, you can additionally find second generation. Well, it's not an official naming, but for simplicity, we can call it second generation hexagon tensor processor. It's available in Snapdragon 8 Gen 1 and 7 Gen 1, and it can provide it provides support for both floating point and quantized models. If you want to run AI models on Qualcomm hardware, you can use an NAPI, but besides an NAPI, you can also have two other options. The first option is hexagon TF-Lite delegate, and with this delegate, you can run quantized models on classic hexagon DSPs. So on DSPs from this section. This delegate provides usually better results than an API, and in general, we recommend using it. The only problem is that it would be soon deprecated, and it would be soon deprecated in favor of Qualcomm QNN TF-Lite delegate. So right now, QNN TF-Lite delegate provides full support for hexagon DSPs with hexagon tensor processor. So basically, these two types of AI accelerators. And it basically complements Qualcomm hexagon delegate. And it also offers quite good support of OPS, better support than an API does. Additionally, it provides you with a possibility of running models on Adreno GPUs. So it's also provide an alternative to TFI GPU delegate. And it has lots of options allowing you to balance between performance and power consumption. This delegate would also gain support for some older hexagon, for some older classic hexagon DSPs, but it won't, most definitely it won't support very old DSPs that can be found in Snapdragon 835, 821, 20, and some other chipsets. So this is all with Qualcomm hardware. In case of MediaTek, you can find in MediaTek chipsets, you can find 4 different generations of the IA processing units. The first generation supports integer models only, and it can be found in these 4 chipsets. Newer APUs, they provide support for both floating point and quantized models. Second generation APU can be found in Helio P90 and P95. Third generation in the last year Dimensity chipsets, and the 5th generation in the last year Dimensity SoCs. And you might have the same question as we had. So where is the 1st generation APU? So technically, the 5th generation APU is the 1st generation APU, but 4 is not lucky number in China. Therefore, 4th generation was skipped. And we basically saw the same situation with Qualcomm last year when they introduced Snapdragon 888 chipset. In terms of naming, this did not make any sense, but 8 is lucky number also in China. So traditions. If you're deploying your models on MediaTek devices, then you can use MediaTek Neuron Delegate. It supports some of the MediaTek Dimensity SoCs. You might notice that it's not supporting every single Dimensity chipset. So for other SoCs, you need to use an API. And on this SoCs, it allows you to run models directly on MediaTek's API. Then we are moving to Samsung chipsets, and this slide is full of pain. So right now there exists only one chipset that has an NPU accessible by external developers, and this is the last year Exynos 2100. It provides support for integer models and only for unsigned integer models. So it does not support, it is not supporting signed data networks. And because of this, if you're using the latest post-training quantization toolkit from TensorFlow, the resultant model would not be compatible with this NPU. And it's accessible through an API only. You know that Samsung recently introduced Exynos 2100 chipset, and here we have a very interesting situation. For the first time during the last 5 years, we have the case when the chipset did not get an API drivers, and there are no final working delegates for this SoC. So on Exynos 2100, external developers right now cannot access its NPU. A little bit more pain. So last year we mentioned that Samsung had Samsung presented add-in delegates supporting a number of Exynos SoCs. Right now, this delegate was deprecated, and after the initial update of Samsung devices to Android 12, it was completely broken. And we just recently checked that right now it works, but anyway, it's deprecated and it won't be getting any updates. And it was also deprecated in favor of Samsung KNN delegate that is supposed to support Exynos 2100, but the development of this delegate is still in progress, so it's not finalized yet. So in case of Qualcomm, only one chipset supporting int8 unsigned int8 models. In case of Huawei, as you can expect, there are no major changes since the last year. We have 2 generations of NPUs. NPU developed by Cambricon that is available in Kirin 980 and 970, and NPU developed directly by Huawei that is available in these SoCs. And the situation with these NPUs is becoming worse right now because This, as you know, these Huawei devices are not getting major Android updates, and because of this, they are stuck with older API drivers, and there are no custom TF-Lite derivatives. And because of this, they are not getting new features and performance improvements. And in case of Google, you can find Google TPU in the Google Pixel 4 devices and Google Tensor TPU in the recently presented Pixel 6 devices. Edge TPU supports only int8 models. Tensor TPU supports both quantized and floating point models, and both TPUs are accessible through an API only. And this is the last slide. This is just for general information. In many mid-range and low-end chipsets, you can mobile devices, you can find Unisoc SoCs. So the majority of them do not have any NPU. NPU can be found only in the Tiger T710 chipset, and there were no devices released with this SoC. So, like, we expect that it is already deprecated, and we will probably never see devices using it. And a more recent chipset is the Unisoc Tiger T770. It supports only int8 models, and there are still no devices utilizing this chipset, but we hope that maybe something would be released this year. So that's it. We have just reviewed almost everything. We have just classified all mobile hardware that can be used for AI inference on mobile devices. And now we move to the next most interesting part, to benchmarking this hardware. And same as before, we are using AI benchmark for this. This is an Android application designed for checking smartphones AI performance. It is based on, it is relying on TensorFlow Lite in combination with Android and an API and TF-Lite delegate, and it is measuring the performance of CPU, the performance of APU, NPU, GPU, DSP, basically any mobile hardware that can run neural networks, and it is checking lots of different performance aspects. When running this benchmark, you can see a visualization of what neural networks are actually doing on your phone. And I believe that those of you who are using AI benchmark should have noticed that last year and at the beginning of this year, actually, we released AI benchmark v5, which size increased by a factor of 4 compared to the fourth AI benchmark version. And this is not because we just added there some films or lots of pictures. This is because we have completely revised the models and the workflows used for benchmarking mobile devices. And the number of tests just doubled. And let's review what tests we're using in the benchmark v5 for checking the performance of mobile devices. The first test is, as usual, this mobile net v2 architecture that is used on mobile devices very frequently. And as usual, we are benchmarking both floating point and quantized model. Second test is also quite traditional. It's Inception v3 network, also quantized and floating point model. Then section 3, it's the standard mobile net v3 architecture. Previously, we used mobile net v3 minimalistic network, but now we're using the largest architecture with hard switch activations that is showing quite good results, accuracy results. Section 4, it's efficient NB4 network. It's a very huge and very, very powerful network, providing an exceptional result on the ImageNet dataset and on many other classification tasks. Next section, we're running up to 8 models in parallel, up to Inception v3 models in parallel, and checking whether smartphone NPUs are able to cope with parallel inference, with a simultaneous inference of several different models. Section 7, it's a new test. We have a new test performing object detection, and here we're using YOLO v4 tiny networks that is showing one of the best performance and runtime results on mobile devices. Section 8, it's a RNN model that combines ResNet34 backbone and bidirectional static RNN, quite often used for optical character recognition. Sections 9, 10, it's the same DeepLab-3+ model, but right now it processes large resolution images of size 1000 times 1000 pixels. Section 11, it's IMDM network, very popular model for image super resolution and image restoration. Section 12 is RGAN network, again, a very, very powerful architecture, providing excellent visual results, but that is still very challenging for smartphones because it's quite heavy. Section 13, same as RGAN model, but right now the resolution is 1000 times 1000 pixels. Next, we have UNIT architecture. It's also a classical network used for image denoising and many other restoration problems. MV3 depth network performing depth estimation. By the way, this solution was developed in the previous mobile AI depth estimation competition by Tencent. And for those of you who are participating in the depth estimation challenge this year, we also recommend you checking the solution as it's really, really interesting. Next, classical DPIT network performing image enhancement, and in this case, now we are tackling images of resolution 2K, which is quite typical for many social media platforms like Instagram. PyNet Plus network performing performing bokeh effect rendering and processing images in parallel at several different scales. Then QNet model for learn smartphone ISP task. This was a baseline solution in the previous mobile AI competition, and it's processing full HD resolution images. XLR network performing full HD image upscaling and is able to deliver real-time performance on the majority of mobile SoCs. By the way, also developed in the previous mobile AI super resolution challenge. Then video super resolution network, a very very light model capable of performing 4K image upsampling. And you will see that on some of the platforms, it is also able to achieve real-time performance. Then we have a few NLP tasks, text completion with the standard LSTM architecture, question answering with a mobile BERT model, which results are just amazing. So the performance of this network is just awesome. And you can just try this model if you are interested in question answering. And Albert model, which is basically a competitor of the mobile BERT architecture. This network also can provide you with awesome results, and in this particular case, it's used for text completion. And the final test where we're checking what is the maximum image resolution that can be handled by mobile device when processing images with the standard ResNet model consisting of 12 layers or 4 ResNet blocks. So these are the tests, and you can see that AI Benchmark U5 has a really extensive set of architectures and extensive set of models of layers of ops that it is benchmarking. And in general, if smartphone is doing good with in AI Benchmark U5, this means that you would be able to run the majority of standard and non-standard architectures on it without any issues. After the end of the test, you can see the results of each network. So for instance, you can see the runtime of mobile network 2 model when it's running on CPU, on DSP, on GPU. You can see the accuracy of this model and many more information. And in the settings, you can also play with acceleration backends. You can switch between an API, between GPU acceleration. You can use custom delegates if your platform is supported by them. So lots of room for experiments. And additionally, it contains a pro mode where you can run all models separately. And moreover, you would even see the power consumption of different architectures on your own device. So for instance, here we can see that Inception V3, that quantized Inception V3 model consumes 5.5 watt and achieves an FPS per watt rate of 3.62, while the same quantized model on NPU consumes only 3.8 watt and achieves 50.5 FPS per watt rate. So we have more than 10 times power efficiency improvement here. And you can basically do this with almost all models from AI Benchmark V5. So same as before, we are releasing all benchmark results on our website. So if you go to benchmark.com/ranking, you will see the results for all recently released mobile phones. We also publish aggregated results of mobile chipsets. So if you go to mobile SoCs section, you will see basically aggregated results for each mobile SoC that is supporting AI inference. And I will briefly remind you the notations. So in this column, you can see the name of the chipset. Here is CPU configuration. Here you can see AI accelerator that is used for quantized inference in the first one. And the second one is AI accelerator used for floating point inference. Here you can see the library that was used for inference. In this particular case, it's QNN HTTP library for QNN HTTP delegate for quantized inference and QNN GPU delegate for floating point inference. And here aggregated results for quantized inference, for floating point inference, and some other results. And if you press on the view detailed results button, you will see detailed results you will see raw results for each chipset. So for instance, you can see that if you run the Inception V3 network on the Snapdragon 800 Gen 1 SoC, then the runtime of the quantized model is 1.3 milliseconds, runtime of the floating point model is 5 milliseconds. If you run the same models on CPU, then the resulting latency would be 61 and 132 milliseconds, and you basically get these results for any network for any chipset. And we have also prepared for you a visualization of the scores of the devices so that you can perceive the results easier. So here we can see intake performance of all mobile SoCs providing acceleration for quantized networks. Yellow bar stands for an NAPI 1.3 score, and blue bar stands for an NAPI 1.1 score. So in an NAPI 1.1 section, in an NAPI 1.1 category, we have very simple, very basic networks like MobileNet or Inception V3, and therefore it mainly shows raw computational performance of mobile devices. While an NAPI 1.3 section contains more complex models, and it shows you, it also shows you how good is the support of this chipset for different architectures and for different layers. And on this graph, on this chart, we can see that the performance of the latest generation SoCs has improved just dramatically. So if we compare and yeah, by the way, here you can also see the performance of the very first Qualcomm chipsets that had NN-compatible hexagon DSP, and you can see that during the last 7 years, the performance improved by more than 100 times. But even if we check last year chipsets, then we can see that the performance improvement demonstrated by the recent SoCs is in some cases 2 times, 3 times, or even 4 times. And with these chipsets, you can run very complex and large networks. This slide shows you the accuracy of all aggregated accuracy of all chipsets, and it shows you as a reminder that when you're running your model on your smartphone, you will not necessarily get the same outputs as you are getting on your laptop or on the server. Because of different optimizations, because of different bugs and some external parameters, the outputs might be modified. The outputs might not correspond to the outputs of the original TensorFlow or TensorFlow Lite model. And you should be prepared for this, and you should always check if the outputs make any sense or not. So right now we can see that the majority of chipsets are already showing very decent accuracy results, so you shouldn't have any problems. In case of some other chipsets, yes, there might be some problems with some networks, but at least right now there are no completely no very solved issues, so the accuracy problems usually happen quite rarely. Now let's look at the aggregated floating point performance, and here we can see basically the same picture. That the recently presented Snapdragon 8 Gen 1 and Dimensity 9000 SoCs, their performance doubled compared to previous generation SoCs. And yeah, with these networks, you can run very, very large floating point models, even the ones that was not possible to deploy 1 or 2 years ago. And again, they offer lots of power. And in many cases, their performance is coming close to the recent desktop GPUs. And again, with this, with the recent generation SoCs, you have a really huge freedom of what you can deploy on them, what models, what problems you can tackle when using these chipsets. And here is also a graph showing the accuracy of the corresponding SoCs. And remember that we told you that GPU TFI GPU delegate might have some issues with accuracy, and you can see this on this graph. So for older generation chipsets and even for some recent generation SoCs, you might see some huge performance degradation. So in some cases, the outputs might be random. But again, even here we see that in the majority of cases, we are getting very, very decent accuracy results, and there are no sort of issues with the outputs of the networks. So we have now covered almost everything that concerns TensorFlow, that concerns Android ecosystem, and let's take a look at what we have with iOS. So we had previously lots of requests about benchmarking of Apple hardware, of Apple devices, and we just basically did this, and will now present you the results that we obtained. And before benchmarking Apple chipsets, let's briefly recall what are the most important performance factor of mobile AI accelerators. Well, the first factor, as always, it's raw computational performance. It's basically how fast the model can perform matrix computations. And if raw performance is not good, then all models would also be running quite slowly. The second performance aspect is support for different inference types, because potentially we want to run quantized models, we want to run floating point models, and we want to be able to switch between them, to have different options. And the last, and in general is the most critical performance aspect is support for different ops and layers. Because if your AI accelerator can run only convolutions and ReLUs, then you won't be able to run many different architectures on it. So, and the more layers your accelerator supports, the bigger is the freedom of what you can deploy on mobile on this particular platform. And in case of Android ecosystem, it's a very, very competitive ecosystem where different smartphone vendors are fighting for customers. They are trying to implement completely different use cases, and therefore they are working days and nights on bringing their NPU support, improving their NAPI drivers, improving their delegates, so that it supports as much models, as much layers as possible, and you can deploy lots of different models with them. And Apple ecosystem, it's quite closed. Apple is not competing basically with anyone because it's not selling chipsets to anyone. And therefore it was very interesting if Apple was able to also to come up with a reasonable solution for AI inference. And to check this, we just we ported AI benchmark v5 to iOS devices. We just performed the exact re-implementation of Android AI benchmark, and we used exactly the same models, and we used the same images. So basically the setup was identical. And good question now, what can we use for model acceleration on Apple devices? Well, you can use Apple CoreML, and you can, alternatively, you can use TensorFlow Lite CoreML delegate. So basically two options. The second, if you're developing applications for both Android and iOS, then the second option is would clearly be preferred, because in this case you can use just standard TF-like models and run them with TensorFlow Lite CoreML delegate. So you do not need to do any additional conversion. And TF-Lite delegate can run floating point models on Apple Neural Engine. It supports Apple 12 and US SoCs. And in general, it is quite nice. It has only one major drawback. It cannot accelerate in 8 models. And you can ask us why we wouldn't, why do not we use CoreML for accelerating in 8 models? And it turned out that well, of course, when you are getting a quantized model, you need first to quantize it. And Apple Caramel, it implements only basic quantization without tensor calibration. And in practice, this means that you would be getting just a really soft accuracy degradation. So we had the same issue with TensorFlow till year 2018, when they introduced advanced post-training quantization with input-output tensor calibration and with calibration with some other tensors. And Apple did not do this. So if you are quantizing floating point model with Apple Caramel, then the accuracy loss in the majority of cases would be dramatic, and therefore this approach is just not practical at all. So if you want to run quantized model on Apple devices and you don't, well, I mean, of course you can just do quantization manually, you can do lots of additional work here, but if you just want to use some standard tools, then the only option is to use TF-Lite, is to quantize model with TensorFlow quantization toolkit. You're getting TF-Lite model and you're running it with TensorFlow Lite. So what results did we get? As I mentioned, we performed implementation of all tests. We benchmarked all models from benchmark V5, and only 4 out of 24 models were successfully delegated to Apple A15 neural engine. In case of other models, either the performance of the model was just very low, or the delegate just crashed. So only 4 models were fully delegated, and these models are mobile net v2, Inception v3, Deep Life v3, and DeepIt. So it's basically the same situation that we had in Android ecosystem 2 years ago. So 2 years ago, if we wanted to benchmark Android devices, then usually these were the models supported by the majority of platforms, and if we were using something more complex, then there were different troubles, and there was almost zero acceleration support for them. So if we're looking at the performance of these 4 models, then the results are looking in generally quite good. So Apple's A15 neural engine can provide really decent acceleration results. And if we just look at the aggregated scores, then it falls behind, slightly falls behind the Dimensity 9000 chipset, and it is significantly faster than the Google Transit SoC. So raw performance of this chipset is quite good. But that's the only thing that is good about Apple AI hardware, because as we found with Int8 models, you can get good accuracy only when using TensorFlow Lite, and when using TensorFlow Lite, you cannot accelerate the resulting models on Apple neural engine with TF-Lite Caramel delegate. But okay, that's not the biggest problem. Again, the biggest problem is that Caramel delegate is not supporting lots of models, lots of models and layers and activation functions. So basically, the support here is close to the support in Android ecosystem 2 or 3 years ago. So in brief, if you want to develop some neural networks, some AI models for Apple devices, you can still do this, but you should really use a very constrained set of ops so that the model can be accelerated efficiently. Otherwise, right now it's not compatible to what we have in Android devices. And just to remind you, here Apple A15 was able to accelerate 4 out of 24 models, and if we're looking at the Dimensity 9000 and at the Qualcomm Snapdragon 8 Gen 1, they are able to accelerate almost all networks. So almost the ops coverage is almost 100%, and here it's around 15%. So yeah, if you decide to develop, you should be aware of this problem, that you should use a constrained set of ops for designing your neural network. And we are now moving to we have covered lots of topics related to AI inference and on mobile devices, and now we will move to the last part of the presentation, and we will talk about more general smartphone benchmarking. So as you might have seen, with each new generation, mobile SoCs are becoming more and more powerful. So they are offering new features, their raw performance is just rising, and especially you can see this on the previous slides, when we were comparing AI performance of the latest generation smartphones and previous generation SoCs. But there is also one major problem, that mobile SoCs are now consuming more and more energy. And the higher is the TDP, the worse is the thermal throttling behavior, and the more problems with overheat, and we are getting the more problems with overheating. And besides that, higher TDP also means higher energy consumption. And for smartphone vendors, they are facing a really tough challenge. They need to find the right balance between the performance and power consumption of their chipsets. And basically the same problem, normal users are facing exactly the same problem. Because if they are taking the recent smartphone chipsets, quite often they have problems with thermal throttling and with power consumption. And you wouldn't see these problems in normal benchmark, in conventional benchmarks. Because if you check the scores of the recent smartphone chipsets are just reaching millions, zillions, trillions, and so on. But the scores are no longer telling you anything about the real user experience that you would be getting. And the real user experience is often looking like this. So if you decide to run some heavy workloads on your mobile device, and during the first several minutes, or even in some cases several seconds, you would be getting good performance. But after that, the performance would drop sometimes by a factor of 2, and becoming comparable with the performance of some mid-range or even low-end chipsets. So you have just bought a very expensive phone, but as soon as you are launching some heavy workloads, it is just cutting, it is reducing its performance. So the frequencies are dropping significantly, and you are ending up with the performance of some mid-range or low-end chipset. And at the same time, the phone gets overheated badly. So, and again, these aspects are not covered by any common smartphone benchmarks. And taking this in mind, we understand that right now it's when we are checking how good is the smartphone, how good is mobile SoC, this is not only about the computational performance, but it's also about the thermal throttling behavior and about power efficiency. And in our lab, from time to time, we are doing different experiments. We are building some prototype applications, and some time ago, we were looking at how NPU inference affects CPU and GPU performance and vice versa. And we saw quite a large number of inference results. And then we generalized the result in application and released the burnout benchmark. That is checking power efficiency and power consumption of all major SoC components, including CPU, GPU, and NPU. It checks the performance over time of all components when they are fully loaded. It checks thermal throttling when different SoC components are loaded simultaneously. This is a use case that is not covered in any single benchmark. And in terms of the workloads, on CPU, it's running parallel vision-based computations using OpenCL, and CPU is multi-threaded computations. And on NPU, these are AI models with typical machine learning ops. So it provides also very explicit visualization of what is happening on your phone. So in each graph shows FPS of the corresponding hardware. So here is CPU FPS, GPU FPS, NPU FPS, and power consumption over time. So you can basically see how so is the thermal throttling and how much energy each component is consuming. And there is a standard mode that will check the power efficiency of each SoC component. Will check its throttling behavior. Will check how sustainable is the performance of your device under full load, and will just provide you with these results. But there is also a pro mode where you can launch any workload separately, and you can play with it quite a lot. So you can just, for instance, you can launch CPU inference and GPU inference and just see how each of them affects the performance of the second one. And you can also log the results to a CSV file and then plot it and analyze this FPS values, analyze power consumption, and you can basically do lots of stuff with this benchmark. And so we already checked the performance of many devices using this application, and let's briefly look at the results. So if we are looking at the computational performance, here everything is quite clear. So the latest generation mobile SoCs, they show very good results. So here we see that Snapdragon 8 Gen 1 is doing the best, and it's followed by Dimensity 9000, by 2 years old Kirin 9000 chipset, which is kind of a surprise. And then we have older generation SoCs. If we are looking at the thermal throttling results, the results here are completely different. So as we can expect, the best performance is demonstrated by mid-range SoCs, which clock rates maybe are not that high, but that are considerably more energy efficient and that emit less energy. And in this case, basically almost all chipsets from this section are mid-range chipsets, except for Razer Phone 2 and Asus ROG phone. So these are two rare devices where developers really cared about their cooling system. So they have very advanced design that allows to cool them, and basically these are only two SoCs that are able to demonstrate two flagship SoCs that are able, two flagship devices that are able to demonstrate good performance results under full load. And if we're talking, and now if we're moving to power efficiency, then here we have the following situation. The latest generation high-end chipsets, they show in general better FPS per watt results, simply because they are manufactured at better tech process, and therefore, yeah, their FPS per watt values are better, but they are also consuming less energy overall. So like they would consume maybe 3 or 4 times, well, usually like 2 or 3 times more energy, but they will do the job much faster. And if we combine all these results, we would get the overall burnout benchmark scores, the overall burnout benchmark score. And the results here also look, from our side, they make quite a lot of sense. So here we can see that cooler chipsets are in general getting the best overall performance. And the devices that are extremely hot, the devices for which we know that they have problems with thermal throttling, that are getting super hot during when playing heavy games, they're getting quite mediocre scores. And by the way, here we did not yet include the results of Snapdragon 8 Gen 1 Plus chipset, but since it is manufactured with a better process, its results would probably be significantly better than the ones of the standard Snapdragon 8 Gen 1 chipset. So you can view the results for numerous phones on our website. We have also published aggregated results for different smartphone SoCs. And so on the x-axis, we plotted computational performance. On the y-axis, we plotted power efficiency. And in this case, for instance, you can see that basically MediaTek Dimensity and Snapdragon 8 Gen 1 chipsets, they are showing pretty much the same overall performance, but they just went for slightly different targets. So Qualcomm optimized Snapdragon chipsets for better performance, while MediaTek did optimizations for better power efficiency. And if looking at this graph, you can infer quite a lot of interesting information. And you can also see how the power efficiency improves from one generation to another. So that's all for the last part. I hope that this presentation might be useful for you if you decide to develop efficient models for AI, efficient AI models for mobile devices. Last year we had a number of competitions where the participants were designing models for smartphones and for different mobile platforms, and you can find the results of these competitions on our website. This year we have also a couple of competitions that was started quite recently. So we have video super resolution competition where evaluation of the resulting models is happening on the MediaTek Dimensity 9000 APU. We have image super resolution challenge with evaluation on Synaptics platform. We have Learn Smartphone ISP competition with evaluation on the latest Qualcomm Snapdragon GPU. We have bokeh effect rendering track with evaluation on on Mali GPU, and depth estimation on the Raspberry Pi platform. And those of you who checked the Raspberry Pi, checked the depth estimation challenge, you might have noticed that we have also launched our new evaluation platform that is located at mlcompetitions.com. And it would be gradually replacing our Code Lab competitions, and it has basically more or less the same functionality, but on this platform all competitions will be happening on demand, which means that you will be able to get the results on the validation data set at any time of the year, and we will regularly test your models on the test data set as well. So, and yeah, you can expect that the next mobile AI competition would be happening entirely on this new platform. And again, for those of you who are participating in these competitions, you know that you need to design efficient solutions. And so here is an overview how all the stages that you need to all the stages needed for running neural networks on mobile devices. And if you designed and if you got the resultant TF-like model, as we told you, you can run it on your own Android smartphone. You can benchmark its performance on your Android smartphone. For this, you need just to copy the resultant TF-like model to some folder on your phone, then download a benchmark application. And after running this application, you should go to the Pro mode, then select the custom model button, and then just select this model, select the desired acceleration option, whether you want to run this model on CPU, with GPU delegate, with an NAPI, or with some custom delegates if they are available. And then you will see the runtime of this model on your phone, on its CPU, on its GPU, on its NPU or APU if it has. So in this case, you can just constantly check in the improvements that you are getting by introducing different optimizations on your own mobile device, and you don't need to do any coding. And again, if you have some questions, you can leave them on our AI benchmark forum. You can find more information in the previous AI benchmark papers that we published together with several smartphone vendors. Today, do not miss the presentations from smartphone vendors, especially do not miss the presentation from MediaTek, Qualcomm, Intel, Synaptics, and Huawei. So they will tell you quite a lot of useful information that you can put in practice when developing efficient models for AI for mobile devices. And also there will be a number of interesting talks about about software for mobile devices. And that's it. I have almost made it. I'm just 1 minute late. And I do not know, probably we should skip our Q&A session. So you can leave, I don't know, are there actually any questions on site? So
Wait, 1 second, Andrey.
Okay.
So yeah, apparently there are no questions here, but I think guys can, as you pointed out, they can write you on YouTube because we are live, or send you an email. I think that's good.
Okay, perfect. So yeah, if you have some questions, you can just leave them on the forum. Yeah, or just send me an email or leave it on YouTube. Yeah, there was actually a question whether you will have this presentation. Yes, we'll publish this presentation and you'll have a link in YouTube comments. We'll provide you a link to this presentation in YouTube video description. So then we are starting with, I'm starting sharing the screen, and we are moving to the second talk that would be delivered by Dr. Alan Lu, and he will tell you about mobile AI trend and the power performance metric, and he will talk a lot about MediaTek software and hardware ecosystem. So welcome, Alan Lu.
Thank you, Adrian. Can you hear me?
Yes, we can hear you.
Okay. Yeah, that was a great presentation. Yeah, and actually a good introduction to my speech too. So I guess I'll start to share my screen and get started.
Good morning, good afternoon, good evening, depending on where you are. My name is Alan Liu with joint speaker Jimmy Zhang, are both from MediaTek. I will share MediaTek's experience of deploying AI technology on the smartphone and suggest a power performance metric for sustained AI applications like videos, games, or XR. Jimmy will introduce a MediaTek-sponsored Video Super Resolution Challenge to promote the low-power mobile AI applications and the power performance metric. Let me share MediaTek's experience in mobile AI application deployment on a smartphone. Since this is an introductory slide, I will use layman's terms to convey the AI technology instead of using AI terminology like MobileNet, UNet. Perception means extracting feature from an image. The most common application in a smartphone is face unlock. Construction means segmenting the image and reconstructing it in a different way. The common application in a smartphone is virtual background, face beautify, or photo bokeh. Quality refers to pixel level processing. That is, the AI algorithm processes the input image at the pixel level and also generates the output image at the pixel level. The computing complexity and order of magnitude higher than the object-based AI algorithms. Of course, the quality improvement need to be impressive to justify the computation complexity increase. Motion refers to the temporal processing. It happens in video and games application on smartphone. A common use scenario is to increase the frame rate, enables the silk-like smoothness when watching a video or playing games. It is a big challenge in terms of computation and power constraint for a smartphone to apply AI algorithms to videos and games. Lastly, we are living in a three-dimensional world. The current smartphone only provides a two-dimensional user experience because it lacks depth information. So depth is to refer to 3D applications. The immersion in VR/MR device is the first step toward the real 3D experience. This makes the already big challenge become a bigger challenge for mobile AI applications, or we can call it a bigger opportunity. I will show the effect of mobile AI on improving the image and video quality in next few slides. This slide shows the effect of using AI noise reduction algorithm, or NR in short, to enhance the photo quality for the night shot. The left photo is without the noise reduction. The right photo is with the AI noise reduction. Night photo is getting more popular because we stayed up late more than ever. The problem of taking a night shot is everything is dark. We need to amplify the image, which boosts the noise. We can see from the photo, the left photo, the noise is all over the photo and particularly visible in the sky and on the girl's face because they are supposed to be flat and clean. I hope you can see it at the remote location because the image compression and decompression process may filter out the noise and make it invisible. This is actually how the conventional noise reduction algorithm does. Use a filter to remove the high frequency component and keep the low frequency content of the photo. The side effect is that it degrades the sharpness and loses the detail of the photo. The pixel level AI algorithm, on the other hand, can remove the noise while keeping the sharpness and details. The result is showing on the right photo. It looks good and does not have the side effect of conventional noise reduction algorithms. This slide shows the advanced version of the night photo. It combines two AI features, noise reduction and high dynamic range, or HDR in short. The left photo is from MediaTek's Dimensity chip with AI NR plus HDR. The right photo is from another vendor without AI processing. It's quite easy to tell the difference between the two photos. The left photo not only shows more details, but we can see a clear reflection of the buildings in the water. It demonstrates that the pixel level AI algorithm can reduce the noise and enhance the dynamic range in this very challenging low light condition. The result is better than human vision in the low light. That's the reason why the photo looks very impressive. There's a name for this style of photos called low-light photography, and low-light photography become the key selling feature for flagship smartphones these days. Let's take a look at different applications of using pixel-level AI super resolution on mobile again. The image on the left is the low-resolution snapshot of a game. The image on the right is the upscale snapshot using AI super resolution on the same game. The AI super resolution sharpens the edge and removes the aliasing component, makes the overall image looks like a native high-resolution game. To make the difference more visible, we enlarge part of the figure and highlight the differences in the white and red boxes. There are two ways to use the AI SR for mobile games. We can make the game quality better for some light-low games. For the heavy-low games, we render low-resolution game to reduce the GPU loading, and then use the AI super resolution to restore the quality and save the total system power. To my knowledge, MediaTek and our customer announced the first smartphone equipped with the AI super resolution for mobile game in April this year. This slide shows a similar AI super resolution technologies used on the TikTok video. It converts an HD video of 720p resolution to a 2K video of 1440p resolution. In other words, it doubles the pixel in both vertical and horizontal axes. This demo shows a quite visible difference before and after using the AI super resolution. Hopefully, you can see the difference at the remote location, not being filtered by the network. The stream video service internet company like the super resolution technology because it can save their investment to upgrade their infrastructure to a high resolution server. I didn't tell you which part of the image is before or after the AI super resolution in the previous slide. That was a test of your eyes. I'll use a video clip and play it twice so that you can see the difference before and after using AI super resolution in real video. I'm playing the video the first time now. And the second time now. The left side of the green line is the original video. The right side is the upscale video using AI super resolution. I hope you can see the difference. In MediaTek, we have the opportunity to engage with leading AI companies to observe the mobile AI feature and model trends. The first trend is no surprise. The model is getting more complicated and bigger to accommodate more applications. Starting from the CNN and adding the encoder and decoder structures for image applications. Then add the sequence structure for video, voice, and games. Then add the attention structure for natural language processing and computer vision applications. PRMR is emerging application that use many AI algorithms. Therefore, the 3D structure is also in the pipeline. Adding each structure makes the model complexity increase by multifold. The second trend is higher resolution, driven by the bigger display. The number of pixels is double from Full HD to 2K, from 2K to 4K, and quadruple from 4K to 8K resolution. The two killer apps using AI in the smartphone are video record and video display. Both applications use many AI features. The video recording from Full HD to 4K is happening now. You can find this feature on your smartphone. And the next trend is to move to 8K resolution. For the video display, the new foldable phone is to push the resolution to 4K level. In addition to smartphones, the current generation of VR devices equipped with the 4K equivalent pixel display. The next generation VR device will demand 8K resolution because the eye to display distance is significantly shorter compared with a smartphone. So we need a very high resolution display to satisfy our eyes. The size of the AI models and computation complexity increase proportionally with the resolution. The third trend is the sustained use. It's how long the AI model is running sustainably. AI applications are used to run and end in a burst fashion. For example, when our smartphone does face unlock, it does it in one shot and take less than a second. Nowadays, AI models are running for much longer time. For example, the AI noise reduction in video recording may last for minutes or tens of minutes. The AI super resolution in video conferencing or games may last for hours. Why the sustained use is an important trend? Because the mobile AI application always comes with the power budget. The power budget for a bursty application is different from that of a sustained applications. This sustained use becomes an important consideration in mobile AI scenarios. I'll elaborate on this in the second part of my presentation. We talk about how the applications such as photos, video, games, and VR, MR keep driving the mobile AI evolution for sustained use. The mobile AI model complexity grows exponentially because the bigger model and higher resolution we just described. I use the complexity versus year in this figure. The mobile AI model complexity trend is shown on the top line of this figure with a steep slope. How to meet the mobile AI application trend in a smartphone? There are three main technologies. The first technology is the Moore's law. The mobile AI model is executed in a high-performance silicon chip. Moore's law help to integrate more functions onto the SoC. We can see there's still a wide gap between what the application demands and what Moore's law can offer. And this improvement to bridge the gap comes from two areas: the hardware architecture improvement and the software and algorithm complexity reduction. It is the combination of process improvement, hardware architecture, and software algorithm complexity reduction to enable new mobile AI applications. I'll give a very brief introduction to MediaTek's hardware and software platforms in the next two slides. Allow me to use MediaTek's Dimensity 9000 as an example to explain the hardware building blocks of the current 5G AI SoC. Our goal is to offer the quote-unquote coolest 5G SoC with the highest performance. There are three building blocks. The first building block is for communication connectivity. It integrates 5G modem and Wi-Fi 6E to provide the multi-gigabit downlink and uplink. It provides the communication link for us to watch a video, upload the photos and video to social media, and a low latency link for cloud game, VR, or MR. The second block is the general computing platform, consisting of a multi-core CPU and a GPU. These blocks handle everything from web browsing, running the app, user interface, and playing games. The third block is the AI and multimedia building blocks. It consists of a specialized AI processor or APU in short to perform computation-intensive machine learning or deep learning operations. The 9000 has two types of cores. The P core stands for performance core. It is used to tackle the neural network operations. The flexible core, as the name implies, is flexible and programmable for signal processing, computer vision, VR applications, and so on. The multimedia part supports a high resolution up to 320 megapixel camera sensor. The video encoder and decoder supports 4K HDR video and 8K video. Last but not least, it supports high frame rate and wide display. All the functions are implemented in 15 billion transistors and packed on a single 1 cm by 1 cm silicon chip. It is quite amazing technology achievement thanks to Moore's law and the Huawei architecture. We need to have a good software platform to fully utilize the hardware. MediaTek's software platform is called NeuroPilot. It is shown in the middle gray box. It consists of software SDK, machine learning toolkit to support different AI frameworks. Users can develop mobile AI applications using the NeuroPilot platform on different products. There are two reasons that MediaTek built our own NeuroPilot Edge AI platforms. First of all, Edge AI devices are severely constrained by power. NeuroPilot middleware and ML kits provide platform-aware optimization to squeeze the last drop of performance from the processor. Secondly, most AI devices are very diverse in terms of CPU, GPU, and APU performance. NeuroPilot provides a cross-product uniform and consistent software platform to reduce the risk and shorten the time to the market. If you ask me, what is the most challenging task to enable a mobile AI feature on a smartphone? It must be the power constraint. When we engage with customers to enable some AI features, we will set the performance and power targets. Typically, we will reach the performance targets such as latency, accuracy, and frame rate relatively fast, but it takes a longer time to converge on the power target. The power target is bounded by regulation. Based on the international standard, it says that the wearable and handheld products, the skin temperature limitation is 43 to 48 degrees for safety protection. Smartphone's thermal resistance is limited by the phone ID design. Typically, it's between 4.6 to 6.6. For entertainment purpose, I put different types of phones and their thermal images on the top of the slide. The bar phone on the left is the common smartphone we are using now. It has the lower thermal resistance and relatively better thermal performance. The foldable phone in the middle and the flip phone on the right have higher thermal resistance and therefore worse thermal performance. So if the foldable phone or flip phone becomes popular in the future, it means we need to burn less power to meet the regulation. We can calculate the total sustained system power budget is under 5 watt. The system power including everything from display, camera sensor, 5G modem, CPU, GPU, APU, DRAM, and so on. And what is the power budget for mobile AI applications alone? From our numerous experiences with customers, it is always under 1 watt for sustained use cases. Be aware that I emphasize on sustained use cases. It means that the AI workload will last for at least a couple of minutes to reach the thermal equilibrium. For example, turn on the AI super resolution feature while watching the streaming video for 5 minutes. If the AI super resolution burns more than 1 watt, like 2 watt, it will reach a temperature that you probably don't want to hold it in a couple of minutes. On the other hand, if the AI feature is a short burst workload in a second, for example, taking a photo, the power can go beyond 1 watt, like 3 watt, for a short moment, as long as the workload turns off before the temperature rises to 43 or 48 degrees. The key message is that the power constraint is very important for sustained workload, and it is different from the short burst workload. The target and constraint are also different for the short burst application and the sustained use applications. I used a table to summarize the difference and call the former a peak performer and the later the sustained performer. The peak performer is like running a 100-meter dash. The duration is short in seconds. The target is to pursue the minimum inference time. It comes with the price of high power, but we don't care because the race will end before the body temperature reaches a damaged level. Besides, we can take a long break to cool down the temperature before the next round starts. The peak performer is bounded by the investment of computation resources, like how many megs or TOPS are put into the silicon, or how to drive the SoC to its highest frequency. The peak performer is tailored for short burst workload like face unlock or taking photos. Speed matters, the sooner the better, but it doesn't increase the temperature as long as it ends quickly. On the other hand, that the sustained performer is like running a 3,000-meter race or a marathon. It takes minutes or even hours to finish the race. The sustained performer needs to run at a fixed rate, not too fast to avoid that body temperature goes too high, and not too slow to lose the race. Since the sustained performer is bounded by the fixed power budget, investing too many hardware blocks doesn't necessarily get the good return. What is needed is to implement a better power-efficient hardware, or to optimize the pace of scheduler. For the mobile AI application, the sustained workload is coming at a fixed rate, for example 30 or 60 frames per second for video, 60 or 90 frames per second for game, VR, MR applications. Therefore, it is important to invest the hardware and optimize the software for the sustained workload based on the application characteristic. Given an AI model, the peak performance means the smallest inference time or the highest frame rate because the frame rate is equal to the reciprocal of the inference time. As the mobile AI application evolves from short burst workload to sustained workload, the current peak performance metric is a good measurement of the short burst workload, but not an appropriate metric for sustained workload, because the peak performance does not consider the critical power constraint upfront. We suggest the power performance metric to address this application trend, and this methodology is applicable for both peak performance and sustained performance. Let's start with the peak performance. The frame rate is the x-axis in the figure. We use frame rate as a performance axis because it maps directly to the videos, games, or VR/MR workload characteristic. The y-axis is the power of turning on the AI feature. We use a UNet model to perform pixel-level video processing as an example. When the APU runs at the highest voltage and frequency, it performs 81 frame inference per second. This is a peak performance, and the power, no surprise, is also highest at 2.9 watt. The third number, 28, is the ratio of the frame rate divided by power. The peak performance number is good, or maybe too good, because the video workload is typically coming at 30 frames per second or 60 frames per second. The problem is the customer's power budget in this case is 1 watt. The peak performance power of 2.9 watt is way over the power budget. So how can we judge if this model can be used for video application? We cannot. The 28 frames per second per watt seems too low for any video application requiring at least 30 frames per second. The truth is that we cannot derive sustained performance from the peak performance power ratio because performance versus power is not a linear function. We need to use the power versus performance curve. So how can we get it? Typically, APU has pre-optimized operating mode, such as high performance mode, a balance mode, and a low power mode. These different operating modes are for the advanced user to trade off the system performance versus power. These modes are exactly what we can use to draw a power versus performance curve, or power curve in short, as shown in this figure. This curve is never linear. The power curve bends upward at the high performance region, like a parabola. It's intuitive. If you are driving at 100 miles per hour, it takes more gas to increase the speed by 10 miles compared with when we are driving at 50 miles per hour. The power curve is nothing new. We can find similar power curve in CPU and GPU power versus performance metric. The only difference is the performance index becomes backing scores or Manhattan frame rate per second. With the power curve, we can get a more accurate power performance metric for sustained performance. The sustained performance can be interpolated from the power curve by fixing the power budget. In this case, we use 1 watt as a power budget. The 43.7 frame per second performance at 1 watt is a much better and meaningful metric compared with the peak performance of metric of 81 frame per second that we can never use, or the 28 frame per second per watt, which is too pessimistic for video applications. Alternatively, we can also fix the frame rate performance. In this case, it would be 30 frames per second, since 60 frames per second is over the 1 watt power budget, and interpolate the sustained power at 30 frames per second, which is about 0.6 watt. Again, the power curve is nonlinear. It heavily depends on the hardware architecture and software implementation optimization. Therefore, the peak performance or the peak performance power ratio is not a good measure of sustained performance. We need to get the power curve to get accurate or meaningful metric for sustained performance. This is my last slide with some takeaways. Mobile AI is evolving from short bursts to sustained applications, running bigger models with high-resolution data. The most critical challenge is the power constraint. The performance metric based on the minimum inference time is not an appropriate metric for sustained AI applications. We suggest the power performance metric based on power curve to obtain sustained performance. We are hosting a video super resolution challenge to promote the sustained performance, and would like to invite for your participation and collect your feedback. I'll stop here and thank you very much for your time. Jimmy will give an introduction of the challenge.
Okay. Could you hear my voice?
Yes, we can hear you.
Okay, thank you. Okay. Thank Alan's introduction to power performance metrics. In the following pages, I will introduce our challenge in ECCV 2022 AIM workshop to promote the aforementioned sustained performance. Video super resolution has recently become one of the most important mobile-related problems due to the rise of video communication and the streaming service. While many solutions have been proposed for this task, the majority of them are too computationally expensive to run on mobile with limited hardware resource and the power budget. Although the computing capability of mobile CPU and the GPU are powerful nowadays, the power efficiency is the biggest challenge for sustained video applications. Even if most flagship devices equipped with mobile APU or NPU, there is still a gap to carry out video super resolution in mobile devices. Therefore, we set out a challenge for the ecosystem to develop a power-efficient video super resolution algorithm on MediaTek mobile APU. We use popular dataset in video super resolution literature, RAIDs, to perform 4x video upscaling task. The participants are asked to train a model that considers the best trade-off between fidelity, performance, and the power. In general, there are some hard requirements that must be satisfied to fulfill the real scenario of video super resolution in mobile devices. First of all, quality is the most basic index. The PSNR of bicubic assembly on RAID's dataset is about 26. So we set the lower bound to 27 dB. In real use case, 30 frames per second is the minimal requirement for video streaming. So the submitted model should run faster than 33 milliseconds. As mentioned by Alan in this talk, the power budget of an AI application in mobile device should be no more than 1 watt. Therefore, the power consumption of running the submitted model should be smaller than 1 watt. In the final competition phase, we would make a scoring formula built upon fidelity, performance, and the power. The latest information would be updated. It will be updated in the Coda Lab website. In this page, I will elaborate the real scenario of video super resolution in mobile phone. In real case, the performance is set to 30 or 60 frames per second, depending on the input video streaming. It's no need to pursue performance higher than 30 or 60 frames per second. On the contrary, you could make the model bigger to achieve better quality if you have additional performance budget. Many publicly available solutions could achieve 30 or 60 frames per second requirement. However, power consumption is the most challenging factor in real video super resolution for sustained use case. As just mentioned, sustained power budget is under 1 watt. In real video super resolution scenario, the power budget is considered to be smaller than 1 watt. According to this constraint, our video super resolution competition aims to address this difficult challenge and to push power efficiency to the limit. In our challenge, we use the power measurement methodology. Given a model, we will have 7 operating points based on different voltage and frequency to plot the power curve, as shown in this figure. With the power curve, by fixing the performance at 30 or 60 frames per second, we could get sustained power by interpolation. In this figure, we got 0.62 watts at 30 frames per second by interpolating the third and the fourth operating point. In this power curve, we could achieve 60 frames per second in this curve. However, it consumes near 1.8 watts, which is impractical and far from 1 watt power budget in mobile devices. With the proposed power measurement methodology and the experimental setting in this video super resolution challenge, we expect to see better power curve and push power efficiency to the limit. For example, in our real product experience, the power budget for AI super resolution is smaller than 350 milliwatts under 30 frames per second scenario. The submitted model in this challenge would be deployed via MediaTek NeuroPilot SDK. More specifically, the submitted TF-Lite model would be applied with our TF-Lite neuron delegate, which efficiently accelerates TF-Lite model on MediaTek APU. As shown in the right graph, neuron delegate needs fewer software stacks, which has smaller software overhead and thus higher power efficiency. On the other hand, our neuron delegate has better model, operator, and the data type coverage than standard NN-API delegate. For example, in addition to commonly used 8-bit data format, neuron delegate also supports 16-bit fixed point activation and weight data format, which could get better quality. We also support 4-bit fixed point weight data format, which consumes less power and bandwidth. For more detail on neuron delegate, you could refer to our GitHub repository as listed below. We also have a Chinese version introduction on YouTube. Okay. This page summarizes the information of our AIM 2022 Video Super Resolution Challenge. Thanks to the workshop organizer Andrey and Radu for bringing the opportunity to promote real mobile AI application in the ecosystem. We also thank our challenge co-organizer, Professor Wenhuang Chen and Professor Honghan Shuai from National Yangming Jiao Tong University. For more details, please scan the QR code to go to our challenge website. Thank you.
Thanks a lot for the presentation, and thank you, Alan, for presenting lots of useful and interesting information about MediaTek hardware. And I think that this, especially the challenges with power consumption, the challenges, the performance that you mentioned are especially interesting and especially useful for those who are planning to develop efficient solutions for mobile devices. So I guess we have questions. 1 second.
We are good here, Andrey. So if you want to continue, go ahead.
Yeah, 1 second. I will just go through the questions in Zoom. So there is one question. For the power consumption, is it possible to measure the estimated power cost of each operation, such as how much power cost for completing a single convolution to the operation with fixed write, fixed kernel size, and fixed filter numbers? It should seem like profiling runtime and memory cost for each operation, as well as profiling power consumption. So we have this question.
Yeah, let me answer the question. Yeah. Actually, yeah, of course, internally we have a simulator that can characterize the power up to the OP level, so it's doable, yeah. But we are not sure if providing so many detailed information to the developer or customer will be very helpful or not. So usually we provide more like a lump sum. So the combine of several OPs into a layer information and provide the power information at the a little bit cost grain level. However, if the researcher are interested in the power consumption of each operation, then we can talk with them and then see if we can offer those a number to them. Yeah, but it's doable. Yes, yeah, we have a profiler can do that.
Thank you for the answer. I guess this answers the question. So there is another question. It was on YouTube live chat and in Zoom chat. How MediaTek's AI, for example, AI denoising and HDR, supports tuning of image quality to meet different customers' tastes?
You mean how to support customers tuning?
So as far as I understand, the question is about whether you can tune your AI engine for different, for receiving different image quality results, and Son in the chat said that yes, you understood it correctly.
Yeah, so the question, the meet different customers' taste. Okay, well, the level 1, of course, usually I start with the PSNR, right? But as we all know, that PSNR is not a very good measure of the picture quality. It's sort of the baseline. So we can just first just tune to a baseline. And the rest of the picture quality, to be frank, it's an art instead of just a number. Because as the question asks, different customer has different taste. So actually we need to work with them. We usually will provide the tools. There's lots of knobs. So the customer can tune those knobs. Either they want to be more like realistic, or they want to be more like a surreal, so it looks like fancier. Basically we provide tools so the customer can do their own choice on how to nudge those knobs. Yeah. But the first time I always use the PSNR to get the base quality. Yeah. It's very hard to answer this question. Yeah, by the way. Yeah.
Yes. Okay, there is another very good question on YouTube. In terms of architecture design, what should be criteria for power optimized behavior? Is it only low power complexity?
I'm not sure if I 100% catch the question, but
as far as I understand, the question is to get an architecture, to get a model that consumes as low power as possible. What should you generally?
Get it.
What are the right directions for doing this?
There are two important directions. Yeah, if we analyze the power consumption, we'll find out there are two big pieces of power consumption come from. The first one is the memory bandwidth. So if they access lots of DRAM memory, then I need to burn lots of power for the data access and movement. So one catch is trying to minimize the DRAM access, and there are quite a few technology, including we actually published a paper in ISCC and doing something called deep layer fusion to try to minimize the access of the DRAM. Yeah. And second thing is, of course, cut the overhead when you are doing the hardware design. And usually it's like related to combine smaller hardware block fuse into a bigger hardware block. So that way you can reduce some of the overhead and reduce the power. Yeah. So that's the two biggest directions. Yeah.
Yeah, I guess to answer this question, we can organize a separate workshop actually to answer this question completely. Yeah, but that's actually a very interesting topic. And another question, is the sustained power concept extendable to different applications across different devices such as HMD and AIoT devices? Could you provide more examples or use cases?
Okay. Yeah, this is a very good question. Yeah, I mentioned that pretty much all the video applications in smartphone are sustained use cases, like video recording, display, or video conferencing. I won't repeat it. And another sustained use occur in the mobile game. We find out that more and more mobile game example require sustained performance. And this is actually not limited to smartphone. We know there are game console and some of the smartphones used for mobile game console too. Yeah. So in this case, like using AI super resolution to upscale the resolution as I show in the one of my slide, or using the AI frame rate conversion to upconvert, like for example, 60 frames per second game to 90 frames per second game. So that sort of application, yeah. And also VR, MR, as the question pointed out, also demand lots of sustained AI applications. Like typically for the VR, MR, each session takes like a half an hour or even 1 to 2 hours. To play the VR, MR device. The power budget is quite stringent because it's a wearable device. So there are quite a few AI or CV algorithms running concurrently. Yeah. So for example, like if you are doing the VR, MR, there's something called SLAM or head position tracking or eye tracking, hand or gesture tracking, and 3D object detection. So those are all good examples that sustain use cases.
Okay, thanks a lot for the detailed answer. Are there any questions on site at CVPR? Okay, Marcos. So no questions on site. Okay, good.
Yeah, we're okay here.
Perfect. So then, thanks a lot for providing the answers to all the questions.
Thank you.
Yeah, and now we'll move to the next presentation that would be delivered by Felix Baum. He is from Qualcomm, and he will tell you a lot about optimizations, about accuracy and performance, optimizations for Qualcomm on Qualcomm-based platforms. Welcome, Felix.
Hello, can you hear me?
Yes.
Awesome. So let me share my screen. Let's see, I think this is the one I want to share. Awesome. And start my presentation. All right, let me see if I can get the can you guys see it, or the Zoom is on your way?
Yes, we can see it.
All right, awesome. So thank you very much for giving me opportunity to talk to the audience. I think that my presentation will be a little bit different. I think that I would love to answer all kinds of questions about the hardware and how things work, but I think that my presentation will be different because I will spend a lot of time trying to show you how you can get better at running your models and what kind of tools we provide you for doing so without having to study in excruciating details all of the details about our hardware and specifics about the way we implement certain operators or not. So with that, again, my name is Felix Baum. I'm a director of product management at Qualcomm. And what I'm responsible for is this AI software that we provide to customers. One question, and I guess in the previous session I've heard is, well, are these software improvements and software tools and everything else, are they available across the platforms? Not sure about previous speaker. For Qualcomm, it does. Things that we develop and technology and software that we build for is very generic, meaning that it works on all of the Snapdragon devices, whatever it's a little tiny itty bitty earbuds for noise cancellation versus a mobile phone versus IoT cameras, drones, laptops, and even automotive systems. In each one of these devices, you can think of multiple use cases. You can do audio on, again, in earbuds, you can do audio on a mobile phones, you can do audio in smart speakers, all the way to the automotive environment where you can talk to your automobile. Once we enable the models, once we have a software to support these AI-based algorithms, you can migrate it from one to another, assuming that the hardware specific for that vertical, so to speak, in a business supports certain things. So starting from the bottom, we have hardware that was built to support various use cases, and not just use cases as if you can come and say, well, what about super resolution? What about audio? What about the gaming scenario? But what we see a lot of times is these use cases are concurrent, and these use cases have multiple concurrent models within one processing block. So the hardware that we built because of that is in place to support this multiple concurrent use cases. Some of them are kind of AI based, some of them combine AI with a CV and a few other activities. So we can't say just run AI and you're done. So no, we have to maybe run pre-processing on the frame, then do AI, then do post-processing, all of that while the second frame is already arriving and we have to start doing the CV pre-processing on the second one. So because all of these use cases are so different, and because majority of the devices that Qualcomm enables and supports are kind of a battery driven operated, we strive for lowest possible power that we can enable these use cases at and algorithms at the same time, meeting customers' requests for precision, for the accuracy, and for latencies. Because of that, what we've done is we try to enable at the lowest level all data types that folks on the call probably familiar with. We enable, well, traditionally, obviously, FP32 is what we see customers come to us with. Obviously, the FP16 is a little bit more efficient. Going down with the quantization, kind of we moved into int data types. We see a lot of studies published that in16 accuracy is as good as FP16. Going even further, we support and enable int8 data types and algorithms. And for this year, what we're also adding is we have a hardware that will also natively support the int4 algorithms. If you have any questions on that, please don't hesitate, come to me, reach out to me, and I'll answer some of the questions. But again, there are certain use cases where you can say, you know what, I'm dealing with a camera, and I have high definition range, and I cannot deal with less than 12 bits of precision. Okay, understood. Maybe in16 is the way to go. But if you are doing something else, like for example, determining if it's a dog or a cat or somebody else in the picture, maybe for that type of algorithm, int4 is sufficient and good enough. In addition to that, what we've seen customers come to us with is they tell us that after they've done extensive analysis of their algorithms, after they've done extensive analysis of their model, they realize that maybe first few layers have to be FP16 or int16. But in the middle of their models, they can go and drop down to int4, int8 sometimes. So because of that, since last year, we started supporting this mixed precision algorithms. And this year, we're extending it to support all of the data types listed below. So if you come and use our software, you can come to us with a model that contains a mix of these data types. You can have some of the layers in FP32, some of the layers in int16. Well, hopefully not FP32, hopefully FP16. But again, FP16, int8, int16, int4, mix it up, make sure that the model works, and then you can use that. Now, on top of that, we provide customers with a low-level library that is, well, sometimes we call it Qualcomm AI Engine Direct, sometimes it's called a QNN, Qualcomm Neural Network Library, but we provide a unified library that accesses the hardware, schedules the layers and operators. It's a very sophisticated, it supports all kinds of operators, and it is built to optimize, to take full advantage of the underlying hardware, regardless of which version of the Snapdragon you're using, in which tier, in which particular vertical. So sometimes it will break operators in much different ways than others. It has full understanding of how much VTCM it has, for example, in a particular device. So it will layer and schedule the operators and memory to minimize all kinds of stalls and models that will have to get stuck and then go to the DDR, which is very expensive, to fetch additional information, to fetch additional data before it can continue. And I think that was one of the questions in the previous discussion. All of that scheduling, tiling, and optimization is kind of something that this QNN library supports natively. On top of that, when it comes to runtime, we support a plethora of the runtimes. If you look at the last few years, obviously Qualcomm has Qualcomm Neural Network Processing SDK, or as traditionally our customers used to call it, Snappy, Snapdragon Neural Processing Engine. We supported for, I don't know, 7-8 years a TensorFlow Lite, and on a CPU, obviously. But then once the NN API came to life, we enabled NN API to run on our devices. And that was up till about last year, where we kind of realized that the cadence of NN API and some of the features that NN API has in it prevents the bleeding edge TensorFlow Lite enablement. Operators are not all there, certain features are not there, hard to deal with the concurrency and a few other things. So what we have done is we built last year TensorFlow Lite QNN delegator, and that's why this Qualcomm AI Engine Direct kind of stands for that. We have a TensorFlow Lite delegate to the QNN. We are working very closely with Microsoft on an Onyx delegator as well, or as they call it, Onyx runtime executor. But yes, That's something that we developed. We already engaged with a couple of our partners, and actually the AI benchmark is using the QNN delegate in it when it runs on a Qualcomm devices. But again, if you truly want to take full advantage of the features, all the levers and switches and flags that we enabled in our hardware, obviously coming and trying to use Snappy and QNN from Qualcomm will allow you to use all these flags, whereas TensorFlow Lite enablement that we have, although supports many more operators that an API does, but it's still kind of limited from the standpoint of understanding of underlying features in the silicon. So what we feel is the folks that we be using TF Lite delegate mostly are either researchers or app builders and community developers that want to build an app, make sure that it runs on TF Lite, and then run it on as many Android devices, for example, as possible. Now, on top of that, we have obviously customers that come to us with all kinds of models, whatever it's ResNets, SSDs, mobile nets, BERTs, and deep labs or super resolution models. It doesn't really matter. The advantage of Qualcomm, so to speak, unifying behind one software stack that sits on top of Qualcomm AI Engine Direct is because with our implementation, if we enable a particular algorithm, a particular model for mobile phones or for the camera apps, it immediately becomes available on every other device, whatever it's an automotive system you're building or smart camera you're building or anything else. And some of the tooling we provide around it, and again, I listed on this slide just a few, and I'll go in much more details on a later slides, are there to help customers with deployment, help customers to be efficient and get better performance without, like I said, having to learn all the intricacies of a specific SoC from Qualcomm. So with that, let me jump right in. What we see in the market today is a lot of customers and a lot of partners would start with kind of building the models, figuring out what they want to do, having an idea, whatever you are expert, and build an algorithm yourself or not, and maybe went to the model zoo to get some kind of model from there to meet your requirements. Doesn't really matter. But we feel that kind of the first phase is where the scientists and ML engineer come up with an idea. They create a model, they train the model, they play with it to make sure that it does, again, basically does what they want to accomplish, right? It finds dogs in the picture, it uniquely identifies my voice, or cancels the noise if you want to do noise suppressions or noise cancellation or other things. That's kind of what you do initially. From there on, we see customers kind of go to the next phase where they say, okay, well, now that I have this model, can I actually get this model to actually run on a real device, whatever the type of device it is, and whatever SoC it is based on, right? This is where we provide, as I said on the previous slide, a runtime support for running these models, but we also provide a set of tools and SDKs where you can convert your model from whatever, TensorFlow or Onyx or some other format, get it into something that you can actually execute on a device. Now, we're well aware that AI moves business, has a lot of new trends, and it moves very, very quickly. While in the past, we tried to keep up and try to, every time a new paper would be published, or like at an event like this that I'm speaking at, or a new algorithm is developed, we had customers that come to us and tell us that, well, we want to use that model, we want you to support those operators. After a while, we just gave up. We can't keep up with the market. And it would be silly to do because a lot of these new algorithms that are famous today will not be interesting in another couple of weeks. So what we have done is we provided a set of tools, compilers, LLVM, TVM, to allow customers to be able to grab these layers that we're missing, support of the missing, these operators, and be able to go grab a Python, PyTorch or Python implementation of them and be able to go and compile them and just run them. Or C++ implementation, compile them, and then dynamically our tools, our runtimes allow you to hook them up into the running system, and now your model can execute, and there are no missing layers. Now, once you have a device, once you have a model that kind of compiles and can run on a real device, this is where you take your model and say, okay, well, I started with my floating point FP32 or 16 model. I get it to quantize, I get it to compile on device. I can kind of run it, but let me go and check if my accuracy is good enough. I mean, you went from floating point to some kind of, I don't know, int4, int8 version of it. You go through whatever your favorite tool is to check the accuracy. Some people use worst case scenario, actually, if it's an image processing algorithm, you print an image and you look to see if there are any artifacts. Hopefully it's a little bit more scientific than that. But there are a number of different tools that you can use to kind of check the accuracy and see if it's good enough for your use case, for your application. If it's not, this is where Qualcomm today, in the last few years, provides a tool called AI Model Efficiency Toolkit. It has a few techniques in it that our customers find helpful to be able to grab quantized model and be able to figure out which layers introduce an accuracy drop and be able to tweak them, be able to replace them, be able to improve on the model to get a better accuracy for the model once it's quantized. Now, the AI Model Efficiency Toolkit also sophisticated enough that it will actually help you with your mixed precision models. What we would actually do, and again, I'm oversimplifying it, obviously, but what you can do is you can kind of grab your floating point model, run it through the AMAT workflow, and end up with, I don't know, let's just say int8 version of it. You run with an int version, it tells you for the int8 version, here's your accuracy, here's precision, here's the end result. And if you don't really like it, you can go and the tool automatically is gonna walk your model backwards and say, okay, well, if this layer I'll keep at int8, but this layer I'll move up to int16 or FP16, will the overall result and accuracy change? And it automatically kind of walks it backwards and forward until it finds the best combination of the layers. And then it provides you with this mixed precision results that says, okay, for your FP16 precision is here, your int8 precision is here, this mixed precision model with layers all over the place is here, and hopefully that accuracy will be sufficient for you. And then again, if using AMAT, all of the layers and all of the precisions and data types, we already support in a runtime, so you can just take that model, mixed precision model that was created, and just get it to compile and run on the device. Next step that we see is this is where now that you got your model and you get your app and it's running on device, the one thing that we see is a lot of our customers come back to us and say, well, gee, now that I get it to run, well, it's not fast enough. And how do I go and optimize the model? How do I go and improve performance? And this is even before you start looking at how much power your model takes and your applications and others. So we have a few tools already that kind of a profiling and some trace analyzers and a few others that can go and look at the models and try to suggest you which layers you can go and tweak to get running better. And then obviously, lastly, if the model is compilable, if the model is accurate enough, if the model is fast enough, you're pretty much done. You take the model, you build it into the algorithm and to the use case and to the app, and then you give it to your deployment engineers to go, DevOps people to go and deploy and launch on the devices. Whatever, again, whether it's a mobile device or IoT device, we see customers pretty much go through very, very similar process. What we also learn over time is that while this is the process that customers go through, there are a number of different ways where we can hopefully come in and do a little bit more for our customers. Again, it's for all of the customers out there. using our hardware, and we want to make sure that they're efficient, just like OEMs and other phone manufacturers that we have a lot of relationship with already, and they have large teams, so they know what they're doing. So first and foremost, let me start walking through this slide. First and foremost, there are neural architecture search tools out there that would help some of the developers to tune their models. We partner up with Google. We have a tool that has hardware in a loop that allows you to go and say, you know what, I'm looking for this type of model, and I care about, and you set up your search parameters, whatever it's a power or performance or latencies or accuracy, whatever your criteria, search criteria is. And this tool will automatically go and find you the algorithm or the model type that would be perfect for the hardware you're targeting. Obviously, again, trying to optimize on the front end, being able to come in to and get your algorithms designed in a way that they would be efficient at running on a real hardware. Obviously, again, a lot of these tools come in from the workstation development environments, train in a cloud or train on some servers with lots of GPUs and capabilities. And while they're doing all of that, they're using traditionally floating point 32, best case scenario floating point 16 to minimize to speed things up. Still, a lot of the models that our customers arrived to us with are floating point models. Once you train them, once you do all of this work, when you come to us and you try to, I don't want to say naively quantize it, to get better performance, to get better accuracy, to get better results at running on a real embedded hardware that battery operated, so power is a big concern. It is sometimes almost impossible for certain types to go and fix and address all of the errors that arrived due to quantization. So we have quantization-aware training tools that would kind of try to prevent that at the source. If you use quantization-aware training, then the models you arrive to us with, they will already be prepared to be able to be quantized. And some of the issues that we have to deal with with int4, int8 types of models and errors in quantization process will not be there from the get-go. So again, I think this is really important, and some of the tools we're bringing in this year to customers. Next thing that we do is we have, as funny as it sounds, Qualcomm has a document. It's an architecture guidance doc that we published for the last, I want to say 4-6 years, that pretty much says, you know what, because you're building it for our hardware, and our hardware was built for in certain ways, please don't do those kind of things. Like, for example, don't, let me pick something. Let's just say that we try to process everything in 32 channels. So do not use 33 channels, because if you're trying to use 33, then we'll have to do 32 plus 32, 64, a lot of wasted resources. Things like that. While we had that paper online and we offer it to all the customers for the last, I don't know, 4 or 5 years, I think that not a lot of folks go and read it and design their models in that fashion. So what we are doing this year, we're actually providing a tool to lint the model, so to speak, where we can take the model, we can look at the model, and we can make suggestions saying, well, here's some of the problematic areas, here's some of the layers that are not as efficient as others, and make suggestions to customers. Now, as a customer, you can make a choice of following these suggestions or not. At the end of the day, if you will follow them, your models will run faster. Quantization analyzer, again, this is where we would go and try to link your models and try to figure out, okay, well, are there any kind of naive quantization mistakes that we did or you have in your model due to weights or biases or activation things that we can catch? to prevent you from kind of running on device and getting like a weird answer and then having to go debug it. Again, trying to do that all at the beginning of the process, trying to help you to avoid these wasting time debugging your applications and wasting your time and resources. Quantization tuner. Again, there's certain things that our customers have where some of them are using all kinds of different techniques to determine if their model provides the right result. Some use square root, some use, there are a number of different ones. As long as it's as long as it's not subjective, and you can define it on what is the mathematical result you're trying to accomplish when you're determining if the model is accurate or not. We have a tool that will actually go look through your model, and then once you target a particular piece of Qualcomm hardware, again, we don't want you to learn about, if you want to, sure, go ahead and study our manuals and figure out how it works. But for researchers, for community developers out there, we don't want them to spend time trying to figure out what are all of the different flags that we have in our software tools and stacks and compilers and quantizers and converters and everything else. We're trying to simplify it. The tool will automatically go and run your model using all the possible tools, all the possible flags, and then provide you with the graphical representations of the accuracy based on what you selected, and then allow you to say, you know what, for what you're trying to do, for the accuracy or precision you're going after, here's the best combination of the flags for this particular piece of silicon. Maybe another SoC has other flags and other things that are not applicable to you. But here's the offer, here's what we're suggesting, and a recommendation to you would be when you're trying to go through the workflow. Again, trying to make it easy and trying to make developers efficient. Performance analyzer. I think that one of the questions that was asked in a previous session is, well, how do you show that your model is optimized? Very simple. We have our hardware for AI acceleration is multi-threaded and allows for multiple processes and multiple operators to be executed concurrently and simultaneously. All of them are scheduled based on an algorithm that we put in place. We use tiling information and memory available information and different allocation techniques to schedule these operators that your model has in a certain sequence to parallelize the heck out of it. Now, unfortunately, every once in a while, a customer comes to us with a model that will have a particular layer that's just too heavy and big, and we'll just get stuck trying to execute this particular layer and unable to run the rest of the, so to speak, threads at the same time. It was very difficult for us to demonstrate and explain to customers how that works. So in the past, just like a previous speaker, we had a very simplified performance analyzer where we just profile information on a per layer kind of basis to give customers hints of how optimal it is. Unfortunately, you guys are experts, and unfortunately, you were asking, it's like, okay, but we want to real information. We want to see concurrencies, we want to see dependencies, we want to see stalls, we want to see when operator is too big, when a model is unoptimized, so you have to constantly get out of the accelerator, go to the DDR, waste a lot of power to bring in an additional data and details. So what we are doing this year is we're updating our profiler to actually go and expose all these details, be able to show our customers where time is being spent, which layers are difficult or lengthy for us to execute due to certain parallelization. And with that, our customers would be able to go look and say, well, gee, if I optimize this particular layer, it will not improve on overall model performance, because that layer, the time that it takes for me to execute this particular op is just free because something else is running on a system. So optimizing for it will not benefit me. versus this other layer, which you can change, optimize, and do other things, and it will shrink your overall model execution to get you better results. Again, we are working on this tool. We're launching it later on this year. We have a few early adopters that we exposed the tool to, and we are right now collecting data and information from them, how useful it is, what is missing, do we need to improve it, or add a few things here and there to it. Lastly, simulators. We always have large OEMs and large clients that build devices. They have reference boards, they have development stations, they have all kinds of simulation platforms, hardware simulation platforms that they can give to the engineers to try to take their models and check to see how this model will actually run on a real hardware. Well, for community developers, for researchers, not all of them have access to latest and greatest Snapdragon devices, even the pre-announced ones for that matter. So what we are doing this year is we are providing our customers access to this QEMU-based emulation environment that is for accuracy validation and other things that is actually bit accurate to the real hardware. You take your model, you execute it on that simulator, and you will see exactly the accuracy that you get, not in your training development framework, but on a real device once you're running it due to maybe some hardware or software specificity that is unique to this particular piece of hardware. Again, these are just some of the tools that we're adding. As I started very quickly on the first slide, there are Qualcomm specific software workflows that we provide customers with. Then there are kind of a community-based workflow with a TF Lite delegator being one of them. These tools will help everybody, we feel, and make all our customers efficient. And whatever they are, large company with a lot of developers and experts, or a small customer with a smaller team of developers, we feel that for them, having access to these tools would be even more important for that matter. So with that, I will stop talking. I think we have still a few minutes. Andrey, back to you. I don't know if there are questions or...
Yes, thanks for the presentation. Well, actually, you said that you would be talking about different stuff, but you just talked about optimizations for Qualcomm platforms with your own software tools. So, okay, yes, there are a few questions. The first question was about was from Son. When compare Snapdragon 865 with 8 Gen 1 Plus, we see big changes in the benchmark. From your point of view, what do you think the biggest update helped to achieve this result?
Ooh.
Yeah, so like, yeah.
That's a very good question. It's a tricky one as well. I think it highlights the fact that at the end of the day, a lot of the improvements and performance improvements specifically could be attributed to two different things. I think that, I'm trying to stop sharing. Here we go, stop sharing. I think that at the end of the day, some of the performance improvements absolutely due to the hardware improvements. No questions about it. From year to year, we learn about new ways we can speed things up. We learn about new ways that we can maybe take an operator that was experimental in the past and harden it in the hardware, thus making it run faster. And in addition to that, a lot of the software improvements, whatever it's a performance or power, are purely due to the software. The way we fuse different layers, the way we find patterns and try to, instead of doing, I don't know, 2-3 operators, execute everything in one cycle. I think a lot of that has to do with us being able to improve our software and use these optimizations and these tools that I highlighted. I mean, these tools that I talked about, they were available to internal teams for the last few years. It just this year, we kind of decided that instead of us analyzing things for our customers, we want to give these tools to our clients so they can be self-sufficient. And because of that, we see, again, that's what the software tools with the software and the hardware improvements, both taken together, bring these improvements to the market.
Mm-hmm. Okay, we have another question on YouTube, and this question was also asked on the forum. When QNN delegate would be publicly available?
Absolutely. We built it last year, and as a matter of fact, I know you were smiling a little bit because you were one of our initial early release customers, where when we built it, we want to make sure that we're doing it correctly. We built it, we launched it with a few customers to make sure that it works correctly. And early in this year, we extended access to our TF Lite QNN delegate to more clients. I think at the end of the day, by this summer, we're planning to close our early access program and be able to launch it publicly for everybody. So I'm thinking that by the Q3 of this year, we will give it out to everybody. Now, one of the things that just between the few of us on the call that slowed it down is, as opposed to an API, so to speak, from Google, where you have a very well-defined set of tests for validation. Here's the NN API CTS VTS validation. If you pass it, you get a stamp of approval that you have whatever, NN API 1.4 or whatever you passed, and you certified, so to speak, right? There is, from what I know, even till now, there's not something similar for the TF Lite delegates. So we built one, we added a few features over the last few quarters. We think that it's good enough and it will support most of the use cases out there. But we were kind of waiting, trying to work with Google to see if they will come up with this validation test suite so we can have a kind of stamp of approval on our delegate. That still haven't happened, so we're probably going to by Q3 kind of give up on waiting and provide it to everybody. In the meantime, if you are trying to use it or interested in it, please feel free to reach out directly to me and I can see if we can add you to our EAR program.
Yeah, I guess this is a complete answer to this question. By the way, what would happen to Hexagon delegate?
The Hexagon delegate was something that we worked with Google a very, very long time ago on a hardware that was hardware architecture that we walked away probably, I want to say 3, if not 4 years ago. Now, in the meantime, there are a lot of kind of lower end devices that are using or relying on this Hexagon NN delegate from Google. And which is why we had a few customers that asked us to kind of leave it alone and not to take it away. We feel that once in Q3 of this year, we have a TF Lite QNN based delegate, the Hexagon NN delegate would probably become obsolete. Now, if you're using it and you want it, please feel free to use it and stick to it. We feel the new delegate will be much faster and much more portable, so you can go and transition and use those older devices and as well as the much newer hardware from us.
Okay, we have a couple of more questions. So the first question, will Qualcomm provide more support about GPU scheduling solutions with different level of priorities? Thank you so much.
We're thinking about it. And the reason why we're thinking about it is if you're truly embedded developer, then what we see a lot of times is our customers come to us and they say, hey, I got this model, let me run it on a CPU. Woohoo, it runs. Okay, I want to run a little faster, maybe at a little bigger power, but still, I just cannot deal with a CPU level of performance. And for them, we enabled running their models on a GPU. I think at the end of the day, when folks look at the GPU performance versus the dedicated AI hardware performance, particularly the power consumption as well, it is the difference is so big that it's just a matter of milliseconds, so to speak, until these customers say, oh, hold on a second, we can't use GPU because it's too hot or it's too slow for us, and transition to our AI acceleration, AI accelerators. So we've done some work on GPU, but usually because folks fall back to GPU because our AI accelerators already overwhelmed and running way too many concurrent models. So because of that, we are doing some improvements on a GPU, but to us, GPU is kind of a fallback scenario that, yeah, still better than a CPU, but definitely not as good as some of the other AI accelerators that we have in our system, SoCs.
Okay, hope this answers the question. So we have another question. For pixel to pixel, well, for basically image processing models, are there any tools that guide model developers to reduce memory usage on Qualcomm hardware? So I think that you covered basically this topic.
Yeah, I think with some of the quantization, some of the tools that we have for quantization and a few other things would absolutely help with that.
But I guess this question more about design changes. So like some tools that will tell you that, okay, this operator consumes too much RAM and it should be generally replaced with some alternative. So it's more like.
So the first tool that we're gonna do, that we're gonna ship soon in a Q3 of this year that would help with that would be definitely architecture analyzer. That will go look through your models and make some suggestions saying these are wrong layers for you to use, or this is too slow, or you have too much data and it's too consuming. The other tool that we have is this profiling tool that will actually show you how your model is executing on a device, profile you per layer, including concurrencies, and show you that, well, gee, changing this operator or replacing it with this will help you to better parallelize your execution and get much better results. So some of these tools are definitely will help you with what you just described. And I think I saw a question from somebody who typed in a message saying that they cannot find it online. Absolutely. These are the tools we're launching publicly in the Q3 of this year. They're only folks that will be able to find them right now on a CreatePoint, and CreatePoint is for uninformed folks, is our website, Qualcomm CreatePoint, whatever, where you can go download our software. But yes, indeed, the only customers that can get access to that would be kind of early access customers that we reached out to and asked to try out these tools to see if indeed they're useful, if we miss things. And yes, by Q3 of this year, I expect that everybody on the call will be able to go to CreatePoint and find them there.
By the way, one more question. You mentioned that you have a document that you show into developers during the past years with some guidelines. Is there a link to this document?
I do not have a link in front of me, but
is it publicly available?
Yes, it's on CreatePoint for download by anybody. Yes, absolutely. If you cannot find it on a CreatePoint, it's called like a hexagon or AI best practices something. If you cannot find it, send me a link, send me an email, and I'll be more than happy to get back to you and send you a link to that doc.
Yeah, because okay, best practices for developing, I know, governable. No, it's not. Okay, because yeah, I guess that it might be interesting for many guys.
and hence the point that I just brought up. We had that document, we had it for many years. Every once in a while, customers come to us and tell us, hey, this doesn't work. And we're like, hey, did you read this document where we specifically outline the things that you're doing? We given up on that. So Andrey, if you don't have a document, don't use it, don't look for it. Just wait another couple months. You'll have a tool that will automate it for you.
Well, I mean, a tool is good, but I think that, yeah, for many guys who are developing models on Qualcomm chipsets, it would be nice to read this document to get a full
I
overview
would think
and
so.
recommendations.
I would think so. Yes.
Yeah. So and therefore, it would be nice to. Well, maybe you just did not yet advertise this document too much, so that therefore the guys were not aware of the fact that there is actually a tutorial telling them how to do this.
Yep, could be.
So I didn't find it by a brief Googling, so can you please send me the link and I will post it in the description of on YouTube under your recordings.
Sounds good.
Okay,
Again, I don't want to do it online because I don't want to mess up the Zoom and other things. Yes. I'll look up the link and I'll send it to you.
Yes, I mean, we'll have recordings, so we'll just add this link under this recording so that the guys can finally find this secret document and use it for creating efficient models.
No, don't want to do it live.
Good. Later on. Okay, thanks a lot for answering questions. We actually had lots of questions for you this time.
No problem. I don't know how much more time we have, but if folks on the call have any other questions and we're out of time, again, my name is Felix Baum. Send me a note. You can find me at Qualcomm's. I think I'm fbaum@qualcomm.com. Just send me an email and I'll be more than happy to try to answer it.
Well, one more question I saw on YouTube. Okay, between Snappy and TF Lite, what do you think would be better supported on Qualcomm platforms?
Between Snappy and TF Lite?
Yeah, so we have this question on YouTube. So the guys are asking, so maybe they are referring to Snappy and TF Lite hexagon delegate or TF Lite QNN delegate. So which
I
one
think
is...
TF Lite in general. Let me just put it that way. TF Lite in general. Regardless of which delegation you use it, through hexagon delegate or QNN delegate, which is much newer. I think at the end of the day, we support and enable both of them. If you're truly trying to use an Android-based platform, whatever it's a few years old, where you use TF Lite and an API delegate to our accelerators, or a newer platform where you use TF Lite and a direct delegation, we always try to enable it for community and third-party developers. We will enable it and we will support it. Obviously, there are a lot of things in our hardware that we enable, and like in the past with an API delegate, we just couldn't expose it to the customers. So which is why I still think that if you truly want to extract the best performance, Snappy, QNN, probably your best choice. Guaranteed your best choice. It has more switches, it has more features, it has more capabilities to partition your system, understand system level performance, and do other things. TF Lite is, while it's good, but it doesn't understand the rest of the SoC. An example would be if you're trying to run, I don't know, a benchmark or any other type of heavy-duty application. You start on a CPU, whatever it's a TF Lite delegate or a Snappy. You have to set up certain power and system parameters. How much bandwidth you want on a CPU, how much what frequency for the DDR should be, what performance levels you want to set up hexagon at or other accelerators. And you, for example, running a benchmark, or you're running a use case where you're taking snapshots, so you have to process it really fast. It's a selfie, right? So you push your algorithm to the hexagon, and then it starts working on the frame that you just delivered to it, or a couple frames. What happens to CPU meanwhile? If the algorithm is big, if the algorithm is too consuming, then a CPU will fall asleep. The AI accelerator will finish with the workload, go back to the CPU and say, hey, here it is, take it. CPU would be asleep, so it has to wake up, it has to get your application back on stack and then receive that answer. With the software that we delivered, we have a number of different flags where you can go and set up all these different parameters and tell CPU, do not fall asleep because you're running a selfie use case or you're running a benchmark. Stay up, wait until you get the response, so you don't have to waste this valuable nanoseconds or microseconds to for this waking up activities and other things. That's something that TF Lite, being a kind of a community generic kind of runtime framework, has no understanding of. Another use case would be, as I think in the previous discussions, we talked about this low power use cases. Let's say you're doing the same algorithm, but this time you are doing video. So it's not important for you to take this frame, throw all the compute resources and process it right away. You have 30 frames per second coming into you, and you have your camera active, you have your GPU and your preview window active because you're like recording a video of your kid playing soccer or some other game, right? So you can only allocate a certain bandwidth for the AI processing, certain bandwidth for the memory, and then you also need certain cycles on a CPU and certain cycles on maybe GPU or other things. Again, TF Lite, being a kind of a common runtime framework that doesn't really understand the specifics of the hardware, probably not going to be good for that. Whereas with a Snappy and other software that we have, we can control the system and we provide it with all these flags, so you can go and do all these, specify all these parameters.
Okay,
but we support both of them.
Yeah, I guess this was an exclusive answer. Okay, so it seems that there are no more questions. Well, at least, yeah. Okay, all other guys who want to ask some questions, they got your email, so they can contact you directly. Okay, good. So thanks a lot for the presentation and for answering all
and sorry
questions.
for a little miscommunication. Apologize for that.
No problem. Okay, good. So then we are moving to the next talk from Intel. A good question is whether, okay, so this talk would be started by Vivek, and a good question if he will be starting his presentation in, okay, here I am. Vivek is attending physically this conference, so he would deliver his presentation directly from the room, from room 2019 at CVPR. Okay, guys, we can't hear you and we can't see you right now. So I guess we need to wait maybe 1 or 2 minutes till everything gets connected.
Hi, Andrey. Can you hear me?
Yes, I can hear you. I can't. Oh, okay, I can see you too.
Hello.
Yes, hello.
Okay, 1 second. Let me work on the audio. Okay, I think. Hello, is it better?
Yes, it's better. And yeah, we just cannot see your slides.
He can hear you, but you cannot hear him.
I see. Is that okay?
Andrey, can you thumb up if you can hear us?
Yes, we can.
Okay, good.
Okay, perfect.
Yeah, so they can hear you.
That should be okay.
Yeah, should be okay. I mean, later, because,
later we will.
If they have questions, yeah, well, that's a problem.
Let me try this. Okay, so the microphone is working, and just the headphone. Okay, can you try saying something?
Yes.
No. Okay, I still can't. Don't. It's always. That's the. Okay. Is it better if we use the audio from your? It's fine as long as you can hear me.
Yeah, but the problem is that I don't know if it's going to fit here. Okay, so
no, that will be too much complication. We'll do it later. Let me start with after the Q&A.
And then for the what we can do is for the Q&A.
Yeah.
Put the audio here.
Perfect.
Okay.
Perfect. Okay.
Yeah, because mainly, mainly because it's lunchtime here is for the people like and for you.
So. Okay. Perfect. With that, I will share my screen and we can start the presentation. Okay. I think I am audible on the session. Yeah. Okay. So thank you, Andrey and Radu, for inviting us to present the optimization of TensorFlow on Intel Core platforms. I am Vivek Kumar. I'm the senior AI software architect at Intel, and I'm joined by my colleague Manoj on this call with us, where we are going to talk about what Intel has been doing, the hardware evolutions and the software optimizations to provide help developers and our industry partners and our consumers the best developer and user experience. Okay. With that, yes, hi. So this is the overview of the content that we have. First, we are going to take a look at the evolving AI use cases at client and the edge platforms. And then we are going to take a peek into the 12th generation hybrid core architecture that Intel has recently launched, which has dedicated hardware performance knobs and instruction sets for optimization on deep learning applications. Going further, we will take a look into the AI software toolkit that Intel has provided with their for their hardware, CPUs, GPUs, XPUs in general. And then we are going to take a look at optimizations pertaining to TensorFlow and 1DNN and some of the compression techniques that we have used with our Intel quantization and compression tool. Yeah. So if we look into, I think before me, there were a couple of gentlemen from other companies who had discussed about the evolving AI use cases at the edge. They mostly talked about mobile, but today I'm going to talk about the use cases that are evolving in the PC world. And the PC world is where the client platform are there. So, and similar to what things are evolving in mobile world, we are also seeing the same evolution in the PC world, where there are tools for productivity and creator tools. Basically, like everyone, a user on the PC, they want to develop a content for text, audio, music, images, and post it on social media. This is like the one of the use cases. The second use cases is people definitely want to improve their images that they took in a very different environment, and they want to use AI to help them and improve their experience with the creator tools. So some of the industry partners are very actively working on putting AI into their applications, and those applications are actually running on the PCs, and that's where we want to drive our next generation hardware and the software support to help give a better performance on those applications. Going further, last few years has been tough for everyone here. Everywhere in the world when we had the pandemic, and the one thing that we really learned is how important is the digital communication and digital collaboration. And with that in mind, the remote learning and the remote working is actually one of the very paramount use cases in PC world as well as the edge devices. And some of the typical AI models and applications are definitely the noise suppression, transcriptions, translations using the NLP, language models. Then there's a need for improving the in-camera experience, then gaze detection. If you're talking to someone in the conference, like right now when I'm talking to people here in the conference room as well as on the Zoom, it becomes very, very critical that we have the AI models, most performant AI models, which are actually helping the developers and the customers to have a good user experience. And also there is a bigger and deeper requirement of improving the video content and games on the PC world, where on the client side, when we really want to save the bandwidth, but at the same time, nobody wants to compromise on the quality. And that's where the super resolution for video content as well as the in-gaming experience becomes very, very critical. And so in general, these are the three use cases which are driving, or you can say the three AI buckets which are driving more and more requirements on the edge side. Either it's PC or it's other devices which are prominent on the edge. With these use cases in mind, we want to so these are all important use cases. They're few years back, they were in research with a great demand of the consumers, and we need to provide them, put them to production as fast as we can. And with the pandemic and digital world evolving fast, there is a higher need to provide the better experiences. And some of the optimization vectors in providing these models from research to a production environment is definitely the sustained AI compute performance, which we just listened in the previous talks. What it means is a edge device should be able to perform a sustained AI performance and without failure. And but at the same time, the edge devices are very susceptible to performance per watt. Because they are battery powered. They also are memory and the compute restraint, so latency is another factor. And that's where the other optimization vectors of small batch sizes and quantization of the AI networks come very, very handy. So if by looking from a research to production, we also analyze some of the trends in the AI models on the client and the edge platforms. So over the years, roughly from 2017 all the way to 2021, we can see that typically the tensor size for AI models in the deep learning AI models have almost doubled every 2 years. And at the same time, when we look at AI model a few years back, they used to be as simple as one input, like an image and or a LS or a audio in a sequence fashion with LSTM and other AI models, and the one output. However, with evolving complexity of the AI applications on the client and the edge platform, we see that multiple insights and different types of insights needs to be driven from a single model. And that actually leads to one model giving multiple outputs. It means is each of the output needs to be analyzed with a different post-processing steps to give a different insight for the application. Not even there was evolution in models, and no one AI model can actually solve the problem of a complete end-to-end application. And there came the sequential model and the concurrent models that need to be run and deployed on the client and the edge devices. And what it means is typically, for example, if you have a camera, there is a real-time requirement of solving a AI problem within 33 milliseconds if it's a 30 frames per second. So in that case, if you're running multiple AI models in sequence, you are impacting the latency. And that's where the need of running concurrent sequential models with high demand of multiple outputs for running one single application becomes very important. So as we see that tensor size and model complexities are increasing very rapidly, and they are also driving the need for the compute and memory requirements at the edge. However, as we know, the edge devices are constrained by their own compute and memory, by their battery power and compute memory and all the other constraints. To solve this, Intel actually launched a new generation hybrid architecture where we have two types of cores on a single SoC, P core performance core and E core efficient core. And you can have multiple instances of each of the core depending on the type of market you are in. So basically for a laptop, for a desktop, you can have a different combination of E core and P core to which can derive different optimization and design points based on the AI requirements that you have for your customers. Yeah. So these P cores and E cores, they have the same architecture, but they have a different micro architecture to make sure that P core on one side, it gives a better single thread performance. However, at the same time, E core gives the better efficient throughput. So basically, it gives multi computational efficient computational density performance can be achieved by E core. But if there is a high real-time requirement and a single thread performance needs to be improved for a particular AI model and application, P core should be the one should be used. But there is a need to efficiently manage these cores as well as managing the battery and managing the overall system health. And that's where Intel is providing a hardware software solution. We call it Intel Thread Director, which actually monitors the runtime instruction mix for each threads which are running from the AI applications. It provides runtime feedback to the OS, and which actually guides OS to dedicate high priority threads to P core for a better performance. At the same time, gives background threads to the E core where there is a need of providing efficient throughput in AI workloads. So with that, as we know, if there is a requirement to focus on throughput, E core is the solution. If there is a requirement for performance, P cores are the are good to go cores for. But anyway, it's under the hood. Intel Thread Director takes care of it. You just deploy the AI model and the workload, and it will automatically assign the priorities for each the threads and the applications automatically. So that's under the hood, and no user or a developer interaction is required to optimize it. With that, there are a couple of other improvements in AI hardware that we launched, and one of them is VNNI, Vector Neural Network Instructions, which are optimized for 8-bit computation, and they are essentially are vector operations, which provides the first of all they do 8-bit computation. It saves the bandwidth memory uses by 4x straight away. And then you have, and these instruction sets are very particular to solve three instructions in one cycle. So what it means, it gives you a performance boost of 2x in your computation at the same time. And indirect benefits of these is that you are going to get less cache utilization and possible potential bandwidth bottlenecks that you are going to get will be resolved by this smart instruction set. We call it VNI. This is for the core platform. For our server platform, we have advanced instruction set called AMX, which actually drives performance for deep learning and the AI applications further. And we have another instruction set XMX for our GPU products. On the top of the hardware optimizations, we look into the software tools and optimizations that we have brought about with our CPU, GPUs, and accelerators and FPGA. In general, we support all the popular AI frameworks, TensorFlow, MXNet, ONX Runtime, PyTorch. We support all the frameworks. We also have OpenVINO, which is a homegrown Intel developed highly optimized runtime framework. All these popular AI frameworks, whether it's external or the internal, the Intel developed, they're all supported with the Intel One API toolkit. And Intel One API toolkit is actually you can build your build, analyze, and do your high performance cross architectural applications on just on utilizing all the goodness of the languages that Intel One API support, and with the quantization tools like Ink that we are going to talk about in the next few slides. And of course, there is a bigger optimized, bigger advantages coming up with the 1DNN library, which we are going to take a look in the next slide. So in general, Intel One API is an open source API for all the customers and developers and partners to go and develop their applications on. So with that, let's look into 1DNN. So as I said in the previous slide, 1DNN is an open source cross-platform library for deep learning applications. This is where Intel is very different from typically what other companies are doing. We like to make our code open source, and this is where we want the community to come and help us, and we help them together to improve the performance on CPUs, GPUs, and other products that we are working on. So in short, what 1DNN does is it supports basically all the let me grab a laser pointer. Yeah. So if you look into the deep learning applications, there are operations like convolution, matrix multiplication, and so on. They are very compute intensive operations, but at the same time, there are memory bandwidth limited operations like pooling, batch normalization, and so on and so forth. So these are the typical categories of the AI operations that 1DNN goes and optimize. And how do we do it? So typically what we do is we look into the first approach is to look whether we can fuse some operations and to make to overcome some of the memory bandwidth issues, and that will give optimized performance because of that. At the same time, if you look into what the standard AI framework operations are, they might be very compute intensive, and we replace them with a highly optimized custom 1DNN operations. And again, this is all part of the 1DNN library. So there is no custom hand tuning by anyone, any developer or customer is needed. However, this is an open source library, so anybody is free to and open to contribute on this. At the same time, this 1DNN leverages the hardware improvements like Intel DL Boost, AVX2, AVX512 instructions, and other processor capabilities. It definitely supports all compilers, OS, and CPUs. It supports all the Intel CPUs, all Intel graphic processors and accelerators. And there's a GitHub link for anyone who wants to take a look at it. After 1DNN, as we looked into the previous slide, we looked at the library section. Now let's look into what tools that Intel is able to provide and to the open source community. And we call it Intel Neural Compressor Toolkit. This is open source Python tool, again, open source to deploy low precision inference solution. It supports models in all the popular frameworks, TensorFlow and ONNX, PyTorch. And what it does, it actually has compression. It uses a compression techniques of quantization, post-training quantization, post-training dynamic quantization for activations, and it also helps in quantization-aware training. At the same time, it does give benefits for a developer to use pruning techniques, and provides all mixed precision support at the same time. I will go much deeper through a demo of Ink, which will tell you how easy we try to make it, because typically what we have seen is the traditional or manual way of quantization is very tricky, and you need hundreds and hundreds of lines of code to do a quantization from FP32 to Int8. So with that, let's look a little bit more detail in what Ink does. So let's say if you have an original model in FP32, you do quantization, you got a low precision model, but you want to do reduce your model size further. You can use pruning, sparsity, and distillation, which is very common in language models, but at the same time, some classification and the object detection model also you can leverage from it. So we provide a auto tuning tool, which is ML driven, to generate a low precision as well as a compressed model at the end. In this process, we'll take a look at the demo when then it will be more clear on what exactly and how to use this tool. So just a brief introduction on what quantization mean. This is a very layman point of view where we want to map all the FP32 data to Int8. This is what quantization mean. But of course, there is much more nuance to this. This as not simple as this, because if we just do a straight quantization like this, it's going to affect accuracy at the overall accuracy as well as accuracy within the layer. So we have developed some recipes around it, how to do effective quantization without dropping the accuracies. Yeah. If at the same time, if we have, so let's say we did quantization, and this is a sample weight matrix, and we want to do further compression, and to do that, pruning is a technique where you want to remove the unscrupulous AI networks, the graph in the AI model, or you want to remove some of the operations which is not going to affect your accuracy at all. So we call it pruning. Everybody calls it pruning. And so basically the tool helps you in pruning some of the neurons which are not going to affect your accuracy adversely. And then if you can do further use the sparsity to just take them out. In a way, you are saving memory and compute both at the same time to improve your performance for AI models. So that's very critical. And at the same time, you can also use distillation. And this is how the distillation model, distillation technique works. Is you have a teacher model which actually helps in distilling some of the knowledge to the student model, which can be very compact and which can be very efficient to run on an edge device to improve, to give a better performance. Yeah. So with that, let's look into some of the nuances of the inference optimization. So for example, if we have a input coming in FP32 and weight coming in as FP32 as well, what a very layman quantization technique that we do is just fuse both the convolution and bias and add and make a Int8 operation, as simple as this. However, this is a convolution. It works straight away, perfect. But there are other techniques which are also employed under the hood in the Intel Neural Compressor Toolkit, which does the quantization. So the most important key thing is trade-off of accuracy is not acceptable in most of the solutions. So accuracy can be one of the parameters for the toolkit to generate a quantized model. And again, the quantization is done keeping in mind all the hardware instructions like VNNI and other instruction sets, which are very, very important for the deep learning and the AI model operations. Okay. So with that, let's look into the graphical user interface of the quantization. So basically, you can actually use a graphical user interface. You can just select your ONX model, for example, which is a 32 model, 32 precision. Just add the optimization where you want to do quantization. You just name it with this tool, and then run it with the dummy data set. And basically, dummy data set is actually a subset of the larger data set. And you just run it to generate a quantized model from a FP32 model. Okay. And then next you can go to benchmarks, add benchmark. So in this particular case, we just want to compare the performance of a quantized model with the original model, and we'll just see how much improvement we can do it. This is a ResNet 50 Onyx model in the original form. And so basically we just ran for the input model. Now let's select the quantized model, and we can select how many cohorts instances you want to run it on, and then just wait for the system to complete the performance benchmarking. And this is all part of the Intel Neural Compressor Toolkit. So the optimization technique, benchmarks, profiling, datasets. Datasets are a location that you can select when you are launching the application. So with this, what we can see that after quantization, we are almost 2x. We see the 2x performance in the throughput. And same way, you can add a new benchmark for accuracy and run it and see how much performance improvement you can do. And this is a very easy to use graphical user interface. Again, this tool is open for anybody to use. There's no hidden links or locations. It's on the GitHub. And with this, in general, what we have found that the typical way of quantization involves a lot of calibration data set, and then you need to be very hands-on on some of the quantization recipes, and because otherwise you are going to lose on your in the accuracy. So the Intel Neural Compressor Toolkit in effect provides all the advanced quantization recipe as a part of the tool, model calibration, and as well as the auto tuning flow. It's already there. We have done quantization for popular AI models, and we have kept it on our GitHub as in our Intel Model Zoo. The links of that we will share going forward. So with this, as you remember, we just talked about the software optimization using 1DNN and then quantization. So with that, if we take a ResNet 50 model and a batch size 8, we have a baseline performance with a TensorFlow on a FP32 model. If we just enable a 1DNN, which is Intel optimization specific for CPUs, GPUs, and all the Intel products, we get a straight away 2.1x performance improvement. And if we quantize the model with the Intel Neural Compressor, and then we run using the same TensorFlow APIs and the same workflow, we are going to get additional 2.8x performance, which is like a 6x total performance gain by using Intel One API on top of stock TensorFlow. Next, we are going to talk about how to enable these optimizations in already available TensorFlow that you can download from the PyP. Yeah. There is some more data on how much performance improvement you can see with the quantization of in-depth models. So here is ResNet's ResNet 50 and ResNet 101, Inception's V3 and V4, and MobileNet V1. So if we just quantize a model, FP32 model to in-depth model, we can just see the performance improvement. They are not same for all the models, because not all models, AI models, are same. They have different operations, different memory, different requirements. So Inceptions are exception here, and getting a lot of advantage through the quantization, and ResNets are on the ballpark of good performance improvement. Yeah. With that, I'm going to talk about AI benchmark that we were able to run with Intel optimizations and the performance improvement that we see. So in the current generation, 12th generation, the hybrid desktop CPU, we ran on a Windows 11 OS. We ran the AI benchmark 0.1.2 version, and TensorFlow 2.9.1 was used. We could see that the overall training score can get a 2x performance improvement straight away. And these are FP32 models, not even quantization, because this particular version is still using FP32 AI models. So this is just the one DNN, which actually helps in 2x performance improvement in training, 25% improvement in the inference score, and overall device score, it gives around 60% improvement. So that's a huge advantage with just using Intel optimization. But how do we enable it? That's very straightforward. So if you have a TensorFlow already installed, you can just enable Intel optimization by just setting up this flag in the runtime. So in case of AI benchmark, we just set the flag like this, set TF enable 1DNN optimization as 1, and then we launch the AI benchmark straight away. And basically we got the 1DNN custom operations are on, and that gives us the full performance improvement straight away. So there is no hidden runtime configuration. There is no hidden toolkit. It's all open source, and it's all there for anyone who can use it. There is some other good news that we have to share with you, that 1DNN optimizations are now default on TensorFlow release greater than 2.9.1. So you don't even have to set the flag now. After the next release, it will automatically be enabled for CPU platforms. In general, if we just summarize, we have improved our hardware instruction sets to improve AI performance on the 12th generation hybrid architecture. We have been working very closely with Google on submitting our improvements on TensorFlow, and then as we have seen with the 1DNN operation optimizations, we can improve the performance by 2x. With the low precision, we can get additional 3x performance improvement on a rough park. We can get more. It depends on the model, so quantization. But an average of 3x performance improvement can straight away be achieved using quantization technique. Yeah. With that, there are some resources to share. These are all links to the open source GitHub, and as well as some of the public blogs that we have released on how to enable optimizations, Intel optimization, and how the Linux TensorFlow is defaults to Intel. Yeah. And with that, thank you everyone for listening to the talk and your attention. Yeah, I can take the questions from the blog. Before we do, I think okay. No, just yeah. So okay.
Can you,
so, Andrey, what I'm going to do is I am going to switch the audio so that we can hear you people on the Zoom. Or
you can mute here. Mute yourself here.
Then we put the audio here. So can you hear us, Andrey?
Yes, we can hear you.
Okay, yeah, so perfect. You can talk now.
Yes.
Okay,
so
great.
You can do it.
Okay, yes, thanks a lot for the presentation, for a nice tutorial. I already saw that there was a question in the chat, and Manoush replied to it. But I guess it would be good if Manoush can also answer, like he can. I guess he can unmute himself and just provide an answer to those who cannot read it. So the question was: does Intel One API support DirectML, or does Intel support DirectML?
Okay. Yeah. I think Manoj is already typing. Or
Yeah.
Oh,
but
you can answer.
Yes. Yeah.
Yeah. Sorry. So, so if I read the question again, is that does Intel One API support DirectML, or does Intel support? Yes. So I think Manoj answered it correctly, that Intel supports DirectML through the OS stack, and DirectML optimizations are done for GPUs and XPUs. So they are definitely part of the One API stack. Yeah. Any other question?
Yes, there is another question on whether Int8 is supported in DirectML.
Manoj, if you can answer.
Yeah, so DirectML is the GPU path for Microsoft, right? It's not the CPU. CPU is the MLAS library, which is also supported if it's the block diagram which Vivek was sharing on the ONNX runtime, right? So if it is a DirectML, VNNI is not supported through DirectML. It is supported through WinML API or ONNX runtime API or TensorFlow PyTorch using either MLAS or one API library, right? Because it's a CPU path. On a DirectML Int8 side, which is a GPU, if the question is related to the GPU, that is something Microsoft is working on. I'll let Microsoft if there is someone from there, but whenever Microsoft enables the Int8 path by default in DirectML, yes, it will be supported, optimized and supported on DirectML.
Okay, thanks for the answer. We have another question on YouTube. Will one DNN be available for PyTorch?
It's on YouTube.
Oh, okay. So yes, the answer is true. Yeah.
Okay, so it is already available for PyTorch.
Again, it's already supported. Further optimizations are like it's a continuous process but it's currently supported through a different plugin, and it's we have further more optimizations to go, but it's supported as of now.
Yeah, to add, it's not by default yet, but yes, it is supported, right? It's not how TensorFlow all optimization yet has been done.
Okay, good. Next question. In TensorRT, we can develop our own custom plugins. I wonder whether Intel has this, if we have our own TensorRT custom plugin implementations and need tool to convert this to Intel platform with minimal or no code.
Yeah, so I think the answer is Intel One API tool. Basically, we have the support for DPC++ language support, where you can go and develop your own custom plugin. And yeah, and anything else, Manoj, would like to add?
No, it's so the DPC++, you can take the CUDA or TensorRT CUDA code, right? And it can convert into, you can convert to DPC++, which can run on even on Intel GPUs for the custom plugin support.
Okay, I hope this answers the question. Okay, one question from my side. So I see that FP16 format is still not supported on Intel platforms. Is there any particular reason for this decision?
On the CPU?
Yes, on the CPU.
So yes, it's currently not supported. It's more about the architecture change, which has been in process. But future platform, I do expect there will be support for FP16. Yeah. On GPU and other XPUs, yes, it's GPUs are supporting, right?
Yeah, so with GPU it's supported, and okay, and do you know when approximately this support will come? So like at least in terms of a number of expected years. So like whether this is about to be launched in newer generations, or this is something that is far, far away?
So it depends on the platform. I would say is, yeah, it's not that far away. I don't know what's the definition of far, far away, but yes, it's coming on a few of the platform, which will be more targeted for deep learning customers. But there's also bfloat16 already available, right? We do support also bfloat16. Yes, native FP16 support is on the CPU is still under works. But few of the platforms will support it soon.
Yeah, because for us, it's quite interesting why you decided to go for bfloat 16 support instead of just the standard float 2.16.
I think they because it was more server side, right? Request and Google. It was a Google requirements possible. We are not from the server team, so I expect for native float 16 support will be there. That is one of our future data type support. That is only missing on CPU. There was no GPU native support. We started adding it, right? That's why it is there from past 2 years. But before there was no GPU also native support. So we do expect in future it will be also available.
Well, good to hear that. And yeah, thanks for the answer.
Any other question from here in the room? Good. We are good over here as well, Andrey.
Yeah, I think that there are no questions in the chat. There were already quite a number of questions. So yeah. So thanks a lot then for your presentation. Again, it would be available on our YouTube channel, so you can check. Especially, yes, there were quite interesting moments when you were showing how to use your tools, quantization tools, and I hope that the participants can later on come and view it again to get a better, to know how to do this in practice. Okay, good. So if there are no other questions, then we are moving to the next talk that will be given by Abdel from Synaptics. And he will tell us about...
Andrey, wait 1 second, please, because we have to, disconnect the laptop and reconnect.
But I think Abdel can already start sharing. Yes, yes.
Hey, Andrey, can you hear me well?
Yes, I can hear you.
Good. So shall I share my screen already?
Yes, yes, sure.
Okay. It's okay to start now, Andrey? I can start?
Is everything? Yes, Marcus is okay. Yeah, I think you can start.
Okay, thank you. Okay, so today, I'm Abdel Younes. I work for Synaptics Semiconductor. I'm based in Switzerland, in Lausanne area. And I lead the solution and platform architecture team at Synaptics and mostly focused on AI and ML technology. So today I'm going to talk about the framework that we developed for the integration of AI model onto our main chipset, which is the VS Video Subsystem 680 processor. And we're going to see how to use this, how we are using the Synapse ourselves, and how our customer can use the Synapse framework to optimize the AI models for an optimal inference on the edge, that is to say, on the VX680 platform. So I start very briefly with some of the products that are currently shipping based on our chipset, the VX680. So there are some Korean products, the LGU Plus from LGU Plus. So we have a set-top box, we have a soundbar, we have also Korea Telecom Giga Genie products. We have a video conference from Arcadian for an operator, a European operator, which is basically doing video conference with a lot of AI in there. We have WNC, which is doing smart display. So the VX680 is a very versatile chipset, which can target many different use cases, many edge use case. So from set-top box to soundbar, going through smart signage or smart display. So one of the first application that we developed at Synaptics is super resolution, because we felt a need to develop a better way to do upscaling. So most video content are still 2K right now nowadays, or even lower, 1K single definition, and all the TV that you can find in the market right now are at least 4K, even going to 8K sometimes. So with AI and with the super res kind of model architecture, we can do a better quality upscaling than traditional computer vision methods. So we develop our own, we train and develop as a use case and as a proof of concept, but also because we want to also show to our customer that this is bringing a better video quality. We develop our own super resolution model, but we optimize specifically to run at more than 30 frames per second in completely secure mode, and I'm going to come back to this point, on the VS680 processor. So just an image that can, I'm not sure this will show correctly over the internet, and over Zoom, but this is the kind of improvement that you can get with super res. So actually, this is the improvement that you get with our own super res model. So our super res model is not the best in class in accuracy, but so far this is the best in class in terms of speed and with quite good accuracy. So this is what we choose to focus on. Now, having said that, Andrey from ETHZ proposed us to organize a challenge about super resolution. So we started last year, and we had really tremendous contribution from users all over the world, and so this challenge is already the result of the challenge is already available on the website, and we are doing it again this year. We will do some change in the evaluation of the challenge. So this year we're going to automate the download of the user contribution, the testing, and the performance report will be automatically generated. And we will still using the same way to import the model using the Synapse toolkit. We are not going to use the Android NN API. I'm going to explain why. And the new, also one new thing that we will do is to provide layer by layer profiling. So the contributor will be able to see what are the bottlenecks in their model. So we're talking here about on target, on device, layer by layer providing, and that's very easy to do. So those are the results from last year. So SuperRes is evaluated through three main metrics. So the first metrics are the quality of the upscaling. So you have the PSNR metrics and the SSIM metrics, and then the other metrics is the inference time in milliseconds. Okay, so Andrey and the AI benchmark guy, they invented some formula which I don't know, but combine those two metrics and generate a score. So here I present the score that we were able to achieve with two of our own models. So we were on top because we are really optimized in terms of speed. You can see that for the challenge, we were able to run in 8 milliseconds the upscaling for the first model, and in 15 milliseconds for the second one. But in terms of image quality, we were not the best. Clearly, the best one was MCG, I think. And next we had SMM research. So they did really good job in terms of accuracy, in terms of model size, but still some way to go for the inference time. So we hope that this year they will get even better thanks to the new profiling data that we will generate. So about the VS680. So the VS680, I already did some description last year, so I'm not going to go into much detail, but briefly, so the VS680 is an SoC, a system on chip, that targets multimedia application. So it includes a CPU, quad-core A73, running at 2 GHz, a GPU from Imagination for VR Series 9, and an NPU, so a neural processing unit from VeriSilicon. That's the Vivante VIP 9000, which is able to do up to even better than 6.75 tops, maybe 7 tops. So this, beside those three main blocks, this VS680 contains video processing, IPs, video codecs, dual camera ISP for the integration of cameras module, and a security engine. And that's one of the main points of the Synapse toolkit. So the Synapse toolkit was really designed to, and framework and driver designed to support secure inference. By secure, we mean data that are not available to the user space, to Android or Linux. So it makes use of the trusted environment, which is called Trust Zone, which is the subsystem of the ARM processor. And all of our drivers, including the NPU and the video codec and audio codec, are implemented to process the secure data in the trusted environment. Going into a bit more details about the NPU, so the SoC consists of many blocks, which all communicate through the same bus, so the AXI fabrics. So the GPU, the video codecs, the NPU, and actually the DDR, the RAM, all communicate through the same bus. So that's a very important point, because we are able to transfer efficiently data from one component to the other. So the NPU is, as the GPU or the CPU, able to retrieve data from the DDR or put data into DDR. The NPU is composed of 4 major blocks. So you have an internal memory, SRAM, a static RAM of 1 MB, which is designed to provide fast access to small data. We have the main power, the main processing cores, which are optimized to run convolutions, either plain convolution or depth-wise convolution. So those cores, we have up to 22 cores available on this NPU, on the VS680, and they are designed to run efficiently 8-bit quantized convolution or 16-bit. But we really favor 8-bit because this is what offers the most performance. You have a tensor processor, which are 8 tensor processor, which are used for constant operation, like fully connected, transpose, and element-wise kind of layers. and you have a PPU, so a parallel processing unit, which is a kind of GPU shader, but is able to run OpenVX and OpenCL code kernels in either quantized 8-bit or 16-bit, or floating point 32 or 16-bit. So this shader is really used as to run glue layers between glue layers that are not supported by either the convolution core or the tensor processor core, or also as an interface to the other component, the input-output that comes from other component of the system. Okay, so now we talk about the hardware. Let's talk about the software stack. So we have two ways to run models on the Synaptics VS680 platform. So this presentation will focus on Android platform because this is what most customers are using right now, but we also support plain Linux platform. So the first and most easier way to run an AI model is through what we call the online model, the online inference, sorry. So a machine learning application will use a TensorFlow Lite runtime library, or a PyTorch mobile, or in China, they will use Lite, which is becoming very popular. And this TensorFlow Lite model, for example, will be parsed on the target through, for example, in this case, the Android NN API runtime, which is standardized by Google, as you know. This will communicate through RPC to the Android NN hardware abstraction layer that Synaptics has been developing. This HAL then targets an OpenVX API. This OpenVX API actually is a compiler. It generates what we call a binary graph, an executable binary graph. We call it executable binary graph because what is actually generated is an executable format that is almost directly run by the NPU. So we don't need to do any parsing. Almost no parsing happens in the NPU driver, what we call the Synapse secure driver. So once this EBG executable binary graph is generated, there is no need anymore for all the upper layer stack. So this EBG can be run almost directly on the NPU. The second way to run an AI model is what we call offline conversion. In this case, rather than interpreting and parsing the open format like TensorFlow Lite or ONNX or Caffe, what we do is we do an ahead of time graph generation. We parse the TensorFlow Lite on the host using the Synapse toolkit. So the steps to run, I'm going to provide a walkthrough in the next slides, but in a nutshell, you import the TensorFlow Lite model with the toolkit. You optimize it if it was not optimized. So, for example, if you have only a non-optimized TensorFlow Keras model, then the optimization step will most probably happen in the a lot of optimization will happen in the toolkit, but most of the TensorFlow Lite already has a lot of optimization like layer pruning or layer fusion. But still, the toolkit will do some more optimization. So if the model is not quantized. So, for example, if it is a floating point 32-bit TensorFlow Lite model, Acuity and the Synapse toolkit that integrates the Acuity toolkit will offer the ability to quantize this model, to generate 8-bit model. This is what we call post-training quantization. Once the graph is imported, the model is imported and optimized and optionally quantized, the toolkit will generate OpenVX source code. So source code that will target the OpenVX API. And then the rest is really standard. It is really using standard tool. The OpenVX source code that we generate using this Synapse Python toolkit will be compiled using a standard compiler on the host. So we use GCC, so the GNU compiler, but we could use Clang as well. Then once this is done, the toolkit, I mean, the generated executable will be run on the host platform to generate an EBG. So the same executable binary graph that was generated on the target using the online conversion. So here we're talking about the same format for the online conversion and the offline conversion. In the case of all online-offline conversion, we have additional option here, which is the encryption and the signature of the model. That's for the use cases where you want to run the model in a secure way on secure and trusted data. So about the workflow. So this is basically the same information, but shown in a different way. So typical model deployment workflow will be to first train a model with external tools. So it can be PyTorch, it can be TensorFlow, or some other, or Paddle in the case of China. This model then can be optimized with an external tool. For example, TensorFlow has the TensorFlow Lite compiler, the POCO, which can directly optimize and generate the unoptimized TF Lite format. Or you can use the Synapse toolkit to do the same thing directly from the TensorFlow model or the ONNX. Once this is done, you compile the model and you have two choices. So either you compile the model on the target or ahead of time using the Synapse toolkit on the host. Optionally, on the host, you can encrypt and sign the model. So for the secure use case. And in the case of the model computation on the target, you just generate the so-called EBG, which will be executed on the target. These slides, now what we talk about the workflow, explains the execution on the target. So in the case of online inference, so using, for example, in the Android NN API, the user process will communicate with the NN HAL implemented by Synaptics via an RPC mechanism. So the NN HAL, NN HAL implementation will interface with two different libraries. The first one is this OpenVX compiler, the very same compiler that is used on the host for the ahead of time offline compilation. It is compiled on the target for the and is used as is by the NN HAL to generate the same EBG. So the NN HAL will use the OpenVX compiler to generate the EBG, and then this EBG will be passed to the Synapse runtime, the Synapse user space libraries, through a very simple C++ API. We have extensive documentation of this API, but I will pause later on in the presentation. So this user space library will communicate through I/O control to the Synapse kernel driver, which will then pass the binary graph, the EBG, to the trusted execution environment, which will be then executed on the NPU. In the case of ahead of time precompiled model, the execution flow is a bit simpler. So we just need to load the model from flash, allocate the input and output buffers, and here we can use optimized buffers because we support the DMABUF standard Linux kernel way. We prepare the model of the execution of the model. Then we fill the input buffer. We select the input and output buffers, and then we just kick off the model execution. And when this is done, we will receive an interrupt from the NPU, and the user process we just have to read the output. So this is Synapse toolkit. So I think the time is almost reaching the end. The toolkit, the Synapse toolkit, sorry, is a Python-based toolkit which integrates, which can be run using Docker, and this way can be run on Windows, Mac, or Linux. It is able to import the main major format for AI, so TF-Lite, TensorFlow, Caffe, and NX. Is able to do model optimization. It will generate source code, OpenVX API using source code, and then will compile and execute the source code on the host. And then this very same OpenVX compiler can also be used on the target for the online way of running AI models. So we have 3 different EBG generated by the Synapse. So we have the standard EBG, we have the profiling EBG, which will provide layer by layer profiling data. So clock cycle, memory bandwidth, and type of instructions. And we have the secure EBG, so the encrypted and signed EBG for trusted and secure inference. So just this slide explains that we are using a very silicon software stack, an OpenVX compiler, which is can be used for many things. We can use OpenVX kernels for customized application that will run on the NPU. This custom OpenVX kernel can be run on the NPU, and the Synapse toolkit will enable the fast and easy integration of these custom OpenVX kernels. So we did a lot of optimization in this OpenVX compiler. We implemented compilation cache that enables up to 20 times faster model compilation when compared to the stock very silicon stack. We did also a lot of improvement in terms of stability and memory execution. Just some word about also the Android NN HAL. So this HAL we have the source code tree that is available to our customer that can support the multiple version of Android. It passes all the CTS and PTS that are necessary for Android. And it supports also the standard NNAPI compilation caching. So compilation takes time, even with the compilation cache. So by using the NNAPI compilation caching, you can just skip this first step and reuse directly the EBG that is generated by the compiler. As a final slide, I wanted to show the new score of the VS680 platform running Android S. So in the past, we were at score at 17 on the IoT ranking, and now we are up to 31.5. So all those optimization managed to offer much more stable and fast execution of AI models. We are still using the standard NNAPI, but in the future we have the option to do further improvements, like for example the integration of NNAPI caching into AI benchmark, or maybe integration of an external TF-like delegate instead of doing NNAPI. I wanted to go briefly over the Synaptic documentation, but I don't think we have time, Andrey, right? It's ready.
Well, I guess, no, I guess you can go through this briefly because, yeah, this information will be important for challenge participants.
Yeah, so our customer will receive and use the Synaptic toolkit, and we provide this documentation that explains how to use the toolkit. It contains most of the same information that I just showed, but in more details. It explains how to do profiling, how to use the toolkit to generate this EBG format. It explains the Synaptic C++ library, so the framework API, okay, which is a very simple C++ API, which you can use to run any EBG format in a very simple way. And it also provides some statistics about reference models. In this table, for example, we provide all the numbers for some popular models, and also the models that are contained in the AI benchmark for 404, I think, APK. So the numbers are in milliseconds. We provide the NNAPI CPU inference time using 4 threads. So here we're talking about milliseconds. The init time for the NPU, which is basically the compilation step. The inference time using the NPU, and the same value for the offline, so preparation, initialization, and inference. So if we take, for example, the MobileNet V2 quantized model, we can see that the CPU, the quad-core A73, is able to run the MobileNet V2 at 27 milliseconds, while the NPU, the same model, can run at less than 3 milliseconds, 2.6 milliseconds on the NPU using the standard NNAPI, and less than 2 milliseconds using the ahead of time offline way. The compilation step will take about 1 second, 1.4 seconds. This is this value here. So this is a rather small model, but if you look at the Inception V3, for example, which is quite large model, I think it's about 30 megabytes. So the CPU inference is about 300 milliseconds on the CPU. For NNAPI, it's about 10 milliseconds. So here we're talking about 30 times faster NPU execution rather than CPU. What is interesting here is that actually with the optimization that we did on the various stack, so the compilation, the inference, the driver, etc., the difference between NNAPI and offline, which is the best you can get, is not so far, is not so much. So we're talking here about, depending on the model, between 5 and 20% penalty by using the NNAPI. But for some other model, it can be more than that. For example, in the case of PostNet, we're talking here about 6 milliseconds, 7 milliseconds for the NNAPI, and we are at less 2 milliseconds for the offline. So offline can really provide a lot of performance when compared to the NNAPI. So what we recommend to a customer is when they have an AI use case, an AI model that they want to try on the platform, to first start with the standard NNAPI, and when they want to integrate a real application, we suggest them to use the Synapse toolkit for better performance. And I think I will stop this presentation with this slide. If you have any questions. Andrey?
Good. So thanks a lot. Yeah.
You go ahead, sorry.
Yeah, thanks a lot for the presentation and for providing lots of useful information. Are there any questions in the chat?
I don't see any.
There are lots of questions on the forum about the competition, but I guess we'll answer these questions separately. Okay, so one question from my side. So you have this VS680 platform. Are you planning to release some more powerful platforms?
Sorry, we are planning to?
Are you planning to release some new and more powerful platforms for IoT, for smart TVs?
Mobile phone, no. So this security is still the
No. Yeah, I agree. I'm just curious if there would be also some newer platforms from Synaptics.
Yeah. There are a lot of platform coming. So, but they are still in development, so we cannot communicate. But already we have we have about 10 different shipping products today, from Korea, Japan, Germany, and a lot more are coming. So it's a very, very successful chipset. And AI actually is really a very important selling factor for us.
And VS680 is the most performant one.
Yeah.
So, and the other ones are more for embedded. The other platforms are more for
Yeah.
Okay, so if there are no other questions, then we can stop here and maybe we can have a 15 minutes break before the next talk.
Okay, thanks a lot.
Thank you too for presenting
Bye-bye.
information. Yeah. Okay, there is one extra question in the chat. I will answer it before we take a small break. So the question is that in a benchmark, the highest score for IoT platforms is 35K, but in mobile SoCs, the scores are way higher. How do I transform one from another? For example, some Snapdragon also used in IoT chips. Can I simply use their score in mobile to compare with the IoT score? So IoT scores were obtained with a benchmark v4 so with a standard v4 version. And in case of mobile devices, the results correspond to a benchmark v5. So the simplest case how you can compare the results, you can go, if you go to a benchmark website to the web page with the results, you will see that there is you can press on the v4 button. I will just 1 second share. Okay, so if you go to a benchmark web page, so here we publish the results for phones, but you can also get the results for phones obtained with a benchmark v4. And these results are directly comparable to the results in the IoT section. So basically, it's exactly the same models, exactly the same workloads were used for benchmarking IoT platforms and for benchmarking smartphones. So, and in this case, you can directly compare the results of different Snapdragon chipsets for IoT platforms, Snapdragon chipsets for mobile devices, and yeah. So I hope this answers your question. And yes, there would be another version, a benchmark version for IoT platforms that is based on a benchmark v5. Yeah, and this is still work in progress. But you can expect that we will release it quite soon. Good. So, and now we take a 10 minutes break, and we'll be back in yeah, 12:30. 12:30 Pacific time. Hi guys, a quick announcement. Unfortunately, our next speaker from Huawei has problems with connecting to the workshop. So we'll now take a 25 minutes break and return back in 25 minutes. There should be a talk from Peyman Minanfar from Google Research. And he will deliver a talk directly from CVPR workshop from 219.
Can you guys hear me? Yeah. Okay. Can you hear me? Okay, perfect. Andrey, are you there?
Yes, I'm here.
Okay.
So I think that, yeah, we have still 1 minute. 1 minute is left till the break.
If you wouldn't mind, if you can stop sharing your screen, then I can start sharing my screen.
Yeah, sure.
Okay, great. Okay, are you able to see my screen?
Yes.
Okay, now I'm going to go into slide mode. Still see it?
Yeah.
Okay, perfect.
Everything is good. I think that we could resume, right, Andrey?
Yes.
Okay. Let me know when you'd like me to get started.
Yeah, I guess it's already 1 p.m. Pacific time, so we can move to our next guest, to Peyman Milanfar from Google Research, and he will talk about denoising for image inverse problems and machine learning.
All right, thank you very much. Thanks for inviting me. It's nice to be with you. So let's go ahead and start with the definition of denoising, which I'm sure is familiar to everyone. So we have a signal that's been measured. It comes from a clean image that has suffered from some noise degradations. And the idea here is to design an algorithm, a filter of some sort, that takes a noisy image and produces an output that's as close as possible in some metric to the clean image that we can't see. Now, denoising of all the different kinds of inverse problems you might be familiar with is one that I would say has delivered most impressively over the years. So here's an input-output pair that you can see. And we can denoise fairly large images. 12 megapixel is a fairly standard resolution on mobile devices nowadays. And we can denoise them with nearly state-of-the-art quality in a few hundred milliseconds on a phone, sometimes even faster, depending on the different pieces of hardware available. So I'd say denoising has come very far, and the path has been a very long one. Here's a fairly simple timeline of sort of the first 40 years or so of denoising. We started with very simple things: L2 regularization, a Wiener filter, and we've gone to heuristics. Various heuristics, robust statistics came in. Some of those heuristics were later made into more mathematically precise form, things like the bilateral filter, but the design of that even was somewhat ad hoc. And then we went to ideas of self-similarity, things like non-local means that formalize the process a little bit more. BM3D, empirical Bayes, I'll talk about these, kernel regression, sparsity methods, and so on. And so that kind of brought us to around 2010. And if we were to look, as we did in around 2010, at all the algorithms that were available at that time that were state-of-the-art, we were faced with the following question. There were many thousands of papers, but very different algorithms had similar performance. And it seemed like somehow we were getting close to performance bounds at least in terms of mean squared error. And so we wrote this provocatively titled paper called "Is Denoising Dead?" And we sort of asked this question. The answer was no, but we did establish, along with our colleagues Levin and Adler in a separate paper, that we were getting pretty close to as well as one can do in the mean squared error sense. But that wasn't obviously the end of the story. Many more methods were developed in the years since, and the biggest changes, the biggest improvements coming from methods employing machine learning. And so I'm not going to go through all these different methods, but suffice it to say that at this point, I think we can get essentially state-of-the-art quality that is achieving as good a denoising as you could possibly hope for, at least in the L2 sense. Now, many different applications have come out of this, especially to scientific use cases. Here's one example of work that we did with our colleagues Mangal Prakash and Florian Jog from both Germany and Italy that applied this method. It's a hierarchical VAE, applied it in an unsupervised fashion to denoising microscopy images. So the images that you see here on the left-hand side column, these are very, very noisy microscopy images. The baseline unsupervised approach is something called noise to void, and ours on the right-hand side, as you can see, we can remove a tremendous amount of noise and preserve a lot of structure. Now, it's important here to note that this is not a general denoising solution necessarily. This is a denoising solution for a particular use case, but the use case is pretty broad in terms of microscopy. And similar methods have been applied for commercial photography as well. Okay, so, but the more important point that I want to get to here is that denoisers can do a lot more than just denoising, and that's kind of the focus of this work. We want to be able to solve more general inverse problems with denoising as an engine. And as you probably well know, denoisers also form the basis of many neural networks and many of the recent methods, things like the denoising diffusion approaches. Here's a kind of unexpected example some of you may have seen me talk about in previous presentations. The image on the left is a blurry image. The image on the right-hand side is a reconstructed version of it where the blur has been removed to whatever extent possible. And the engine that was underlying this algorithm was the median filter. It seems like a crazy use case for a median filter, but that's exactly what we used. All right, now a bit more generally, let's talk about denoisers and think of them as a function from the n-dimensional Euclidean space to Rn to Rn, but not all of Rn. Images are usually restricted to some range, 0 to 1, 0 to 55, and so on. And so it's basically mapping this 0 to 1 interval multiplied by itself n times. And in terms of notation, the x here, I'm thinking of it as an image scanned into a very big column vector. Now, these functions, these filters, if you like, are typically, but not always, non-expansive in the similar sense as low-pass filters in the linear setting. So these are kind of non-linear versions of low-pass filters. Before I get into some of the categorization of different kinds of denoising, let me give you a very intuitive idea which we have been using for a while now, and in practice, it's very, very useful. So the idea here is that denoisers give rise to what I call perfect reconstruction multi-scale decomposition. That sounds kind of fancy, but the idea is super simple. And it's the following. Suppose I take an image and apply a denoiser to it, and I'm calling that f of x here. And then I consider the residual. I'm also calling it a Laplacian operator when you compute x minus f of x. So of course, if you add these two pieces together, you get exactly x back, right? So this is in a way, this right-hand side is a decomposition of the identity operator, right? It's a splitting of the identity operator. Now that I've done this once, I can repeat this process. I can apply the same principle here to f of x and apply f to f of x, and then look at the residual of that. And the second term here at the end stays exactly what it was before. Now, I can keep going, right? I can just continue to repeat this process as far as I would like to. The important thing to keep in mind is that this approach is useful and it works for the practical cases that we're interested in. If f of x is non-expansive, if it isn't, then this repeated application of f can have unstable behavior, and it may not be pleasant to work with it. Okay, so now let me just take exactly what I said here and just introduce a new parameter here, alpha. So the denoiser is not necessarily a fixed thing. We can retrain it. We can parameterize it depending on how much noise we have and so on. So I'm going to introduce this vector of parameters alpha here. Otherwise, this is exactly the expression I showed you before. So this vector parameter alpha can be let's say if the denoiser is CNN, it could be the weights of that network. or it could be something related to denoising strength or any other parameter that you would like to use to parameterize this. All right, so I can repeat the process, and I'm just writing this in somewhat more formalized setting. And the idea here is that if I do this n times, what I get is on the right-hand side, I get two pieces. The first piece is f applied n times on, let me turn on my laser pointer here. Maybe you'll see it better. Okay, so this first term is the filter applied n times. And then the second term here is simply the accumulation, it's the cumulative residuals. So it's basically adding up all the residuals. And each of the residuals rk are the difference between applying the filter k plus 1 times and applying the filter k times. So nothing terribly surprising. All right, now I can take this and think of it a little bit more broadly. So remember, I've taken x and I have split it exactly into these terms. Now, what if I want to do a recomposition? I want to take these terms and combine them in a novel way to get not x, but some modified version of x. I can do that. And here, the recomposition, I'm calling this by just putting some coefficients in front of fn and in front of the residuals, properly normalized so that I don't send this output image into a range outside the valid one. And so now I have a formulation for a whole family of images that are related to x. And these are, you can think of these as processed versions of x. And I have two control knobs. I have alpha and beta, alpha being the parameters of the denoiser and beta being the parameters of how I combine these pieces together. And now I can set up a very simple learning structure where if I have example pairs, input and output, let's say I go to Photoshop and I take an image and I pull it into Photoshop and I do a bunch of fancy processing and I get xi hat. So now I have input and output pairs. Now I can take these two pieces and I can construct a loss function where the first piece is a training error that looks at the difference between the output that is one of the examples and the processed version of the input. And then the second term is some sort of regularization that I apply to the parameters that I'm optimizing over. And so this is a very nice, very simple structure. And I can go, I can make n be as large as I want or as small as I want. That also gives a way of regularizing the process. And so I can take an image and decompose it in this fashion and recompose it back, blending these components together and get an output image that, for example, in this case, is a high dynamic range version of this with various components of the image suppressed or enhanced. And this is effectively, if you write down the equations in an explicit way, what you have is you have basically a base layer. This decomposition gives you a base layer and a bunch of other medium to fine scale details that you then recombine to get the final effect that you're looking for. This is very, very useful. We get a lot of interesting use cases out of it. Here's one. There's very little noise in this. This is a professional photograph. But the face here has a lot of high frequency information in it, which we can selectively remove. So effectively producing a wrinkle reducer. We can also cartoonize and many, many other use cases. We can do dehazing. Here's one example. All right, so now that I've given you that quick summary of some of the very simple things that we can do, let's talk about general nonlinear denoisers. There are three categories. Pseudo-linear is one of them. I'll explain what they are. Then there's Bayesian, and this is including the two main Bayesian approaches, maximum a posteriori and minimum mean squared error. And finally, other PDEs or CNN-based ones, and you'll see how these fit into the other categories as well. So pseudo-linear denoisers first. So pseudo-linear denoisers, just like linear denoisers, except for the fact that the coefficients here of this linear combination of the input pixels can be possibly dependent on those input pixels. So this is just like a linear filter, except the weights depend on the input pixels. Here's a matrix form of the same thing. I'm going to take each output pixel and look at all the weights that combine the input pixels to give you the output pixel. Now, this is using all the input pixels in the image. Some of those weights might be 0. I might just be looking in a small local interval. It doesn't matter. I just set those weights to 0. But I can collect all of these weights into a vector, into a row vector like this, and then I can stack them all into a matrix, and I get a matrix W. And so at the end of the day, the filter that I get here, and this includes all the things like the bilateral filter and non-local means and all these other filters, what I get is some matrix times x. except that that matrix depends on X. And this is what I call a pseudo-linear filter. As I said, the examples are many. Here's one, is a non-local means weights. These are what I call KIJ. This is the Gaussian kernel that measures similarity between patches at this location and maybe other locations. This is what the weights look like. So if you were to scan these weight images into rows and normalize them so that they sum to 1, you would get one row of that matrix W. All right, these are very, as I said, very desirable for a couple of reasons. One of them is that you can prove that many of these filters approximate Bayes denoisers. They approximate map denoisers, MMSE denoisers. They're essentially empirical Bayes processes. And the other reason why they're really attractive is that they operate in 2 stages. One stage is nonlinear, which is the calculation of the weights. And the second stage is simply linear filtering. So you can play many tricks like optimize this nonlinear weight calculation to something that's offline, build a lookup table, and so on and so forth. And then it becomes basically a spatially adaptive linear filtering, which can be implemented very efficiently. All right, the second is map. These are Bayesian denoisers, maximum a posteriori versus minimum mean squared error. If you have a setup like this, x equals u plus e, the map estimate is the image that maximizes this posterior p of u given x. And the MMSE is also related to the distribution p of u given x, except that it's the expected value. Here's a cartoon of what these things look like. So the map gives you the peak of this distribution, and the MMSE gives you the expected value. They don't necessarily coincide. In fact, almost always they don't coincide, unless this distribution is unimodal and perfectly symmetric. All right, so let's talk about the map denoisers more specifically. The map denoisers are usually of this form. The first term that you see here, the norm of u minus x squared, this is simply because of the Gaussian assumption, so that's the L2 term. And then this phi of u is what we call a regularization, which in this statistical setting is negative log of the prior. So this is p of u here, which we assume to be something, and I'll show you some example of this. It's important to also remember, if you're familiar a little bit with the optimization literature, this here on the right-hand side is also called a proximal operator, which has many interesting and useful properties. Because of this realization that this is a proximal operator, there's some nice theory that shows that this right-hand side, even though it doesn't look like you could write it in a closed form very easily, it turns out there is a kind of closed form to it. And that is the following. The map estimate is x minus sigma squared, variance of the noise, times the gradient of phi sub sigma of x. Now, you might ask, we have phi of sigma, phi of x here, or phi of u here. What is that? How do I get phi of sigma? Well, phi of sigma, it turns out, it's a smoothed version of this phi. And it's called the Moreau envelope. Let me show you an example of how you calculate it. So let's say we start with this phi of u being the L1 norm, OK? If that's the L1 norm, that's this blue curve here. When you compute the smooth version of it, or the Moreau envelope of it, you get the so-called Huber loss, which is L2 between -1 and 1 down here, and it's L1 everywhere else. And then if you take the gradient of that, and x minus sigma squared times the gradient of that, you get precisely what is known as soft thresholding, which is something hopefully you're all familiar with from the context of classical denoising. All right, so this is very nice. This is for the map scenario. What about the MMSE? MMSE turns out is also very interesting. If you look at the right-hand side here, this involves computing a really nasty integral. So you have to have pu given x. And then this is a very high dimension. Like, if u is an n by n image, then this is an n squared dimensional integral you have to compute. And it's very nasty. It's very, very difficult to do. But it turns out there's a trick that avoids having to compute this integral. And that is something called Tweedy's formula. It turns out this is something that's been known since the 50s. It shows you that this integral can be computed precisely as x plus sigma squared gradient of p of x divided by p of x. Now note that p of x is simply the marginal distribution of x, which is the noisy image. What this means is that the right-hand side here depends only on the noisy image that you're given. You don't actually need to know explicitly P of U anymore. So this is beautiful because it says that you can empirically approximate this right-hand side and get away with building denoisers that are close to MMSE optimal, but only use the given noisy image in kind of unsupervised way. And so let me take this and try to write this using a set of equations that are similar to what I have before. And I'm deriving to a point here. So if I take this gradient of P divided by P, I can write that as log of P of X. Gradient is still there. And then if I call the negative log of P of X as phi sigma of X tilde to distinguish it from the phi sigma that we had before, then phi sigma tilde is simply also a smooth version of P, except that it's smooth in a very standard way now. It's just blurred, right? So basically, you take the prior and you blur it, and this is what you get. So remember, adding noise to a distribution blurs adding noise to data blurs the distribution of the data, and that's exactly what this is saying. All right, so here's an example for, again, the L1, starting with L1. So blue here is the L1 loss. And then if you compute the smooth version of this, this is no longer the Huber loss. It's something similar to it. It looks like this red curve. And if you compute this MMSE, which is I've written as X minus sigma squared gradient of phi sigma tilde, this is what I call, I've given it this name called smooth thresholding. Maybe others have as well. Anyway, not the same as the previous case, map case, but looks kind of like it. Right? It doesn't have this 0-watt zone in the middle. All right, so the summary of the denoising operators. Let's talk a little bit about this. So remember, the pseudo-linear was x, wx times x, which I can also write as x minus L of x. L is just identity minus w. So it has this Laplacian formulation. The map estimate, x minus sigma squared gradient of Moreau smooth phi. And the mean squared error is x minus sigma squared gradient of the blurred log minus log blurred prior. So the bottom line is that the general form of all these denoisers is pretty much exactly the same. It's x minus something function of x. And in fact, you can think of these all as a perturbation of identity. So in the ideal case, if noise is gone, right, the denoiser ought to behave like an identity operator. So you can see, for example, in this case, if sigma squared is 0, you just get x back. Most of the denoisers that we design by hand fall into the pseudo-linear category, and that doesn't exactly work, right? Because we don't try to satisfy these general conditions that that are required of a denoiser. These are more empirically designed, right? So these are approximations to these other map and MSE. So they don't exactly satisfy these conditions, but you can still think of them as very close approximations. You can think of them as shrinkage operators. They take x and take something away from it. Gradient step on some energy function. Again, this looks like an energy function. I will show you a little bit more in a moment. Okay, and then so let's go to this energy function formulation. I think hopefully this will pull it all together. So remember, I just told you that the denoiser can be written as f of x equals x minus some vector field, right? X minus some v of x. And this v of x, in the most desirable case, was the gradient of some scalar energy function, right? And the energy function was given by those smooth losses in the other cases where you had Bayesian interpretations. But I can very generally think of v of x as a gradient of some other energy function, and I can make this energy function even trainable, right? I can be fairly arbitrary about it so long as it has the right desirable properties. And if I do that, this f of x, I can write it as the gradient of 1/2 norm of x squared minus e of x. This is, if you just carry out this derivative, you'll just get exactly what's up here. So nothing mysterious. This is, if e is a convex function, then this difference is actually a difference of two convex functions. So there's all kinds of nice, interesting mathematical properties as well. All right, but a useful side effect of defining your denoisers in this way, using the energy function, is that it is a conservative vector field. The denoiser is a conservative vector field. It turns out that the gradient of any scalar field is a conservative vector field. Okay, so that's a useful and very nice property. And also the gradient of f of x is symmetric. And that's again by design, because this is the gradient of an energy function. These are, of course, naturally true for the map and MMSE estimate, but I'm showing that it is much more generally true if E is simply an energy function that you would like to design from scratch. All right, I want to elucidate a relationship that exists here between the denoising functions that we've talked about, and in particular the residual, and a concept in machine learning that has been very popular. Well, it sort of comes from statistics, really, but it's been very popular in machine learning, called score matching. Where does that come from? Well, let me rewrite this f of x equals x minus gradient of energy function. And let's look at it specifically for the MMSE case. So remember, we could write this as x plus sigma squared gradient of log px, or x minus sigma squared gradient of phi sigma tilde. All right, now let me just rewrite this equation a little bit differently. So if E is in fact an energy function that describes somehow the manifold of images in a proper way. So, you know, in a way, we thought about P as the prior, as remember, P of U was a prior that described the distribution of clean images. P of X is a distribution of noisy images. But remember, because we've simply blurred the distribution, P of X is just a blurry version of that P of U prior. Now, if I were to rewrite this with this right-hand side, what it shows you is that if E is a good description of images, then the tangent to this space is in fact just the residuals. And that's really interesting. And what it establishes is that the local geometry of the manifold, if E of x captures the geometry of the manifold, then the residual captures the local geometry of the manifold near x. It's basically the tangent space, right? And this is precisely what people call the score function. And this is the residual of the denoiser is what they use as a score matching function. Okay, so again, to summarize here, good denoisers learn local geometry of the manifold, and good denoisers can allow us to sample from or project onto this manifold. A very useful case here is the denoising diffusion models, which effectively allow you to project onto the manifold of images using denoising. So the forward direction, what you do is you start with an image and you slowly add noise to it until it's all noise. And remember, if you do this, what you're doing is you're taking the distribution of x and you're slowly blurring it. And the reverse direction, basically, you have these steps that slowly de-blur the distribution. And that turns out to involve the gradient of the log P of x. And this is pretty much exactly what I showed you in the last slide, if you recall. It's basically this term here. Okay, and so this score function, we can get that by simply computing the residual of the denoiser that takes you in this opposite direction. And there have been many, many works here, one of which is something that we did recently, where we didn't want to start with pure noise and go to an image. We wanted to start with an image that isn't perfect, so like blurry, and then go to a reconstructed image. And so we actually built a system that decouples a diffusion model into a conditional one that's conditioned on this input image. And it has a deterministic initial predictor, which is just, it could be some standard deblurring algorithm. And then it's got a stochastic component that predicts not the image itself, but the residual. And then we combine these two pieces together to get a sample reconstruction. This is very useful. It has significant improvement in perceptual quality, very efficient sampling, and flexible perception distortion trade-off. This is being presented in CVPR as we speak. And finally, I want to close in the last couple of minutes with denoisers as regularizers. Now, in our community, in the imaging community, two major works have developed in this direction. One is the plug-and-play prior, plug-and-play model for reconstruction that uses ADMM to minimize a loss like this. And then it replaces one step in the ADMM, which looks like a proximal denoiser, with an arbitrary denoiser. Then you're no longer optimizing this loss function, but it turns out it doesn't matter. It still works. The other approach, very much inspired by the first, was what we did in 2017, which is we started with the Laplacian regularizer and we generalized it to arbitrary denoisers under certain conditions. And here's the thing. So this is the Laplacian denoiser where L of x is data dependent. This is very difficult to work with directly, but many people had tried, including myself and colleagues of ours over the years. But what we did instead was we said, okay, let's take this approach here and just take W of x and replace it with a very general denoiser. It turns out sometimes when you generalize a problem, the solution becomes easier. And that's kind of what we noticed, is that if you replace this W of x with an f of x, it's more general, but has certain properties, then under the right regularity conditions, like Jacobian symmetry and homogeneity and so on, then this term is actually very easy to differentiate. And it turns out with the right conditions, the residual is in fact the gradient of this regularization function. And this was in our 2017 paper. So just to quickly finish this, I can show you an inverse problem being solved using this approach. Here's a linear inverse problem. This term here, let's say h could be a blur. With the right f, as long as f is contractive, it turns out this component here, this regularization is also convex. So the whole thing becomes convex, and you can leverage powerful optimization algorithms. So here's one. This is not super powerful, but it really illustrates the point. It's just a very simple fixed point iteration. I can write xk plus 1 as a bias vector. This is fixed. It doesn't change with iteration. This is a fixed matrix. Again, doesn't change. And then this is just f applied to the image in the kth iteration. I can redefine this f of xk as zk. And then it turns out I can write the whole thing as zk plus 1 equals f m zk plus b. So you apply a linear function m to z, you add a bias, you apply a denoiser, and that's your iteration. So you have this very simple affine operator followed by denoiser, affine operator followed by denoiser. And this is very similar, by the way, to what is done in the denoising diffusion processes as well. So these are all really connected at a very fundamental level. Some examples. Here's a deblurring example. This is red with a median filter, just to close the loop with what I promised you earlier. And I think I'm pretty much at time. So let me conclude by simply saying that denoisers, I think of denoisers as fundamental building blocks for many, many different things. It's sort of like, if you got your education in signal processing and electrical engineering, you would think of things like the Fourier transform as being really fundamental. So I would claim that denoising is as fundamental to imaging and perhaps the solution of inverse problems, and maybe even to machine learning, as FFT is to signal processing. They are very specific. They have very specific form. They are stable perturbations of identity. You can solve many problems with them. And finally, as I mentioned, having a good denoiser means that you have some nice insight into the nature of images. But exactly what form that insight takes is still being worked out in the literature. As you know, there are many, many works that use denoisers to do machine learning. So I think that's kind of getting us closer and closer to understanding how denoisers reveal the nature of images. And with that, I will stop. I'm going to share with you the slides as well. They have some relevant links to papers and so on and so forth. And with that, let me stop and allow for some questions. Thank you.
Thanks a lot for the detailed presentation. Yeah, I guess that this topic is especially interesting when we're talking about mobile devices, because as we know, noise is something that hurts a lot. And there are still lots of things to improve here. Right. Yeah, are there any questions in the chat?
Okay, I could ask a question. So, Peyman, as usual, a very nice talk, very nice introduction. Could you please elaborate a little bit? How important is the noise type assumption? Mm-hmm. So most of the techniques are starting from the Gaussian noise assumption, and are ending having a very nice and powerful tool, okay, but not always works in practice, right?
Yeah, you're absolutely right. So the reason why all of this stuff is described in terms of Gaussian noise is because we know a lot about its properties. We know how to develop optimal denoisers for it, and so on and so forth. But really, the fundamental ideas here about using denoisers to build various structures is not really tied to Gaussian noise. Like if you look at that basic decomposition that I showed you earlier, that's just a general functional decomposition. It doesn't require you to be dealing with Gaussian noise or anything of the sort. And furthermore, then when you talk about maximum a posteriori, map, and so on and so forth, we know pretty much what the Gaussian version of those things will look like. For employing things like empirical processes, that Tweedy's formula that I said, that version of it anyway is for Gaussian noise, right? So we know a lot about that. But it turns out there are versions of all of these results for other noise distributions as well. It isn't clear to me if they exist for every noise distribution, but certainly I know for many other noise distributions, also, for example, Tweedy's holds. So you can do empirical estimation on other kinds of noise as well. The other relevant bit to mention here is that many of these models, especially the machine learning models, may be for building generative models for natural images, right? So it may make sense to use one kind of noise distribution. But if you're working exclusively in the domain of, let's say, biological images, or if you're looking at, medical images and so on and so forth, it may be worthwhile looking at denoisers as your building blocks that are trained with different kinds of noise for that particular application. So I think your point is, your question is a very good one, and it's an important point that I'm showing kind of just a slice of the theory and the ideas for Gaussian noise, but it's not limited to that.
Okay, and now let's narrow down and come to some camera sensors and the typical camera sensor noises. Okay, so what will be like the recommendation?
Yeah, that's interesting. I mean, again, it depends on the light levels, right? So in good light, you can make assumptions that things are Gaussian and you'll be fine. In low light, you have to make different distributional assumptions, and maybe just don't make any specific assumptions. Just use training data to encode a denoiser. So there's a lot of different ways to deal with that. Yeah, I mean, it's a valid point, and you may have a variety of different. You might have sensors with different full width capacity. You might have larger pixels, smaller pixels. So, I mean, it's not one size fits all, right?
But definitely, from your previous talks and so on, it's better to do the denoising directly in the raw readings, right?
Yeah, absolutely. I mean, that's always true. You either have to work directly in the raw data, or you have to have a really good simulator for the entire ISP, so that the noise that you're working on in the given image is modeled in a sort of appropriate way. By the way, I like that you asked that question, because a lot of this is completely lost on the machine vision community, right? I mean, you take an image and all the trouble that we've gone into to produce that image, and the noise that is contained in that is often kind of a side story. But I think now with the people are beginning to realize how important noise is and how important denoising is, and I think it's bringing imaging kind of to the forefront of importance for computer vision as well, because we build this building block, right? So, and they can use it for machine learning. So it's great that this thing has happened.
Okay, so those were my questions. Thank you very much. Andrey, are there some other questions?
Yeah, I guess there are no other questions.
I have, hello, hi. I'm Harsha. I'm from Dolby. I work on video denoising related tasks. I'm going through literature. My question is more about adding on to what previous questions were. For example, if I consider a video and then if there is a noise in it, that noise is not a static noise, right? It's more like a temporal noise where every frame is associated to next frame's noise, kind of. When we go through literature, it's more about giving this noise as a Gaussian noise, and then more like in a supervised learning pattern, they learn that, right? But in real time, when you see videos and their noise is not essentially a Gaussian noise in terms of temporal thing. So is there any way we can model that noise?
Yeah, I mean, if you're talking about capturing a burst of images, essentially a video at the sensor level, then you have a sequence of raw frames, right? There you can make some independence assumptions, but once you have that encoded into a video, if you're talking about the video once it's gone through the encoding process, then of course the noise is completely different, and it's been correlated both across space and across time. And then, as I was just saying, with respect to the single image scenario, you need a model of the entire process. You need to know how the pixels that were captured at the sensor were modified and then encoded and so on and so forth. So yes, you can get a model. It's just a really, really complicated model. It's usually very difficult to get a very good analytical model, but it's probably more tractable to kind of get a learned model, right? So let's say I give you an image and you're able to produce a map of that image to show me how strong the noise is at each point, right? I think things like that you can do.
But in a universal level, there is no such way to model. Let's say you have a video, you can't just model the noise, right? I mean, as far as I've seen.
No, there's no single distribution I think you could assign to a video. No. So if you're chasing for a specific distribution, I would say that's not, you're not going to find it.
Thanks, Raymond. This is a wonderful talk. Thank you.
Thank you.
Oh, hey, Professor. And first, I think very impressive in presentation. I do have a question about the linear model you just mentioned that you just use the Laplace layers. And can I just understand, because I use the guided filter a lot. Sometimes I just review your, just after listening to your presentation, it seems like there's some, the equation formula you guys share the same strategies, try to find the minimal energy functions to do that one. And also I found that there is a guided map there, which can I just treat you actually use the Laplace layers as the guided map to, to process in this denoising and kind of share the same strategy there, but a different, guided map there.
Yeah, so I would say that there's a difference between what I described. I assume you're referring to this general formulation here I was talking about, right? I think you can still see the screen, right? No?
Yeah, kind of. Yeah. This one, well, anyway, yeah. Go ahead.
Yeah. So I would say that this may be indirectly related to guided filtering, but it is much more directly related to residual networks, right? So the reason why residual networks are built the way they are, you have the skip connection, is that it's so that the network can actually learn the identity map, right? Okay. Without that skip connection, the network will not learn the identity map. And that's exactly the same thing here, in the sense that this X that you're building by decomposing these different pieces, it's by design allowing you for some set of coefficients, alpha and beta, it is allowing you to just get the image X back, right?
Yes.
So what it does is it forces you to stay relatively close in some sort of bound around X. So you're not just generating random images, you're generating images that are very closely related to X in this very specific parametric sense, right? And so I think in that sense, it's much more, if you're looking to analyze kind of the relationship between what I said and some of the things that you've seen before, I'm not sure it would be easy to establish a relationship with a guided filter, but I would start looking at it more as a residual network and see how you can make those connections.
Okay, yes, because I treat this one as something like if the residual net, what I understand is it seems to me sometimes because we do the trainings there, we do the multiple scale there, multiple scale features there. It sounds like we did a multiple scales of guided map there, because guided map also want to have the features there instead to just return equally to training this model, try to learn the multiple scales of the features there.
Yeah,
can I understand this way?
Yeah, the other thing that's important to remember is that, yes, this is multiple scales, but it doesn't involve any decimation, right? So in typical multi-scale settings, you filter and downsample. So as you go coarser, you have fewer pixels. Here, the number of pixels is exactly the same, right? So there's no upsampling, downsampling. So that's one major difference.
Okay, Aki. Thank you, Professor.
My pleasure. I'm gonna, in the chat, I'm also going to share with you the link to my talk, and let me just make sure you all get it. Okay, hold on. There. Any other questions?
Okay, if there are no questions, then thanks a lot for the talk. I see that lots of guys open this link and would be checking the slides now. Okay, and
so please don't let me distract you with this, and pay attention to the next talk.
Okay, good. So we are now slightly changing our schedule, and we'll have now a presentation from Huawei talking about benchmarking, about testing, about testing AI servers. Hi, Tsao. I guess you can unmute yourself. Okay, yeah, good. We can now hear you.
Hello, can you see my screen?
Yes, we can see your screen.
Okay, hello everyone. Good evening, good day. So this is the talk about the performance test of AI server systems. So as we know, the AI computing infrastructure has developed for several years. So because the tensor-oriented computation drives specific design for the acceleration. So the AI computing infrastructure can be to some extent, which is different from the one for the generic computing. So the computing infrastructures in this kind can be interconnected as clusters, or even HPC infrastructures providing more computation ability. So it is needed to ensure proper monitoring of the performance of an AI system throughout their lifetime. So there are some typical AI computing infrastructure instance. For example, you can have some AI accelerating modular, and also you can have a AI edge server, AI edge station, inference server, and also the card, and also the training card, and also the training server. From the other part, and you will have some port or even cluster conformed by AI servers. Different kinds of AI computing infrastructure can provide different computing ability for different kinds of scenarios. So based on this, so because we are discussing the performance test of AI server systems, so we name the AI server system as a joint name of AI computing infrastructure, including AI server cluster, high performance computing systems. So in a standard, we specify an AI server as a server with specified design and implementation that provides computing abilities for AI applications in an information system. So different kinds of server can be used here. So the server for the generic computing supports AI computing by AI acceleration, instruction set, or acceleration circuit, or acceleration modular. This kind of server is a typical of AI server. It's a type of AI server. Different kinds of AI server can be grouped and connect as an AI server cluster, which is regarded from the external as one server to jointly provide dedicated processing, capabilities for artificial intelligence applications in an information system. So if you have a task which needs a lot of computation resources, you can even compute it within a high-performance computing system. According to the definition from the ISO IEC standard, the computing system which is designed, stored, and optimized to execute high parallel applications. So inside the HPC system, so computing devices such as GPUs, NPUs, and others are used in HPC system for achieving high processability, specifically for those tasks needs large-scale parallel computing. So when an HPC system contains accelerating processors and is built for the purpose of processing AI tasks such as training, machine learning models, or inference, it is called an AI HPC. So this is the definition specified by a standard. There are issues related to AI server systems performance test. So, for example, the multiple factors can influence the performance of an AI server system. For example, the connection between services, connection between accelerating modulars, and the topology between them, bandwidth and configuration, and of course, task distribution, manner of use, and extra. So the question, how to test the actual computation ability of them remains. In the sense that for now, there are two issues actually, at least. Lack of more complete and appreciated metrics for AI server systems. The second is lack of guidance of text technology, which helps the elaborate design of test processes, helps to get more precise results, targeting on finding system bottlenecks and drawbacks. For example, the exact power consumption by AI computation rather than by system maintenance or other jobs. So here is an abstraction of the process to be tested. The first one is an example of training. So here, if you split the example of training into several phases, then you will have different kinds of view in order to test very insight to the overall training process. And also it holds for the inference. For example, you have a job distributed onto your cluster, then different machines or different worker nodes can be used inside this cluster. So if you separate the time for the whole training inference task, then you have a detailed vision on this. So if we are discussing AI server system performance, then we should define it. So the performance is measurable results. So it can be related to quantitative findings and also can be measured or computed based on one or more defined metrics. So they are critical or required by users. So from a standardization view, so it is defined by some ISO IEC standards. So as we know that the different kinds of measures can be used to represent the performance of an AI server system. So we group them into three subgroups. The first is duration related. For example, the E2E training or inference latencies, and the durations of stages during training or inference, because we have just divided a whole training or whole inference process into sub-stages. Yeah. So the second kind of measures is task related. So the first is throughput and we always call it effective computing ability. It measures that how many jobs can be processed in a unit of time. So the second task-related measure is combined effective computing ability. So it is a kind of combination of throughput. So the third kind of measure here is the energy related. For example, the isolated power consumption of training or inference processes, or the training inference power consumption, and also the E2E training or inference power consumption. So actually, there are a lot of performance measures regarding to different types or kinds of AI server systems. Yeah. So here, actually, we have joined in an IEEE standard for the performance benchmarking for AI server systems. So there are many organizations also attend in this standardization process. For example, Intel, NVIDIA, and also some other Chinese companies, for example, Inspur, Lenovo, and also Huawei, Tencent, SenseTime, and the other ones. So we have spent nearly 1 year for the standardization on the performance test of AI server systems. So we had a preliminary outcome, a standard that, and it is associated toolkit, focusing on the performance test of core infrastructures for AI computing. So it's providing evidences to AI computing system optimization with test technology-based measures and methods. And also it provides approaches for the performance test with domain-specific data and applications as well as test planning. So here, and we show the table that has been or is enabled, that is being enabled by this test standard. So we have different workloads for the image classification, natural language processing, and the other scenarios. And also we have some other things which is going to do, for example, the super big data set test and the test with super heavy computation and also super high dimensional input and output. So this super thing is almost from the needs from the large scale model training and inference. So in the aspect of metrics, so the E2E duration, power, and the throughput are enabled by the test system. And also we have some combination computation balancing, duration of learning or inference stages, bandwidth throughput, and the others and the other metrics are enabled. So this standard has been reviewed by the RESCOM of IEEE Standardization Association at this time. So there also has exist some hard questions of performance test. For example, how to isolate performance against the AI workloads out of an overall performance measured on an entire AI server system. So it is hard because different processes execute different kinds of tasks. If you would like to just measure one task, for example, the performance, or for example, the power consumption of one kind of task running your computer or server, that is very hard. It is not easy. So the other one is how to apply the artificial intelligence for the test of AI systems, realizing an automated test with adaptive test strategies on the system performance bottleneck discovery, and as well as AI-based performance optimization strategy generation. So the third question is how to guarantee the test accuracy on uncertain system with workloads at non-deterministic exponential complexity. Yeah. So we had discussed with the experts from NVIDIA and Intel and the other companies about the test in real practice for the first question. So actually, we use power meters for the cluster, and we had a preliminary outcome about this. So if we discuss about the question 1, it is a trial for isolating the performance against an AI task out of the overall performance of an AI server system. So as we know, it is hard to isolate the performance of an AI server system against the specific AI workload. It is hard because the server can simultaneously execute the other jobs, and performance of all the jobs affect each other. When it is executed on NPU or GPU, CPU can join for scheduling and scalar computation. So if you know how the computation are processed in an AI server system, so because there are many kinds of data types, for those data types, you have to choose different kinds of processors in order to have some acceleration. So for the tensor or matrix computation, so different kinds of accelerator, for example, NPU or GPU can be used because it is a little bit faster. So CPU can join as a scheduler. So because if you apply the pipeline stream in your server system, then the CPU should prepare the waves. Yeah. And of course, CPU can be used for the scalar computation. So if we are performing a task should consider the formation of AI processing components. If we would like to isolate the performance of an AI server system against a specific AI workload. So if a coprocessor is set on a card or within a SoC, the question is relatively easy to be resolved. Yeah, because they are used together. For example, in a accelerating card, if there exists a coprocessor on that, it means that the coprocessor will take the responsibility for the scheduling and the scalar computation. If we would like to isolate the power consumption of that card, it is relatively easy. If the main CPU are used for the purpose above, then the counting on its utilization is important. So we propose the following approach. And the first is record to base power consumption by power meters with a period of idle. It means that the noise of power consumption in a idle time. So the second is when processing an AI task, sample the utilization ratio of CPU for the task process and compute. Then record the total power consumption by power meters for the duration of AI task execution. So the last, then we can compute an approximated power consumption against that AI task. So it means that based on the utilization ratio of the CPU, whether it is working for the scheduling or scalar computation, or it is used by the other process, for example, the maintenance process of the whole system. So we just count it. Based on this, we can to some extent isolate the performance, for example, the power against an AI task out of the overall performance of an AI server system. So this is the investigation on the question 1. For the other questions we had encountered in the standardization process, and we had continuously discussion about and try to resolve them. Yes. So this is the talk from my side. Thank you very much.
Thanks a lot for this talk. Yeah, I guess that you covered many important topics related to benchmarking, and these topics are not necessarily just related to server benchmarking, but to benchmarking other hardware. So are there any questions? Yeah, I don't. Okay. Yeah. So I see no questions in the chat. So then, thanks a lot for a very nice talk. And we're moving to our next speaker from OPPO, who will present a work called Clip for Hashing and Supervised Deep Hashing for Cross-Modal Video Text Retrieval. You can, okay, we can see you. We cannot hear you yet. Okay.
Can you hear me?
Yes, we can hear you.
Oh,
can
you see me now?
Yes.
Okay, cool.
Yes.
So thanks, Andrew, for your introduction. And hello, everyone. So my name is Yikang Li, and I'm a senior research engineer from OPPO US Research Center. Today, I'm glad that I can have this opportunity to present some work about a compact binary feature learning for the video text retrieval task. So we call it clip for hashing, since this work is done by mainly focusing on the well-defined clip model as our continuous feature representations. And in this presentation, I will briefly introduce what we are doing right now and what different techniques we used for making our algorithm more suitable for mobile devices. Okay, let's start. So as we know that, thanks to the boom of the different kinds of social media, so millions of visual data like images and videos are uploaded, downloaded, or streaming by using mobile devices every day. And people are getting more obsessed with those kind of visual data since it can bring more intuitive perception for people to know about the world around us. And from some surveys, we even can know that nowadays, more than half of the data used in social media are visual data. However, here comes the problem. So these visual data are really costly and hard for our mobile devices to store and retrieve. So let's take some simple examples here. So if one phone taken photo takes about 2.5 megabytes, then if we want to store about 100,000 images on our mobile device, it may require about 250 gigabits. And the video data is more costly, since a 1 minute video clip that is taken by the mobile device will usually take about 70 megabytes, and therefore it needs more. It needs more about like 70 gigabits for storing only 1,000 videos. Due to this kind of storage issue, users would do the data organization frequently, like daily or weekly, which is really annoying. And the users like us want to find the target items among this kind of huge data quickly, which is also a challenge in our current mobile devices. So what's the worst? The current common search system is based on the labels that we need to define them all in advance. Here I show an example using my own iPhone. When I search with a keyword like a kid, it will pop up the photos that I took from my son. However, if I search with keyword like little boy, it shows nothing here, since the little boy is not in the label vocabulary. Even not mentioned that we want to search with a semantic sentence like a little baby playing in the garden, something like this. And besides that, the label-based search engine cannot provide the most relative items to the user by ranking, so which will usually lower the user experience. Therefore, so a good pre-trained cross-modality model is necessary for this kind of issue or problem. Currently, a good pre-trained vision language model can cover many downstream tasks like image or video retrieval and classification and segmentation and so on. And the figure here, I set it from the original CLIP model website, shows that the performance of the CLIP model on 27 different datasets. And we can see that almost all of them perform with more than 70% accuracy on those datasets. That is really amazing and powerful. However, as we also show here, usually the model size of this kind of pre-trained vision language model takes about 300 to 400 megabytes, which is really huge for mobile device. And even if we want to extract the features to store on the mobile device, it also takes some space. For example, let's do some simple mathematics here. If we want to store 100,000 CLIP features, it can cost about 200 megabytes. So researchers developed methods to make it happen or possible to deploy models or store features in mobile devices. There are mainly two directions: the model quantization and feature quantization. The model quantization aims to reduce the model to a mobile device friendly size with a variable performance loss. And the feature quantization is what our current work focuses on, and it reduces the feature storage size. Well, it also can maintain the semantic meaning of the original features. And learning the compact binary feature is one branch of this kind of feature quantization, and we believe it as important as the model quantization. And one more thing here to note is that feature quantization not only benefits the storage of the visual data, but also the searching speed, since it uses the homing distance to find the best matching atoms. Okay, so let's start the algorithm part. Here is the flowchart of our CLIP for hashing algorithm. So in simple terms, we extract the features by using the well-trained CLIP model for both visual and textual data, and train our model with the similarity matrix guidance. The whole training process is similar to the most deep hashing method. And for the video data, we use the mean average pooling along the frame feature sequences to obtain one feature representation for the entire video. And the hashnet here is to project the continuous feature into a subspace that is optimal for quantization. And the goal of this training procedure is to maintain the continuous semantic meaning of the visual textual pair data in the homing space. And to my opinion, what makes our algorithm different is those three aspects I listed here. So first one is that we use a single hashnet for our algorithm, which is possible since we use the pre-trained cross-modality model. This kind of cross-modality model will project both visual and textual features into the same common space. And secondly, the dynamic weighting method we use to reweight the similarity matrix to obtain a better similarity guidance for our whole algorithm. And the last one is that we define a new quantization layer here called min-max quantization layer, which is more suitable for the pre-trained vision language model. Okay, let's have some details here. So since the single hashnet is straightforward to understand as we use a pre-trained vision language model, we mainly introduce the dynamic weighting and the min-max quantization layer. For the dynamic weighting, it mainly takes 3 steps. First, we form the similarity matrix by using the visual to textual and the textual to visual similarity as shown in the equation number 1. Then we set the diagonal of the formed similarity matrix, which here we call it S sub C to 1. This procedure is intuitive since all the paired data should be the same as each other. And we know that the similarity value of the paired data locates along the diagonal of the similarity matrix. That's why we set the diagonal to 1. And the last one is we tune the similarity matrix by using new weights, which are computed by the exponential of the normalized distance between the atom or the value and the bound. The bound here, I mean the minimum or the maximum value within each batch. And actually the weights equation number 3 here will make the similarity value for each data pair more distinct in the similarity guidance matrix. And for the min-max quantization layer, we think it is simple but effective. The quantization happens along each dimension within one batch. If the distance between the value itself to the maximum value along the same dimension is less or equal to the distance between the value and the minimum value along the same dimension, we will quantize this value to 1. Otherwise, the value is quantized to -1. Here, I also show an example to help us better to understand the min-max quantization layer more clear and better. We compare our min-max quantization layer with the other 2 most commonly used quantization layer here, the sum function and the by-half layer. The sum function is really straightforward since it will quantize the value by setting the threshold to 0, which will set the value to 1 if the value is larger than 0 or to -1 otherwise. And the by-half quantization layer here is designed for maximizing the bit entropy along each dimension. And it will force half of the value equal to 1 and the remaining half equals to -1. So from the figure, we can see that the ABC 3 features show some similarity or relationship in the continuous space. And we can find that the sum function will lose the semantic relationship dramatically since except the A feature, all the other features are quantized as the same binary code in Hamming space. The by-half layer will make all the ABC features the same in the Hamming space, which is also not optimal. But our min-max layer make the C a little bit different from A and B. We believe this is essential since compared A and B in the continuous space, the C is indeed a little bit far, but not so far from A and B. Therefore, the C is only one value difference in the Hamming space. It also shows that our min-max quantization layer is more suitable to maintain the semantic meaning in the original space. We also did some experiment on some public data set, and all results are better than the baseline method. Here, we show the R at 1 metric performance on MSR VTT dataset. The y-axis is the average value for recall at 1, and the x-axis represents the byte size for only one feature. We can see that our algorithm outperforms other hashing-based methods a lot for different bit settings. Those baseline hashing methods here are those triangle ones in the feature in this figure. And our method can even beat the methods in the continuous space with larger bit coding, like the 2048-bit coding. We can find this baseline in the continuous space are represented with circle here. And we can even have a similar performance with the original clip zero-shot learning on MSR VTT dataset, but our feature requires 16 times less storage space than the original clip features. And we also compared our compact binary feature with original features in efficiency settings. If we want to store 1 million visual data, the original features takes about 2 gigabytes, while the battery code only requires about 64 megabytes. Besides that, the searching speed for the original feature is about 172 seconds within this 1 million data, but the battery code only takes less than 1 second to find the best match. Therefore, in a conclusion, I think our clip for hashing method is efficient in both storage and speed for this kind of search and retrieval task. In the meantime, we can still maintain the performance in the well-defined semantic space. Okay, here I also show an example running in our demo machine. I'm not sure whether you can see clearly, but I will explain it. If we search with keyword dog, it will pop out some video clips that contain dogs randomly. And if we search with keyword happy smiling dog, it will rank the most relative video clips on the top and provide them to the users. We can see that all the video clips on the top showing here, right? Showing the dogs opening their mouths and looking like smiling at the camera. So this also shows that our binary code-based searching also works for the semantic retrieval task. Okay, I think that is all about my introduction to our work. Thank you very much for your watching and listening. I will give it back to Andrey. Thanks.
Thanks a lot for the talk. Are there any questions in the chat? Okay, I don't see questions. Okay, this means that everyone understood everything. So
thank you.
Yeah, thanks a lot for the talk, for the presentation. Yes, and then we are moving to our next speaker, who will present a work on on a fast image super resolution for mobile gaming upscaling. The speaker is from Samsung, and I think he will present directly from our CVPR room, right? Mm-hmm. We can't hear you. No sound. So you are unmuted, but there is no sound for some reason. Okay, I think that we can now then go for another talk. We had a request from one of the participants to present it a bit earlier. So, 1 second. Now we'll have a presentation of the paper Updated Compression for Deep Neural Networks on the Edge.
Okay.
Mm-hmm.
It's going to be right. Yeah. And probably this one. Oh, this PowerPoint.
Mm-hmm.
Did you Touch something here, or this is from?
I didn't touch.
Okay, and who is?
Someone is sharing.
Yeah, it's me. I'm Tan Jun Chin. May I start now? Can you all hear me?
Can you?
Yeah. Yes, we can hear you.
Thank you.
They cannot hear us. Wait 1 second.
I can hear you.
Yeah, the sound is very. It's not loud at all.
This should be better.
Can you hear us, Andrey?
Yes. Right now.
Okay.
Okay.
Yeah,
sorry for that. Yeah, I think you can hear me now. Yeah.
Yes. Everything's good.
No, that's someone.
Wait.
Thanks for allowing me to start early. Thanks for having me. So as Andrey mentioned earlier, as you can see the title, Update Compression for Deep Neural Networks on the Edge. So first, some acknowledgements. The main bulk of the work was done by Bo Chen and Ali Bakshi, and also acknowledge our sponsors, SmartSet, CRC. Okay, so here's the motivation for our work. We have the usual server edge device setup, where on the server, we have data for the training and model refinement, optimization, and refinement. And then inference is done on the edge. So it's assuming here that on the edge, there is some device that's capable of performing inference using neural networks. So I'd like to emphasize again that our setting, maybe not the same as everyone's setting. So it's worthwhile to emphasize. We have the data on the server, the labeled data on the server, where we can do training and refinement. Okay, and the edge device is mainly for inference. Okay, so once deployed on the edge device, there is a need to continually updating the model on the edge device. Okay, because there's covariate shift, or you have more data for the same task, or even you want to completely change the task on the edge device. Okay, so the constraint is once we send the edge device, or once we deploy the edge device, we may lose physical contact with the server. Okay, so settings like this, for example, we encounter in IoT type applications where the edge device is deployed in the field, and it could move around maybe on a mobile robot, and afterwards it's quite difficult to physically pair the edge device and the server. All right, and also we consider the case where there's a communication bottleneck, and that bottleneck, the communication bottleneck, serves as the main motivation for our work here. One observation as we were doing this work is that we think edge devices are actually edge compute devices, to be more precise, is getting more and more capable, right? So every year, maybe not every year, but quite often you see companies like NVIDIA coming up with more and more powerful edge compute devices. So, inferencing on edge devices is becoming less of a problem, but of course, model complexity keeps growing. So maybe it's not completely solved by that. But on the other hand, we think that communication bottleneck is always going to be, maybe always is too strong, but it will likely remain a bottleneck, right? And even if, we have 5G, 6G, whatever, if we can get away with transmitting as little as possible, to save power, to save cost, it is still worthwhile to compress the update that we send from the server to the edge device. And by update here, we mean update the machine learning model. So to put what I've just said in vague hand-wavy words into more system, more framework. So this is concept of operation diagrams. First, we separate the pre-deployment and the post-deployment phase, whereby in the pre-deployment on the server side, again, as I said, we have the data set D1 here, we train a model. And you can compress the model. I'm sorry I attended this workshop late, but it's 7 a.m. here in Australia. We can compress the model, and I'm sure that earlier in this workshop, you've heard several talks on how to compress models, how to inference them more efficiently. And in our setting, no problems. We assume that we can compress the model, we load them onto the edge device, and we deploy it. So post-deployment, we have new dataset D2. And for simplicity, we assume that D2 is a superset of D1. So D1 basically grows larger to become D2. And we can refine the model on the server, and we could refine actually the compressed model C1. The question is, how do you update the copy of C1 currently on the edge device? So the naive way would be just override C1 and transfer all the parameters that change in the model to the edge. All right. If communication is not a problem, then no issues here. Can you hear me? Can someone confirm him?
Yes,
we can hear.
Yes. I
Okay.
think maybe yes, there are some problems with the internet connection on site.
Okay, cool. Okay, so our proposed method is same setting. We have dataset D2, which is a superset of D1. We refine C1 in a manner that introduces small changes to the set of parameters. And then we just send the small set of parameters to the model on the edge or to the edge device. And then instead of just simply overriding, there's a bit more further computation required. Is somehow we have to reconstruct or reconstitute the model from the small set of changes sent to on the server. Okay, so we obtain a lot of inspiration from federated learning. The first method or the first few methods we tried out indeed were taken directly from the federated learning literature. So to refresh everyone's mind, in federated learning, we have a cloud and client architecture as well. The difference between the setting here and our setting is that in the federated learning, we assume that on the edge devices, we have labeled data. So after initialized with some initial common model, then each edge device will perform the model refinement individually. And then the model parameters, each of the device will transmit the model parameters back to the server for aggregation. And this happens not just one time, but multiple times across the lifetime of the algorithm. So therefore, it is crucial in federated learning to make sure that the communication bandwidth required between cloud and the server and the client is as small as possible. So taking inspiration of that, as mentioned, for our specific setting, where training is always done on the server, the data is always on the server, the obvious thing to do, which is the first thing we try, is to reparameterize the model. And I emphasize again, because we had a lot of trouble with the reviewers in the main conference, the model that we are reparameterizing and trying to, whose update we're trying to compress, can already be the compressed model. This is already edge efficient model. We reparameterize the model into a learnable and a frozen section. And the trick is only to refine the learnable part of the model. And then the frozen part of the model is also transferred to the edge device pre-deployment, okay, and never changed, all right? And then once new data is available, we refine the learnable part and only transfer the changes in the learnable part to the edge device. And on the edge side, a separate routine is conducted to combine these two. Okay. A bit more detail. We went as far as only performing the reparameterization on the convolutional and fully connected layers. All right. So for the other layers, other types of layers, we don't touch. We only reparameterize the fully convolutional, the convolutional and fully convolutional layers, fully connected layers, and specifically by rearranging the weights in these layers into a matrix, into a tensor, and then into a matrix, and then we decompose them basically using linear algebra. So we tested out several methods. My colleague came up with quite fancy names for them. Low rank approximation. Well, that's not fancy, but mapping learning and knowledge augmentation. Really, there are different ways of choosing what to freeze and what to allow changeable. So low rank approximation, as the name suggests, literally only allows a low rank version of the weight tensor to be updated. Okay, so this is taken straight from the federated learning literature. Which is therefore this is our baseline method. And in the low rank approximation, the blue portions are only retained and are allowed to be updated in the refinement process. In mapping learning, we freeze the right singular vectors. We freeze the column space basis vectors. And the column space basis vectors are shared, so between the server and edge device at the start before deployment, and they're never changed throughout the lifetime of the algorithm. Only the blue part gets updated during refinement. And then finally, the method that we found works best is actually retaining a set of basis vectors, both left and right singular basis vectors, and never change them. And then we just add additional columns, n of them, and also the corresponding singular values, and add additional columns on the right singular vectors as well, and only refine the blue part. Okay, so to recap, as a high-level summary, the yellow part in each method does not get changed; they are frozen, and they're shared between the server and edge throughout the whole lifetime of the algorithm. Only the blue part gets changed. So jumping straight to the result, I think the method is simple enough that we don't really need to dig into more equations. So you see here similar type of figures, but they're actually quite different experiments. On the left-hand side, it's a relatively large network and on a standard data set. And you can see that most methods actually perform well. So in particular, the baseline of low rank approximation, the yellow/gold color, and also RM, which is random masking. Random masking, as the name suggests, literally is deciding which of the weights to fix, which of the weights to change during the refinement, and chosen randomly. So we only need to transfer the random seed generator from the base from the server to the edge. So even random masking performed quite well. You can see that on the x-axis in each graph, it is the size of the update as a proportion of the number of parameters. You need to basically, this result show that we only need to transfer 1%, the amount of data that's equivalent to 1% of the network parameters in order to perform the update quite successfully. Accuracy on the data set D2, the larger data set, can reach up to 90% with simple methods. So the results on the left-hand side is telling us that even for ResNet 18, which isn't really the biggest model out there, there's a lot of redundancy in the network. So that shouldn't come as a surprise to anyone. On the right-hand side, we changed the setting. And this goes back to what we said earlier about the fact that the model that we're trying to update on the edge can already be a compressed model. We tried out with tiny ResNet. And you can see that you start to see differences in the method. And our best method, KA, the light blue one, you can see is pretty good, as well as ML, which is also our method. And whereas LRA and RM is less capable, and you can see differences of about 1% or more in accuracy, which tells us that if your model is already compressed and there's not a lot of redundancy, an update compression method that is more strategic will give you a bigger benefit. As usual, table with bold numbers, saying the things that I already said earlier. Similar experiments, not in a graph, but on a small model, MobileNet V2 as well. You can see that the differences in the method is big. Well, actually not this one. Well, VGG small, you can see the big difference. 2.28 accuracy lift from dataset D1 to dataset D2. And whereas random masking doesn't work quite well because it's randomly choosing the weights to freeze and refine. Whereas the bigger model, you see less of an effect in strategically compressing the update. One final experiment to highlight. What is the effect of the differences in size between D1 and D2? So on the x-axis here, you show that we show the size of D1 as a percentage of D2. So when we started the experiment, obviously we know what D2 is already. D1 is just a subset of that, and in this experiment we're changing the size of that D1 subset, and you can show that. Firstly, all methods show that if your D1 is much smaller than D2, you're going to get a bigger accuracy lift, right? That's obvious because you're adding more data for training from D1 to D2. But you can also see in our experiments that methods that try to compress the update more strategically, it actually learns better when you enlarge the data set. So that's why you see a downward curve for all methods here. But the proposed method, which is more strategic, is higher on the left-hand end of the graph. So to summarize the impact of the proposed method, on the top here, you see what we believe is the current state of the art. We have a compressed model on the edge, but when the training and refinement is done on the server, and this could be done continually, you always need to transfer what amounts to the number of parameters in the model on the edge. But what our work allows to do is that your edge device could have a large compute device already running a compressed model, but we allow even a much smaller amount of bandwidth to be consumed to perform that update. So could be that in the future maybe we just need to consider running full-size model on the edge, as long as the bandwidth that you use for updating is small. It doesn't really matter if your edge model is big or small, because devices can eventually catch up and absorb the big models. And that's the end of our talk. I'm sorry if it's under the limit or over, and happy to take questions.
Thanks a lot for the presentation. It's fine that it exceeded your time frame a little bit. That's not a problem. Are there any questions? Okay, it seems that there are no questions. Well, if there are no questions at the VPR side, then we can probably move. Okay. Second. Okay, yeah, there are no questions. Okay, thanks a lot for your talk. And we are now moving to the next presentation. So, I guess everything should be already set up at CPR. Marcos, are you here?
Just 1 second.
if we would finally get connected to CPR room, then right now will be a presentation from Samsung called RenderSR, a lightweight super resolution model for mobile gaming upscaling. By the way, and a really interesting paper with a number of interesting practical results. Okay, yeah, we can see it.
We have some echo issue.
That should work. So you can hear us, right?
Yes, yes, we can hear you.
Okay,
we can
perfect.
see you. Yes.
Is that right?
No. They see the.
Oh, you see mine.
Yeah.
See me. Oh, okay. My screen is sharing. But why they still see me?
Do you need the notes?
We saw your slides and see an outline.
Somehow. Do you see slides?
Yes.
Oh, okay. Then I think I can go ahead and present.
Yeah, sure.
Okay, but they see.
Yeah, this is slides. Okay.
Yeah, so but this is the presentation, the presenter.
That's fine. Yeah.
Okay.
That's good enough. Hello, everybody. So this is Ting Xingdong. So I'm a staff engineer in Samsung Austin Research Center. Okay. You guys can hear clearly, right? Okay.
Yes.
My topic is RenderSR, lightweight super resolution model for the mobile gaming upscaling. And today, this is my agenda. So first talk about the motivation and our model design. After that is our data set collection and the training details. Later, we present some results and give some initial performance data. Finally, some conclusion. Motivation. So the super resolution is a very hot topic and is on the mobile. It's mainly driven by the display. The number of those factor is the high refresh rate. So and now the major is the very high refresh rate. Well, your gaming may be 60, but the refresh rate is 120 or more. Well, the GPU's rendering capability is relatively low. So there is a big demand for the resolution. So on the market, there are tons of different features and selling points. And most of them are targeted for the photo data sets. And some research, and we decide to come up with our own customized model. And we named this model called RenderSR. This model is small. It's very lightweighted. It only has 4 layers. However, we purposely make it wide, make it fat instead of long, because we want to take advantage of the GPU's, because GPU is optimized for the bandwidth instead of latency. There may be other like long and skinny models, maybe variable at the same 40K width, but that's our design choice. According to some research, as long as proper training, the fat and the small, the fat one is equivalent to the long skinny one. So the first 2 layers is to convert 2D and use for the feature extraction. And the third one is a transpose convolution used to reconstruct and upscaling 2 by 2. The fourth layer is a sharpen layer and it's optional. it's a dedicated sharpen filter. It's not trainable. The sharpen filter can be between 0 to 1 and tunable by the end users. Our model is bandwidth aware. It's the hyperparameter is picked up by considering the mobile SoC bandwidth. Mobile SoC bandwidth is around only 50 gigabytes, fall behind the discrete GPU. If we give the of the RenderSR is equivalent to on the intermediate layers and bandwidth, and you can calculate the upper limit is the channel is 64, and you can go down, but you can't go high because this is just a theoretical number for the theoretical bandwidth. So this is RenderSR size and compared to other models. So you see it is on the lower end of the spectrum. The data collection and the training detail. The photo SR, the data sets is from the camera mainly, and the lower usually the LR is interpolated down from the corresponding the HR, like by cubic down. However, for our gaming one, the gaming data sets is not from by cubic, not because of interpolation, but from the actual the GPU rendering. When gamers play on their phone, what do they see? They see the actual GPU rendering results. So we don't want our model run how upscaled well, how interpolated well, but want them to learn how they render them well. So, however, to get aligned HR and LR is not easy. When you play game, you know, right? When you play on given resolutions, they have offsets. So we collect two data sets. The first one is screen. Screen is from a graphic GFX benchmark, and because this benchmark is designed for apple-to-apple comparison, and it's repeatable, predictable, configurable. There are a lot of knobs, and generally you can get the same frames with LR and HR. No anomaly, no text, very user-friendly. So finally we collect the 10K images pairs. However, if we come up to more real products, more real gaming products, this is UE4 engine product. It's called Eastern Garden. We see a lot of anomalies. So we see random birds, the flower pedaling, dropping, and the swimming fish, big extra, basically physical animation. And we have to disable these objects and the text to get corrected frames, because our model is not designed to detect them. This animation is just very random. We want to get rid of this randomness. Also, to collect to as much as the scenes, we have to insert the capture actor to adapt different scene scenario. And however, there is a big delay when you're saving the frames to disk. So that's usually some frames just skipped, especially for the HR. Finally, we package into a benchmark and run it on the executable mode on the Windows. And after pruning, we get 800 images. So this is pruning. The left one is corrupted. The right one is a good one. Some training details. The input frames are randomly cropped into 96 by 96 or 128 by 128 tiles. Our experience shows that the tile size doesn't matter, and all the tiles are augmented by operation. we first tried on the TensorFlow 1.4, and then we migrate our experiments on the 2.3. Our we use NVIDIA GPU, and it trains 8 hours, 300K steps. Mini batch is 6, and we use L1 loss function. Because the previous research shows L1 loss function has better convergence than the L2. Each data set has its own training weights. As you see, our parameter is very small, so it's only 4K. Well, if you download a game on your phone, it's multiple gigabytes. So we think that's a small overhead. And even you can like each scene in the same game can be even have different ways. Like the players like in the castle and outside the castle, that's different scenes. We 90% of data is used for training and 10% is for testing. We experiment on 3 channels, 3 kinds of channels. First is Y CBCR, and we only train on the Y. The assumption is because the Y channel is more sensitive to users. And then we experiment on 3-channel RGB. Also, we experiment on the RGB depth channel. The depth channel I'll explain later is from the GPU pipeline. Here is some results. So first is Ask Green. So this is about 1 channel or 3 channel. I don't know if the internet bandwidth is good enough. So we asked our reviewers board. They said the middle one, the RGB image is much better than the Y only one, Y only training. You can see the areas on the lights, on the shed on the stone. So because this result, later on we all switch to at least RGB training. So we are basically abandoned one training. And also our review said the RGB is very close to the ground truth result. So this is the zoom in. If you very zoom in very details, you see, okay, RGB is not still, SI still not as good as ground truth, but much better than YCBCR, the Y only training. So this is bicubic versus our RenderSR. See the leaves is the RenderSR is much better. Also the front and the bar is very smooth. Very clean, the ad. Our average PSNR is we get 28.11, while the bicubic is on 23. And this one is we adding the depth buffer. The depth buffer is not obtained like you run a segmentation, you get a depth on the photo. No, you don't have to, because depth buffer is from the GPU pipeline. So you can get that data very easily. Why we consider depth, because for the far away object, so it's intended to be blurry. It doesn't need to be upscaled very well. So you have some tolerance. So the middle one is we added the depth into the training. The PSNR is improved a little bit, and we also want, because it's far and the near, and there are more contrast. So we think that the contrast, we want to have some more measurable data. So we compare their root media squared contrast. We found the contrast is much better. It's better than the RGB only, and but anyway, the HR, the ground truth, is still the best. Also, because you add in the depth, the size, your model size just increase a little bit. So this is with compared to other models. This is data from the Zen Garden, our second data set. you see the bicubic is the worst, and RenderSR with sharpening, without sharpening. I will talk about sharpen later. And it's 28.11, and with depths a little bit higher, 28.3. You see other models, they are pretty big. So of course our PSNR is behind other big models, but I think but not so far away, just a little bit less. We also compare with other interpolation-based solutions like AMD's FSR. So the left one is FSR, the right one is RS, is our solution. You see the mountains on the right corner, and it's the FSR is blurry. Also, the leaves on the rectangle. The RenderSR is more differentiable. Also, on the bracket, the number is the PSNR value. So this is the RenderSR with a sharpening. So the first picture is without sharpening. Just this one we enable sharpening. Why we enable sharpening? Because our loss function is L1. And we found the L1 loss function, they tends to, it's norm loss. It tends to blend the high frequency signal and the low frequency signal together. So make the picture, I mean, more smoothly, but cartoon-like. So we use a sharpening filter to block some certain low frequency. So to make the picture more crispy. However, the cost is the PSNR value, but is downgraded. However, we asked for our reviewer about, and they all said that the right picture, the sharpening picture is better, much better visually. So this is the sharpening versus the ground truth. Some people said it's not indistinguishable for them, and someone even said the sharpening, the RenderSR plus sharpening is even better than ground truth. However, we still have some limitations. For the tiny objects like the grass, they are clustered together. It's not as good as the ground truth. That's because our model is very small, so it can't like recognize so low fine details. But for the big objects like the tree trunk, the cloud, the mountains, it's very good visually. Also, this is a movie. The left one is a ground truth. Some performance data. This is very initial performance data. So we upscale for 540p to the 1K frame. And we first test on the desktop entry-level GPU. That's NVIDIA 5500. And we use OpenCL kernels. The teraflop is 5.2, and for the FB32, that's our default model, is 13 something, and it's very close to our goal, 12.5, 80 FPS. So I think we see from the desktop level GPU as this approach is fairly practical. However, when we move to the mobile platform, this Snapdragon 855, so 8 years ago, our SoC kind of old. and we found the FP16 is 200 milliseconds. This is we get this data based on the AI benchmarks projection. AI benchmark accept our model, but it's only since it's only upscale 128 by 128 or 256, I forget. It doesn't accept a whole 540p frame. So this data is based on the projection. It's very conservative because when you upscale the lower image and higher image, you share you share the same overhead. So we think 200 milliseconds is too conservative. And the software stack is TensorFlow Lite dedicated. Of course, it's the mobile GPU is performance. TensorFlow is much behind to the entry-level GPU, discrete GPU. Because this performance on the mobile GPU's performance, so we propose another the NPU solution. This is future work. We haven't fully implemented this one yet, and it's pipelining between the GPU and sorry, that's the typo. Pipelining between the GPU and NPU. So basically, the GPU render just focus on the rendering, and let the NPU to do the super resolution, to do the upscaling and send it to the display. The NPU has much bigger computing capability, and recent NPUs they all have the FP16's data type support. And basically, based on what you need, you might have to fine tune this pipeline a little bit. Depends what you want to upscale. So if you upscale the final image, the final image, they probably have some text, and that text is 2D rendering. And if you for our initial internal evaluation, the upscaling the text is hard. So if you upscale the final image, this pipelining probably works for you. But if you only upscale the pipelining inside the GPU, like you only upscale the 3D rendering image, and you still leave the 2D overlay, text overlay to the GPU, then you probably need to modify this pipelining a little bit, and you have to hand over the NPU upscale result back to GPU and let GPU to do the final blend. And also the current software stack, the current software stack, like the previous PP mentioned, the inference engine might have to be modified a little bit, because for me, the current software stack, the NPU, they accept the jobs from the CPU. Well, if you want to pipeline between the CPU, GPU, then probably GPU and NPU probably have to not go through the current software stack, but design a special route from between the GPU and the NPU. So some take-home message. The N-based solution is much better than interpolation-based, whatever the cubicle or FSR. And even with very small size, like 40K, and you can get very better results. The industry and academia still like a reliable scientific metric for the image evaluation. Sorry, is a typo. Like the PSNR might be can still be used as sanity check, but it doesn't necessarily correlate to your subjective image quality. And L1 loss, like normal loss, tends to blend the low and high signal together. Well, a sharpening filter can block some certain low frequency signals after your SR and make the frame more crispy. Finally, the pipeline between the GPU and the NPU for upscaling is more variable than the GPU-only solution on the mobile GPU for performance perspective. So that's all. That's my presentation. Question?
Thanks a lot for the talk. Yes, are there any questions? Okay, maybe I have one.
No.
Okay, so I have one question.
Sure.
I will speak here so they can hear me also.
Mm-hmm.
So I saw the solutions from last year mobile AI super resolution challenge.
Mm-hmm.
And some guys did something, I think, quite smart. They use bicubic interpolation as a baseline. And what they do is they merge the bicubic interpolation result plus whatever a neural network produces. It's like with the bicubic interpolation, you kind of upscale. Obviously, you don't have details, but kind of you can upscale the structure, and then with the neural network, you learn kind of a residual to sharpen and improve the details.
Yeah, some models actually do this. I believe some models they do this one. They do upscaling by cubic first, like SRC. So and then directly work on the, because upscaling you get the high resolution, right? You get a high frame, you have more pixels. So the cost is your computation will be increased because after all, if you put upscaling by cubic first on the first layer, then all your computation will like quadruple. Will be increased 4 times.
That means that basically what they do is kind of skip connection, like in a residual network. So they do the bicubic interpolation, and they learn kind of upscaling details with the neural network from the low resolution image, and then they merge both.
Oh, you mean merge? Okay,
yeah.
Like a residual.
Yeah.
Yeah, I think it's promising.
It's like to add details to the bicubic interpolation.
Yeah, I think it's a good approach. Yeah. Mm-hmm. Actually, yeah, we can just overlay them together, blend them together. Yeah, we can try that. Mm-hmm. Thank you for comments.
Yeah, I have also one question, more or less technical question. So you mentioned AMD FSR technology, and so the latest Exynos chipset, it's using also AMD-based GPU. So is this FSR upscaling available on the latest Samsung chipset?
Yeah. So let's go back. I see what you mean. So yeah, right. So
yes, because here it's desktop chipset, but the latest Samsung mobile chipset is also using AMD graphics. So, and yeah, the question is whether AMD FSR technology is available on Exynos 2200.
Right. So our latest Galaxy S22, like selling in Europe, not selling in the US, is based on like the SoC.
Yes.
And it is we partner with AMD to use their RTMH2 like technology for the GPU core, and we use OpenCL stack as well. So this Navi is Navi core, Navi 1, I think, or Navi 2, forget. Yeah, the software stack is there, but we need, since it is our first first new GPU SoC, so we still need to do some performance tuning on the software stack. Yeah, the best is yet to come.
Okay, yeah, I guess this answered my question. Okay, then if there are no other questions, we are moving to the next talk called an efficient hybrid model for low light image enhancement and mobile devices.
You guys, can you hear me?
Yes, we can hear you.
Let me just share my screen. Give me a second.
Wait, Andrey, wait 1 second, because I have to switch the laptop to put the presentation properly here. So wait just 1 minute.
Okay, yeah, you can just start sharing the screen, and we need to wait a few seconds to.
Okay, and yeah, I just want to say before I go in there, share my screen. We can share my screen right now, yeah?
Yeah, I mean, you can start sharing your screen. We just need to wait maybe a few seconds till the guys fix everything and see.
Okay, first thing, before I start, I want to thank Andrew and Randall for hosting this event. I think this is a very good workshop, and actually is an excellent bridge to combine the industrial with the academia. And there's lots of industrial questions academia sometimes we just put aside. We can share the different opinions. I think this is very good. And hopefully next year we can just in person and discuss more details about the, the problem there. Yeah, I just want to thank you guys for hosting this event.
Well, we should also thank you because you're actually creating the material for this workshop. Without you, there won't be a workshop.
Just let me know when ready to go.
So is everything finalized in room 219? Okay, yeah, so we can start.
Okay, first, good afternoon, everyone, and good evening, good morning, different time zone area. So my name is Jicheng Fu from Lenovo Research, Chicago, USA there. And today I want to share with you our project, and we call efficient hybrid models for low light image enhancement in mobile devices. And from this title, there's some keywords I want to highlight here. The first thing is efficient and hybrid. From the model perspective, our domain area is low light image enhancement, especially in the mobile devices. And refer to the low light in the mobile devices, I think most of you experience the bad, experience when you go outside, hang out with your friends in the restaurant, for example, at night, and in the evening, you want to capture the beautiful scenes, night vision, or you want to capture the picture with your friends, and the restaurant light is not enough. You can high possibility to experience the image degradation problem there. When we refer to the image degradation, we refer to some such as low visibility, noise, low contrast, and color loss there. So I also list some images there, and you can tell there's different levels of the image degradation there. And this, the low light images problem is existing for a long time, especially recent years as the smartphone just pop out is popular. And this is like a battle area. Different companies want to focus to, I cannot let our customer to bear this problem. Let's just increase this problem. So there are actually two high approaches on this problem. They are the first thing, of course, hardware. If you have better sensor, of course you have better image information, you can capture that. It's another one is like software. So in this product, we focus on the software level. When we talk about the, from the algorithm, like software level, giving formulate this problem, like giving a low light image, we always want to find the most appropriate functions to do the transform the low light image to be a better one, an enhanced image we call it. So we call this function as a combination of different operations there, such as a very simple one, linear, like again on the plus bias, and also there's some complicated, even the deep learning, we can just say there's a combination of different features, combined as a function. So the goal is how can we find the most appropriate functions for our problem there. And besides of finding these functions, you have to think about this, our domain area is mobile device. When we talk about mobile device, for example, I'll give you an example of our company model, products there. We always want to ensure, because we have some resource, constraint there. For example, the memory is less than 500 megabyte, and also the FPS should be, at least 15 for the resolution 1440 by 1080. It's part of viewfinder. So we have the specific KPI there and a constrained resource there. How can you balance the functions, the ability versus the resource consumption there? So when we have this problem, of course, when we do research, we always want to look back the state of art to see whether there existing some algorithm can help us solve this problem, or at least can inspire us to solve this problem. Of course, I think many of you can familiar with some old, traditional, but still widely used in current industrial, for example, the histogram equalization, and also the gum correction still in the 3A there. And even there's some complicated algorithm like the Retinabix there. But it's during the past 5 or 10 years, the CNN-based pop out. Why? Because the math algorithm we just talked about that you still need, they have limited parameters. And you also need or rely on the expert tunings on this limited parameters with limited user cases. However, the AI CNN-based, such as CNN-based network can, can just release the burden of the expert's experience, can just learn the parameter, the most, tunable parameter from the ground truth. And that's why I think there's just blooming and there's excellent work just pop out to show how this deep learning work has done greatly in the improve the image quality there. So our work actually is inspired, for example, especially for the HDRNet and the DSLR. I think the DSLR is also written by Andrew. So, and another one learn to see in the dark and the GAN-based models. But now we have 2 different categories of the algorithm there. But when we want to deploy this algorithm into our mobile side, we found, oh, this is not, is what we actually totally can solve our problem. Why? They have some, of course, they have some pros and cons of for example, the math model. Like I mentioned that you can obviously get an illumination improve with a constrained user cases. But if the user case is beyond the assumption the algorithm have made or beyond the parameter tuning ability to make, artifacts just pop out, noise, and even the information loss. You can see there's a comparison I show you guys. Definitely, this is not good enough to deliver answer product. So now we just switch to the deep learning. Yeah, deep learning, of course, give us a better image quality. It's as close as to the ground truth as the better one. We think the better one, ground truth here, we refer to this is the one the customer will be happy with. But always we have to fix the problem, the first data set. Second thing, the mobile side, they have computational resource and running time constraints there. Like the CVPR conference, the majority papers and training, even deploy inference on the cloud AI. But when we transfer their algorithm to the mobile side, actually we cannot repeat this, we cannot get the same levels of image quality, and as well as make sure the running time, the computational resource is within our KPI. So how to solve this challenge, how to get a better image quality while get a the low computational cost is the problem there. Actually, this is the one that inspires us to propose this hybrid model. So when we talk about hybrid model is we just want to use a very tiny, fast deep learning models to recover the missing semantic information from the low resolution input. Then we can get a low resolution, output with a better, semantic information recover. So we use United ArrayNet as a backbone. Then people just wondering, okay, you have the low resolution one. How can you get the bigger one, the higher resolution one? So that one is we're based on the guided filter, try to estimate the transformation relationship between the 2 lows, then apply to the high resolution. Then we can get we can combine them together to form a hybrid model, and we can get a better image quality while ensuring real-time processing. Now I share with you this hybrid approach flow. The first thing, of course, we have high resolution, low light input. Here I mean just single frame there, and we downsample to a tiny dimension. Then we use the United ArrayNet to train the model and predict the model. As once we have the predict images, we can use the guided filter strategy to try to estimate the alpha and beta. We call this alpha and a linear, like a gain and a bias, transformation relationship between the high resolution to the high resolution output. Then we can easily apply this linear algorithm on this high resolution low light to generate high resolution output. So that's actually we call this hybrid, because all the stuff, the guided filter here, this to estimate the transformation relationship, we call it non-trainable layers, which means that's we call this hybrid. So I think I have talked the overall architecture. Now I'll give you the performance of our model. And we evaluate our model based on different chips. Actually, it's based on the Snapdragon chipset, it's Qualcomm. And we have some different GPU configuration. You can show the different running time. This is all 4040 by 1080. And our focus actually is the bottom. Now you see the bottom. Why the bottom? Because that one, actually, the price is cheap. So it's the price based on this kind of hardware currently on the market is about $500, which means you have low cost, but you can experience the better image quality. That is attractive. Now I show you guys demos to show how good our model is on the real case. We call it see in the dark. And now this is the viewfinder there. In case this is me there, that is without algorithm, without algorithm there. And also this algorithm, this can extend to the snapshot. We can do the snapshot easily based on the modification of this, but the back, we share the same backbone. And yeah, this is me. And also we send this one to the third party, and we can easily apply for the video calls, and it's the different, based on a little bit in the configurations change on this one. I think this model showed the promising results. Also, we show another concept here is we also compare with, this is our model, this is without our model with same device, and different competitors. And it's from this video, you can barely see, you can apparently show their Apple is the king. But you see the price, yep, which means the better price give you a better sensor. And of course, they have, other ones that algorithm in the Apple. But what I want to deliver here is the gap cost, caused by the different sensor. We can use algorithm to catch up. So now back to our model itself. Since we have architecture, what's the next? Of course, dataset. And also, as mentioned, that we use the supervised training, which means the image should be pairs. And then in order to capture the image, without the misalignment issues, and so we designed a special hack into our own phone there to create a tool to capture the auto exposure as the low light image, and also to enable the long exposure as the ground trace. So the long exposure is calculated based on the current, the lux level, and sometimes it's as long as the 32 seconds to generate the ground trace there. And currently we have accumulated over 5K image pairs, and which is still increasing. And based on the first 3K, you can see the different lux range we have collected there. And if you guys are interested in the data, please feel free to reach out to us. So the next one is, like I mentioned, that is the whole architecture there. This is the learning-based model, and this is the not learning and non-trainable for the estimation, which means can ensure the fast processing time there. So now I want to share with you guys some experience when we do this low light project and deploy on the phone side. And we know the convolution algorithm right now is the most popular one is convoluted and separate convoluted. And for this low light, so separate convoluted can definitely decrease the running time and also decrease the memory cost. But the thing is, the separate convoluted here can cause a little bit more blur than the convoluted. That's what we noticed. Want to share with you guys. Of course, the different loss function there, the quality issue. Since we use the UNet as the backbone there, when we just upsampling there, and we compare with upsampling like bilinear interpolation, why we choose that? Because this one is supported by the GPU acceleration there. And the transpose convoluted will cost a lot of parameters, but we didn't see too much on the image quality difference there. And another one is pooling master. So when the low light there, you want to improve the overall brightness, sometimes it can generate overexposure issues. Based on evaluation, we find that using the max pooling, can much more easy to cause the overexposure issue than the average. And also the padding master there, the same. We find this is very interesting there. If we use the padding method, use the same plus separate color 2D, and our results will be, experience some border issues, which means on the border of the image is always in artifact state. But if we, switch to the color 2D, and the border issues just disappear. I think you guys can find the root cause because the different calculation strategy versus separate color 2D versus color 2D. And in order to this one, and also enjoy the fast runtime and memory reduction on the separate color 2D, we use the reflect, the padding. And also, since this is a phone side, the phone side, when you get a sensor, is raw, then you get a YUV there, it's not RGB. So how to combine the different Y and UV layers to do the processing, because the U and the Y and the UV, they do not share, the different, they do not share the same syntactic information, especially for the features information there. It's different from the RGB. There, how to combine them together is still a problem there, ongoing. So now I just tell you guys, okay, what do we have done to generate a low resolution input to the output with the model? Now we have this one. The thing is, how can we get a, do the high resolution output? Of course, there's multiple, functions there. And the most attractive here, we use the guided filter. And now you can see based on the guided filter hours, you can tell the image quality is clear and better. And that's why we call this one is like try to use a guided filter to learn to estimate the transformation relationship between from the low resolution input to output and mapping back to the high resolution input to the output. I think that's the overall architecture of our model. And the future work is always we want to have a better image quality and less computational resource. And then we find another challenge, how to actually do the image, IQ measurement. PSNR offers no. Sometimes in the real industrial, we just use the subjective measurements there based on huge people evolving to give a score. And also continually like the model optimization, like the TensorFlow recommend the post quantization and ensure your channel number can divide by 4. And also they provide the proving. But when we actually use the proving there, we find the proving only support the limited operations to do that. And for example, how can I ensure the reshape function can be dedicated by GPU? Is still a problem there for GPU and CPU dedication, support, and scheduling there. And also, we still want to expand our external collaborations for researching these advanced solutions. And feel free to reach out if you are interested and want cooperation. Also, we are hiring if you want to interested in this topic and join us. Please find the information in this slides. And yeah, I think that is our work just from the research. And any questions, comments, or suggestions? Thank you, guys.
Thanks a lot for the presentation. Are there any questions? Yeah.
Okay, very nice work there.
Thank you.
You are mentioning that you have a large data set that you collected.
Yeah.
Okay, this data set, you are planning to release it, to make it public?
We want to release public. But if you just want to right now, for your group one now, we definitely share direct to you. And if we want to public, definitely I have to confirm, and our team have to confirm our legislation group. But like I mentioned, the cooperation there, if like such as your facility wants to cooperate, definitely we would like to share, because this is definitely can accumulate or accelerate the research problem there.
Another question that I have, did you try to apply for video? Okay, so you are doing your enhancement in each image separately. But did you evaluate what happens if actually you are applying on a video stream?
We do. We did. And the thing is, on the video side, there's two things. And first, the KPI will change. The KPI means the running time and the size. And actually, when you want to deploy the video, we have to work close with the product team to ensure, how much buffer time they give to us, how much, the resource they give to us. But that one sometimes constrain our ability. They say, okay, this is now, you guys video, because it's continuous streaming there. Like this morning, the Qualcomm director is sharing is how can we solve it? The product team doesn't like it. Okay, it's just affected other components on my device. I would definitely not let you do that. So I think this is ongoing research. Definitely, we are working on that one. But right now, we still need to have a better strategy for scheduling from the the software level, especially for example for the phone side from chip level. Yeah, from the feature 2 based on the Qualcomm, how can we just smart scheduling these resources? That's why I just mentioned the GPU scheduling, and I also GPU scheduling from for the Qualcomm, and we hopefully whether they can provide or because otherwise different company will have different standards for scheduling. That would be a mess actually.
Always.
Mm-hmm.
Okay, those were my 2 questions. I don't know. There are some other questions, Andrey?
I'm just curious if this solution is used in some commercial products.
Sorry, I didn't get it.
Is the solution used in some commercial products?
No, I don't think so.
Not yet.
Let me see. Yeah, I'm just. I think this should be fine. Yeah.
Okay.
Mm-hmm.
Okay. So, any other questions?
Okay. If no, I thank you guys. And move to the next one.
Thank you.
Yes. Thank you too.
Mm-hmm.
Okay, and now we are moving to the next presentation. 2 presentations from Fausto. This presentation is called PhoneDepth and Dataset for Monocular depth estimation on mobile devices. Hi, Fausto.
Hi all. Can you hear me now?
Yes.
Okay, I'll go on and share the screen. I'm hoping you guys can see that now.
Yes.
Okay. Good. So good morning, good afternoon, good evening to all of you, wherever you are. So I'm Fausto Tapia. First of all, I'm gonna present you this paper about PhoneDepth, presented a new dataset for monocular depth estimation on mobile devices. So this is the agenda for today. We'll go through some problem definition and related work descriptions first, to then later on go into depth about our dataset and how we evaluated it. To later on go with some visual examples and end up with the conclusions or recommendations. So let's start with some problem definitions. So first of all, the depth estimation from images has been some problems somewhat studied up to now because of different applications like robotics or and so on. Now, what we want to focus on now is to use information available in mobile phones, on mobile devices, to being able to acquire accurate and depth maps and as fast as possible. So this is the main focus that we put onto our dataset. So there are different things that mobile phones now provide. So normally they used to have they have images, so from normal cameras, but also some more modern phones also have depth sensors that are not so accurate in a sense. So let's go through some related work now. Yep, so here's a table about different data sets available out there as of now. there's a couple of details we could talk about there, but the main issues that that we can encounter are typically that none of them have perfect characteristics. So for typical issues of different datasets they are either too small. For instance, the ones that have big image resolutions are very small, but also most of them provide highly sparse dataset. Highly sparse depth maps, meaning even the ones that say that their depth maps are dense in a sense, they're not completely dense. And also, well, again, low image resolutions, and many are very niche to their application. In this case, for instance, almost all, I would say half of them go for the approach of solving autonomous driving problems. So let's describe a bit our dataset now. So each sample in our dataset comprises of 2 streams, one per different phone. So you will see what I mean by each phone. So we have 2 phones here, and I'll describe the hardware itself later. So each stream of corresponding to each phone has one phone image, one phone depth map, meaning the depth map acquired from the hardware in the phone itself. Then another depth map corresponding from an external sensor to that is then projected into the same frame, and a confidence map for this depth map, the last one I mentioned. So the dataset comprises of total of around 6,000 images or samples per se, so meaning sets of these images of these a set of these number of images and depth maps that I just mentioned, from which we have indoors and outdoors of around 4,800 images indoors in different buildings and sites, and also outdoors are around 1,200 images. Again, different neighborhoods, urban areas. Just as a reminder, this was actually collected in the city of Zurich, and so that's there. Okay, so moving on. Now we saw this table before, and now I just added our dataset to this in the last row. So just again to mention a couple of things that our dataset has more as an advantage compared to others, even though ours is not relatively big. But we have high image resolution and also high resolution of depth maps, but also different depth sources because we use 3 different devices. So we have depth source of time-of-flight sensors and dual pixel sensors, and also from a professional stereo camera. Furthermore, the density of our depth maps is high compared to other, very high compared to other datasets, and yeah, and we also provide true depth. So let's go forward now about our data collection procedures. So in terms of hardware, we use the rig you see on the right. So remember, I was talking about phone 1 and phone 2 before. So phone 1 is the one on the right in this image. Is a Huawei P40 Pro with the time-of-flight sensor, and the other phone is a Google Pixel 2 with a dual pixel sensor. Meaning these sensors are the ones that provide the depth in these devices. Then for actual ground truth mainly reference, we use a set camera, which is a stereo-based camera, which is the one you see in the middle there, with some specific settings. So we set it so that we can measure from 0.2 meters to 10 meters and some confidence to allow for enough, good enough density in the depth maps acquired. So in terms of actual collection procedures, just to avoid nuisances of having to actually synchronize all the settings directly, we used a fixed rig as the one you have there with the static scenes as well. Additionally, we had some software there with an app for acquiring them in a simultaneous way for just ease of collection that used ADB and obviously an interface with the set software. Additionally, we used various heights for data collection just to give some variability. Okay, so now about data processing, there were a couple of steps for processing the data. So as you know, we have 3 different streams for depth, and the goal is to represent different depth maps in each phone. So it's available in each frame. So the first step was image decoding. So the phone images are encoded, the depth maps of the phones are actually encoded within the images themselves. So there's some work there to do. So basically we just decoded the images there. Then the next but more important task was actually acquiring dense, good-looking depth maps for the set camera itself. So there's a couple of parameters that can be set there. So in general, adding more filtering gives somewhat degradation and degradation effects in terms of density, which is what you see as we move to the right. So if you get these parameters just right, you can get a nice and dense depth map as the one on the left. Again, these depth maps are using the proprietary set camera algorithm, just changing some of their parameters. In order to get these depth maps from this stereo camera into the phone frames, there's different approaches that can be taken. So now what you can see in the images there is the ones on the top are the image on the frame from the set camera, and the one on the bottom is from one of the phones. So are comparing here 2 approaches. One approach is the one we actually used, and the other approach is one that we tried also. So the geometry-based approach there is using camera calibration and then reprojection of depth maps into the other camera frames, which because mainly of different field of views and resolutions between the cameras ends up with this effect of kind of sampling effect that you can see there, which is why we moved to use another method, which is by using a dense matching technique. In this case, we used a PDCnet technique that I have referenced here. It's a deep learning based method developed by Wong. And basically from here, what we do is match depth maps to the other depth map given optical flow from the images, from the RGB color images. So in terms of evaluating our dataset, there's a few first setup here. So we use 3 different datasets to evaluate this. So first MediaTek dataset, the mobile AI challenge dataset as well for depth estimation, of course, and our dataset. We use a regression approach for different models that I'll mention in a bit. And for latency measurements, we used but with the AI benchmark and obviously optimized models in TF-Lite. In terms of losses, we use the normal MediaTek loss. comprise those scale invariant mean squared error, gradient error, and ordinal loss. And the ordinal loss was not actually used in the datasets that do not have ordinal samples. And for reporting more metrics, we also have used RMSE, absolute relative error, and the scale invariant RMSE. And this last one is the one that we mostly focused on. So now we have 3 different branch of experiments that we did for showing the value of this dataset. So one of them here is using the two different ways of training. So first, the typical way of training is the one on the left, showing basically that you have an image, then you pass it through a neural network that is trained in a way, and to obtain a depth map. And then you have a supervision only from a ground truth depth to calculate the loss. Now, because we have for each phone, we have 2 different depth maps, we can leverage both of them. So this other type of training, that topology that we define here, is I2DP. And what we do there is use one of them for the accurate one for actual scaling, for actual error estimation, and the other one for gradient error estimation, because it's more gradient acute. So then we did this topology with 3 different models: FastDepth, which is one standard one; Park model, which is one of which is the winner from last Mobile AI depth estimation challenge, and we also introduced another network, which is bigger than the others, just for reference, which is using EfficientNet before as a NEC encoder and Parks decoder. For almost all of the metrics here, we can see improvements of around 2 to 3% in scale invariant RMSE, and also in the other measurements, which I would say you can check more in detail when you read the paper. So the second type of evaluation we did was actually using pre-training. So what happened here was we trained from scratch on PhoneDepth and then fine-tuned on these other MediaTek and Mobile AI datasets to see how much we can improve, and also trained, of course, from scratch only on these other datasets. So what the results show here is again a good improvement on performance for the case of the Mobile AI challenge, especially in the scale invariant RMSE, but also in the other metrics. However, in the case of MediaTek, it is less clear. Yeah, mainly because the MediaTek dataset is much larger. Now let's move on to the other type of evaluation. So remember these 2 graphs of I2P and I2DP types of training that I mentioned before. Now, because phones also have a depth estimate from their local sensors, we can also introduce another type of training, which would also imply another type of network that takes the images and raw depths as inputs. So they're basically the same as the ones on the top, but having the raw depth from the phone sensors. So in order to do this, of course, we cannot use the same networks. We also need to put the depth initial estimate as into the network. So this is the actual architecture of the network implemented for this purpose. It's nothing too fancy, it's just for didactical purposes, for showing how things improve once we use this topology of training. So, and yeah, and in this architecture, we have an encoder, which is the one we mentioned before, the decoder, which is a park decoder, and then we have a lightweight depth encoder in the middle that basically concatenates features at different levels. So for this experiment, there is, again, different types of models, mostly the same, actually, but trained in a different way, except from the last model, which is the one that introduces depth as, the last two, sorry, that introduce depth also as an input. And we can clearly see big improvements here in scaling variant RSME, but also in the other metrics, meaning that there is value to add there from this type of training. Let's show some visual examples of how the things look like in this type of networks. So these are, yeah, from left to right, we can see first images, input images, then a projected depth, which is depth projected to the camera frame, to the phone camera frame from the set camera, which is the ground truth per se, and then the phone depth, which is only 8-bit resolution, and that can be used as an input or just for training. So that depending on the different topology. And then we have all the other different topologies of training that can be available from our dataset. And as you can see, as we move from left to right, where we use more, it means that we use more inputs, input depths. So if we start from the left, we only use one depth for supervision. Then, when we move to the right, we use 2 depths for supervision and also 1 depth for as an input. So again, as we move from left to right, there's quite big improvement in terms of sharper edges, but also accuracy, as you saw in the previous slide table. So let's go for conclusions now. So yeah, we introduced a depth estimation or enhancement dataset for mobile devices specifically, where we have 3 different depth sources with good depth map density, but also high image resolution. And a good thing that we also include is confidence maps. Another contribution here is the introduction of this depth refinement task, which is now possible because of new hardware and not so new, but actually hardware that there is in current mobile phones, meaning that we also have depth maps available, or some raw depth maps available. So as per what is next in this train, I would say for sure during this paper we didn't use the confidence maps, which we think would be high value later on, especially for convergence and convergence during training. But also this data set would enable further research on depth enhancement for mobile devices especially. So, yep, that was all from my side. Thank you very much. And I'm happy to hear questions.
Thanks for the presentation. So are there any questions? Okay, there is a question from Sinson. Can you elaborate how you are going to use confident map for the training?
Yeah, sure. So the confidence map could, so depending on, there are different regions in the images that can either because of the mapping or because of the actual sensor accuracy, don't provide a very accurate estimate. And this is the case usually for stereo cameras. So a way of using the confidence map is to weight down the pixels, the pixel errors in the regions that are not where you know that the estimate is not good enough, and that is one of the points that cause sometimes training not to work properly or reach suboptimal levels. I don't know if that's answered the question.
So, no, yeah, this answered his question. So, thanks a lot for the presentation. And we are then moving to the next talk, to the next paper presentation called SMM-Conv, Scalar matrix multiplication with zero packing for accelerated convolution.
Hello, hi everybody.
Hi, Gil.
Okay, so this is the work of my student, Amir Ophir. And the title is SMM-Conv, Scalar matrix multiplication with zero packing for accelerated convolution. So the goal is actually to be able to implement convolution in a more efficient way. We specifically talk about inference only on CPU-based architectures. So what do we want? We want two things, basically. We want to be able to execute the convolution faster than previous approaches. And if we can, we would also like to reduce the memory overhead. So this is, of course, an important task, since convolution is ubiquitous and basically in every convolution, almost in every convolutional network, we would like to accelerate it. So basically, up to recently, the most common method to execute convolution was the IM2 call. What does it mean? The idea of IM2 call is to pack the windows one near each other as the columns of a matrix. So in this way, we can take a kernel, maybe one or two, and then use them as, for example, a matrix with, in this example, 2 rows. And then we have actually 2 matrices, one for the kernels and one that actually contains all the sub windows. So basically, when we pack it this way, we can see that there is overlapping, there is a redundancy. For example, the first window and the second sub window share the same numbers. And it goes on and on and on. So basically, when we do it this way, there is also, of course, additional memory that we use, since we use the same number for again and again for each column. And also because of the size of the matrix, there is a problem with the multiplication. However, why we want to do it in such a way? Since basically the rationale is that matrix multiplication is very fast. So even if we have all this memory overhead and inefficient memory access, we can still implement convolution in a very efficient way. Okay, so previous works, basically, there are 2 notable previous works, there are a lot. Direct convolution showed that we can implement convolution directly in inner loops, and it works quite fast, but it works only for channel last configuration. And there is MEC, the memory efficient convolution, which actually still use GEMM and packing, but the packing is more efficient, but they still have packing. Okay, so what is the benefit? What are the benefits of our approach? We do zero packing. It means that there is no redundancy in the way that we implement the convolution. We use scalar matrix multiplication instead of matrix multiplication. We also use the same memory buffer to perform several convolutions in order to save memory. And we can work in both channels first and channels last configurations. So the key idea, previously, when we would like to, suppose we have a kernel and we have an input, an image, so we can actually see the aim to call as multiplication, element-wise multiplication between submatrices. The key idea behind our method is that we can actually see convolution as a linear combination of the kernel's coefficients. How is that? Each coefficient corresponds to submatrix, and by aligning them, we can actually multiply each coefficient with the corresponding submatrix and sum them to get the final result that we want. So instead of coupling together all the coefficients of the kernel and then trying to multiply them with each sub-window, we in effect sort of separate them. So how can we see it? So if we take, for example, a simple example, we can take an element in a kernel, we can actually compute exactly to which submatrix is associated with it. And we know it beforehand. So basically all we need to do is we need to identify the submatrices for each of the element of the kernel, and then simply multiply them and sum them. So, and of course, it goes with not only kernel of one, with every generic kernel. So how do we do that? We simply take the first sub-window that we can compute beforehand and multiply it by the corresponding element in the kernel, take the second window, etc., and then sum them together. So basically the multiplication here is done by using scalar matrix multiplication, which is also very fast. Okay, so basically we have zero packing. The reason that there is zero packing because we only use each of the, I will show you later, we actually do not duplicate the same number. I will show you later in the configuration how we apply it. However, we would like also to use the same memory buffer as much as we can. So how do we do it? So there are basically two ways to do it. We actually take a submatrix, which includes two windows. In this example, it can be much more. And then we multiply the appropriate value, the appropriate kernel coefficient with the corresponding window, sub-window. So basically we slice it. We slice this sub-window, and for the first sub-window, we multiply by the first coefficient, and the second sub-window, we multiply with the second coefficient. So we use actually the same memory for both windows. This is the reason that we actually reuse the memory and we don't duplicate it. So this is the generic format. So in this case, we move vertically instead of horizontally. So suppose we have a kernel as an input and we have an image. We take a slice of the image, which we know beforehand since exactly how to slice it. And then we multiply the corresponding coefficient with the appropriate submetrics. We use the same memory. Note that here, 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 and here, it is the same memory buffer. And then we only take the appropriate sub-window and multiply it with the appropriate coefficient. And we sum them all. And we can do it again and again for different sub-matrices according to the structure of the kernel. And eventually, we sum all of the multiplication together, and we get the results that we want. So basically, it can be seen that this is actually a linear combination of the kernel of the sub-windows when we use the kernel coefficients as the coefficients for this linear combination. Okay, so in terms of memory, we can, of course, gain, we do it much more efficiently, and we can see that since we reuse the same buffer in order to do the multiplication, we can save a lot of memory. So there is actually two versions: single-threaded SMM convolution that is straightforward. We multiply, we slice, we multiply, as we've seen before. And we also have the parallel version. In the parallel version, of course, we can slice in parallel several sub-windows. So how does it work? We compared our approach with different methods. It can be seen that our gain a significant speed up. We can see that compared to make and time to call, our approach is very fast. So we also evaluate the performance, the speed up relatively to each layer, how much we accelerate the computation of each layer. And we can see both in AlexNet and in VGG and in YOLO V3, our approach presents a very nice speed up. So the key question that we actually wanted to know, how we can scale, how we can scale the model. So basically, it can be seen that when we use, for example, 32 on 32 and 64 on 64, the input size, we can still gain significant speed up, where the dashed line is the baseline is IM to call. That's it. Oh, one more thing. We can also see that if we can, if we increase the input channels, what is the effect on our speed up? And we can see that even if we use a very large amount of input channels, like 256, we can still introduce a significant speed up. Thank you.
Thanks a lot for the presentation. Are there any questions? Okay, seems that there are no questions. Then again, thanks a lot for presenting this paper. And this was the last presentation for today. So thanks everyone who was watching us, who stayed with us more than 6 hours. We hope that you learned something, and maybe you learned even a lot during this workshop. And again, hope to see you all next year. So hopefully we'll have this annual event next webinar as well. And yeah, those who are participating in the competitions, in the mobile AI competitions, we would see you at this autumn. And yeah, we wish you to get good results in these challenges. And those of you who did not yet participated in the mobile AI competitions, you still have your chance. There are still you still have more than 1 month to develop efficient solutions for mobile devices. So you can you can still do quite a lot. So yeah, thanks everyone who was watching us, and then we are finishing it. We're finishing our event. Okay, bye guys.
Thank you, Marcos.